Switch for that. It'll work. Check, check. I marked on the bottom, but obviously when they're thrown around, you wouldn't know. I noticed in other rooms they put gaff on the side.
Yeah, I think people want you have gaff, you can do that to one if you want. Okay.
Boxes. I asked the guy if he wanted it up front. He was like, no, other people are going to throw them. And I was like, okay.
Quick question. Do you know anything about this thing, or you do this?
I just do this. And then I'll just be kind of like in and out a bunch. I'll be here like when they start sessions and end sessions. And then during sessions, I guess I'm supposed to not be in here. Oh, that doesn't make sense. Why don't I just sit here the whole time?
You're probably gonna have to be here to wait on exactly like the moment where they switch to questions at the end to do this part.
Well, if they're already on, they just,
Want to actually hand it to the, like, go out there and
they said someone else was going to throw them. Right?
they told me that well, the audio person is gonna be.
Well, we were told not to be in the room, so
Well, somebody's gonna, I mean, unless right now you wanna leave it on the side, or they're probably just gonna say, the speaker's gonna put it on audio, they're gonna always just go to the tech people and just be like, hey, but I have to stay up here, so it's gonna be,
I won't be in here. But
like, he was like, either way, somebody, when they finish talking, they're just gonna set it somewhere. So maybe it'll just be floating around the room or something.
they'll be on, and everybody will just hear them whisper. It's not hot
I thought
enough
this
for
was
them to
audio.
hear us right now. It is.
And then, like, cause you're gonna be the one muting or unmuting or handling the microphones and things.
Because we were told just like make sure it sounds good when they start, and then walk out.
What? I was told someone's gonna be here like the whole time, like.
That's not what we were told. I'll just be coming by every 30 minutes, every session.
If it gets awkward, I'll just, and they're looking for somebody, I will figure out what I need to do, and if it's just me. Well, I was just gonna ask him, do I click record on here, but you're already recording a separate.
Well, this stuff is sent over to there, so you might have to hit record on there. I don't know. So they're under the impression that there's a tech in here all the time.
For giving, administering this microphone, for the Q&A part,
Yeah,
to actually take it from here down into the audience and do that part.
I left it at the front and
Let's leave this at the front and someone can take this
one in the
down.
back. Yeah, that's cool.
Oh, one in the back of the
We can
room.
leave one in the back, one in the front, so when the person's speaking, to hype everything up, they toss it to somebody. Do we have the cameras?
Yeah, they put them in here.
Okay, cool. So I put one at the table up front, so when the person's speaking, they can toss it to somebody.
This shouldn't be that hot because I'm just touching the bottom here and it's like flashing on the board. But on the other one, you touch it and it doesn't do anything. Check. Well, yeah, I mean, it's, yeah, they sound low, but I just turned this up and not the gain. Check. 1, 2. Oh, he's already got the
I
plus
mean,
10.
that's no problem with us being in the room, but most of the time we'll be doing the changes and definitely don't like the question and answer too. We probably physically sit and burn 100% of the time. But we don't know when question and answer is going to happen.
Yeah.
So
There's no point. Like, I might as well just sit here. And what else am I gonna do? All of my sessions are in half-hour increments.
just make sure you watch who's doing it too. This the same person as here, so if we making them that's pretty good if they get
Right now, I just have the handheld up there.
Right now, that's all everybody using inside of B, inside of A, not sure yet, but inside of Salon, that's what they're using too. You getting good feed through the mics? Going to you? Check 1, 2, 2, 2, and I'm far. You are.
Say
You
again.
getting good feed? Like audio coming in? Yeah. I just heard a little feedback
I
too.
can see it on here. I mean, yeah, it looks,
Check 1 2 2 2, and I'm far away.
yeah.
We're getting feedback from this. Check 1
I'm
2.
getting an echo, but I don't know if it's just.
I'm running off of both
Oh,
of
it's
these.
probably, yeah.
Both of these are bouncing off each other.
Yeah.
All right. The wipes. We good to go. Let me check D. Angels down in bag. E. I mean G is about to start. Like I said, A started. I'm just waiting for B, but I have both of them inside of those rooms. So,
Might as well just hang out here. It's either that or hang out outside the door. Like,
yeah, it's true. Because it's going to be more boring out there than it is in here.
oh, there's nothing to do anyway. Yeah, it's not coming through.
It's
not loud enough. At least I think.
Let me check on Baldwin D, and the guys are floating around.
I have C and Mag here, so
I'll take Mag downstairs.
there's
I
one
gave
for
you
Mag downstairs. No, you gave it to Al, but Al, a lot of these like overlapped with Al's, and a lot of them don't overlap with mine. So I was like, oh, I could do that, but if I'm also just gonna sit
Yeah,
it
Al down there. Like I said, that's what I said. We can float the switch.
yeah.
The reason they said they didn't because they only paid for 6 people to be in 6 rooms. So that's why I
Charge them for it.
only charge for it. They only expected you to have 4 people. They said they would have their own. They just wanted us to be able to float. I'll just make sure these other rooms are together, Magnolia and G. G was the first one done.
I mean, I'll take the liberty to like walk out if I want to, I guess.
Yeah.
But
It's a deal. Once again, just make sure you look at who's presenting because we have people here multiple times. I noticed in G, the first person presenting, they're together, so they covered all of this time. How's everything?
Good, good. Everything's perfect. Microphone is on, yeah?
Yes.
right now it's off, but
Okay.
there's just a switch on.
Would you
the
like to
body.
use the handheld?
Either that or we have a lavalier if you'd like
It's
to.
fine. You should be okay.
All right, we're gonna send a catch box over to you.
Perfect, yeah,
So
I
you
will.
want to do question and answer?
Yeah.
Actually, let's see if
And-
we get
I don't
feed.
know which one's which. There should be two.
Yeah, perfect. We do have 2, right? Like those 2 are.
Yeah.
Yeah. And in terms of the slides, will you make them full screen once we start? Or?
That's
Yeah,
that's
it's recording
them.
on
Yeah,
here.
yeah, okay.
And I already recorded what's recording on the camera, so I'm just there. Check
Yeah.
it, but.
Yeah,
Still being recorded.
perfect. Okay. All right. Hello and welcome, everyone. Welcome to Linux Plumbers Conference 2023 and to the Networking and BPF Summit track. This is just a real quick intro around logistics and so on so that you're aware. This time we're spending 3 full days for our networking and BPF track. Really happy about that. It's keeping growing. We had it over the last years, and yeah, it keeps getting bigger. We're actually thinking potentially next year to even have like a dedicated BPF and dedicated networking because we have many submissions. This year we had 40 talks in total. So it is really awesome to see so many participating in the community. I'd like to thank the technical committee of the networking and BPF track, which are all the networking and BPF maintainers, David, Jacob, Paolo, Eric, Alexei, Andre, Martin, and myself. And in terms of the sessions that we have, each session is 30 minutes. That should also include discussions. We will have warnings if you're going closer to the end. And please make sure that you're staying within your time slot in order to be respectful also to the others. Hopefully we will have active, productive discussion. That's one of the goals of Linux Plumbers, to drive the ecosystems, the subsystems in the kernel forward. So yeah, questions can be made live in person here. We have throw boxes. We have 2 throw boxes for the room. They can also be made if you're participating virtually or in the chat. In terms of schedule, I put the link in the slides here, but I think you all are aware where to find it. We have a couple of breaks that are aligned with the rest of LPC as well. And yeah, so there's a 30-minute break in the morning and in the afternoon, and then there's a 90-minute bigger lunch break where you can also participate in the hallway. In terms of schedule, we have it roughly divided into, very high level topic-wise. So Monday, the first half of the day will be around core BPF. The second around BPF and security use cases. On Tuesday, we'll kick it off with BPF and tracing. Then the afternoon, slightly more around BPF and networking, and then there are also some miscellaneous topics that we have. And Wednesday is like whole day around networking. So the morning, networking and transports, and in the afternoon, more around container and other miscellaneous bits and pieces. In terms of time, so today we're starting officially 9:30. All the days they are going until 6 p.m. The Tuesday will start a bit earlier. We're starting at 9 a.m. and Wednesday again 9:30. Everything is video streamed and recorded, and we will make the talks available on the website a few days after the conference as usual. And on Monday we also have a fun session that is optional to attend for you. It will be around 6 p.m. where Quentin will present something like a fun book that he has been working on. And yeah, that's it. Be kind with each other, have fun, connect with peers, and yeah, have a fun BPF summit. And also I'd like to thank the sponsors. Without them, it wouldn't be possible to have this kind of event. Cool. And with that, moving forward for the first session that we have. Let me see. I will give you the speaker, Ellen.
Thanks, Daniel. Can you hear me okay there?
Yeah, we can hear you well.
Excellent. Thank you.
Perfect. Yeah, please kick it off.
Great. Thanks, Daniel. So my name's Alan McGuire. I'm here to talk about evolving the BPF type format. So BPF type format, it's a compact description of types, functions, variables. It's embedded in the kernel and modules. It's in most distributions these days, which is great. And for modern BPF, it really is become central and vital for modern tracing, F entry, F exit, compile ones run everywhere, struct ops, k funcs. I probably don't need to describe what all those things are to this audience, but it's really become vital for most of the modern BPF functionality. But a pleasing development is we've also seen it being adopted by other subsystems as well. So ftrace, Masami has done some work there, which uses BTF to give argument types and return values to give more informative tracing output, which is a great development. There's a huge potential for debuggers too, because this information is always available. You don't have to go through that extra step of downloading a big dwarf package. The dwarf information is huge, whereas the BTF for the kernel is pretty small, around 8 megabytes. So, having it always available is a huge win. Actually, my colleague Stephen Brennan is talking about this in the debugging microconference. He's going to talk about the concept of dwarfless debugging, that having this information close to hand gives you almost everything you need in kernel debugging, and having it right there is great. If you look at the eBPF Summit, Brendan Gregg gave a great talk there called Fast by Friday, and one aspect of that is essentially the talk centered on the idea of being able to fix performance issues within the 5-day week, and one aspect of that was having debug information available. So having BTF there in the kernel already embedded is a huge win from that perspective. So once BTF is there, all sorts of solutions and things become possible. So really what we should really be doing is making sure that BTF is available, first of all. So if folks pipe up and find issues which hamper BTF availability, we should really try and make best effort to resolve them. And once BTF is there and folks have it, we should make sure that it's solving the problems they want to solve, that they care about. And then finally, and these are all in order of priority. So finally, we want to make it easy to evolve the BPF type format as we find new use cases for it. And undergirding all of these solutions, we really want to make sure we avoid breaking existing tools where possible. We don't want to cause pain for users. And we want to minimize things like need to coordinate between versions of tools and the kernel and so forth. So we really want to evolve things while keeping compatibility where possible. So the first issue we've come across, and it's come up a couple of times on the BPF discussion list, is that the VM Linux BTF is currently embedded in the VM Linux image, and it sometimes bloats that image such that it can't be used for embedded systems. So this blocks their use of BTF. So basically VM Linux with that BTF section of 8 megabytes or so forth becomes big enough that it becomes a problem for these type of systems. So the solution we've talked about here is to support moving that BTF out from that core VM Linux into a module. So the BTF section is delivered via a module. And the reason this helps for the embedded situation is that modules tend to be delivered on a separate partition. So the size constraints that apply to VM Linux itself don't apply to the module. So the idea would be to go from config debug info BTF equals Y to config debug info BTF equals M and deliver it via that module. Now, the key thing is, again, to not break things, we want to make sure everything works the same as before. So we have a sysfs representation of BTF. It appears in sys kernel BTF. So when a module is loaded, the BTF representation appears there. The VM Linux one should still continue to appear at VM Linux. And what will happen then is no tooling will break because it all accesses that VM Linux image from there, that VM Linux BTF from there. So the idea is move it to a module, but everything else stays the same. So that's the suggested solution for that. So I might just pause there quickly because I want to make sure, anyway, to allow the room in and to make sure people want to give comments or feedback they can. Okay. So Lorenz is asking how the module will get loaded via libBPF or some other magic. That's a good question. I haven't really thought that aspect of it through. I've roughly prototyped this, but yeah, I mean, ideally we'd do it on demand. So the first user of VM Linux would trigger the loading of the module. So essentially the experience would be the same for users. It just happens that BTF arrives via a module instead. So the next issue isn't an issue around overall BTF adoption. It's more around people who are building modules and want to include BTF with them. So if the module is built less frequently in the underlying kernel, what can often happen is we end up with invalidated BTF. So if I move to the next slide here, what we can see is we have this split BTF module representation. So the module BTF defines only the types that are unique to the module and not shared with the core VM Linux BTF image. So this is this model of split BTF, and this is a great saving in terms of space. But the problem is the VM Linux BTF can change for even due to minor things, and those IDs in that VM Linux will change as a consequence, and thus any references to those IDs from the module BTF can cause problems, that they become invalidated, and the BTF for the module then becomes useless. So this is a big problem, because if you're not building your module at the same time as you're building your kernel, then that module BTF becomes invalidated. So the suggestion here then is to just build standalone module BTF. So we kind of take the hit of taking more space for the BTF. But the nice thing is it's fully self-referential, so there's no invalidation from the underlying VM Linux. So this is not in every case. This is just in cases where the module would be built out of tree, for example. So by making the standalone, the BTF standalone, then it's just fully self-referential. So any changes in VM Linux won't invalidate it. Now, the only problem with this is that all the tooling and the kernel as well assume that all BTF for modules is split. So the VM Linux BTF will use IDs up to a certain number, and then the module BTF will start at the number subsequent to that, so that we can recognize a BTF ID is modular specifically by the ID being greater than whatever the VM Linux ID is. So obviously, when you have standalone BTF, the IDs are going to start at 0, 1, 2. So they're going to clash with VM Linux ones. And the tooling doesn't know about this concept of standalone BTF. So the solution is, when the module loads, we can remap those IDs for the module. So instead of going from 0, 1, 2 in the way the standalone ones do, we remap them to start beyond the VM Linux IDs in the same way as split BTF would. And the value of doing this is that the tooling can stay the same, the kernel can stay the same. That renumbering is pretty trivial as well. It's just basically adding whatever the last VM Linux BTF ID plus 1 is. So it looks exactly like split BTF to tools. It just happens that it's fully self-referential, so there's no references back to the VM Linux BTF. So it solves that issue of invalidating BTF IDs. So that renumbering will happen when the module is loaded, and that essentially solves the problem with that invalidation. And actually, there's a sort of connection between these two solutions. So one of the ideas in this solution is we define a BTF base variable in the K-build subsystem. So the BTF base in general for in-tree modules is going to be VM Linux. So when we're building module BTF, it's done relative to VM Linux. So that's the BTF base in those cases is VM Linux. If we're building a module specifically for VM Linux BTF, that BTF base can't be VM Linux anymore because it's not there. It's in that VM Linux BTF module. So the BTF base variable would be used for that case. And the BTF base variable can also be used to connote the fact we're not building our BTF relative to VM Linux. We want to build standalone BTF. So you can see there in the slide, I've kind of described how you'd build a standalone module. So you just make BTF base equals, and then it's just empty to specify the fact that we're not actually building it relative to VM Linux BTF. So with this sort of solution, then the tools all work the same for split BTF as they do for split BTF. So for a standalone module, you can dump the BTF, you can use it in the same way for tracing. It just happens to be fully self-referential. So I think this solves the problem. Now, the only kind of wrinkle with this is that we have, within modules, we also can have a BTF ID section, which is used for K-funcs, for example. So in that case, we have to update those IDs because they're generated at the same time as the standalone BTF is. So when that module loads, we have to remap those IDs as well, but that's reasonably straightforward to solve. So that sort of brings us to the end of the actually adoption issues with BTF, which are things that make it hard to actually use BTF in the first place. So the next step is to really talk about usability issues. So once you've got BTF, what are the problems we run into? So we can pause here for a minute just in case anyone wants to come in and provide some feedback. So moving on to usability issues. So one of the things that happens when you build, oh, sorry, got some.
In terms of, can you hear me?
I can hear you, yeah.
Okay. How do you plan to do, like, do you plan to do the same for modules itself, or would that be shipped with BTF, or like regular kernel modules?
Oh, no,
I mean,
no,
here you
this is
talk
just,
about,
yeah. So, I mean, this for in-tree modules that are built at the same time as the kernel, there's no issue. This would just be for cases like, let's say if someone's delivering a module out of tree with a package or something like that. In that case, the problem they run into is that if they build that module against VM Linux BTF, the next time that VM Linux changes, that BTF is invalid. So, you know, this is the real challenge. So this is a giving away for folks who aren't building their module at the exact same time as the VM Linux kernel is being built, giving them a way to actually provide BTF for things like tracing. So the idea is not to change anything for in-tree modules at all.
So one problem with having like completely self-contained BTF within the module is that it's basically like not integrated with fentry and all that stuff, and LSM and like all the stuff that relies on, you know, like lists of BTF IDs that are allowed to, you know, to be called SK funcs and all that stuff. So how do you go about that?
Well, if you think about the way the BTF is generated, even in the standalone case, so let's say your BTF refers to an SK buff or something like that, it refers to the SK buff that was in the dwarf information initially in that module. So it's referring to its representation of things at that time. So the kfuncs will still work. They just are defined via the SK buff definition that's associated with the module itself.
I think it's a little bit more complicated because we have like lists of special types that you can ref count and all that stuff. And like if you have your own copy of SK buff in your kernel module BTF, that will be completely different BTF type for the kernel. So you will not be allowed to work with SK buff the same way, I think.
So would we need some kind of compatibility check between the two and then maybe use the same ID based on that compatibility passing or something like that?
Well, one way is to do BTF deduplication so that SK buff is detected as the SK buff coming from the VM Linux BTF, right? But the alternative that I wanted to kind of propose / ask if you suggested, what if like for those modules that need to be sort of BTF relocatable, right? Instead of just having complete copy of BTF, maybe we can have like a separate section where we list like the kind of assumptions that we make about base BTF, right? So like if I'm using SK buff, I'll just record that I expect SK buff to be in VM Linux BTF, and it was BTF ID 10, for example, right? And then during the kernel module load, we can, well, kernel will have to kind of find the actual BTF ID and rewrite them. So basically, it's still BTF, like split BTF, but just sort of relocatable split BTF. And we can discuss how to make sure that, you know, like the types when they change the size, what do we do about that and how do we detect that and all stuff. But, you know, that's details.
Yeah. Yeah, I mean, we sort of have a similar problem with the KABI today. You know, when you're trying to support a kernel version for a couple of years, often you have to pull changes in from upstream to fix things, and sometimes things can change. But we generally, the way most distros kind of deal with that is that they say these are the things that shouldn't change. So we kind of have some of these problems today in that context. So that might be something that might inform the discussion. But it's a great idea. We should definitely think about that. Sorry, go on.
So I think that the duplication is the best way. You have to have the complete definition for the type as used in the module, and then you will look for this type in the kernel, one that completely matches, or do core if something changes. But you have to have the complete definition, not just the size, not just the number of members. It has to be the same type, or for you to do just replace the number that is in the module with the number that's in the kernel, and then you don't need anymore the one that is in the module. But I think that's the duplication at kernel module load time done by eBPF.
Problem is that BTF dedupe algorithm is currently in eBPF. It's user space, it's recursive and all that stuff, including it in the kernel. is kind of a stretch.
Yeah.
That's like one reasons why we don't consider that as like the very first idea, I think. It's
Yeah,
kind of
exactly.
complicated. Kind of no one
Yeah.
understands it and stuff like that.
Yeah, I mean, in a way, that's what motivated going this route. That trying to put that into the kernel seemed to be a big challenge to me. But yeah,
So I
it's
think like
something
some sort, like we can add like a section to BTF-X or just have like a separate ELF section just for modules, right? Which will be sort of BTF relocations, right? Like it's not core relocations, it's just like pure BTF relocation where you can say, okay, type 10 is named skbuff, and maybe we include, I don't know, size or some hash that will be like type ID agnostic, right? But something to validate that like the at least memory layout is more or less compatible, right? And then like renumbering all the type IDs is trivial. That's not dedupe, that's like one pass and that's it. So much simpler, it seems.
And I guess the good news to say is when I've experimented with this, the modular BTF ID tends not to be massive, which would, when it's standalone, so that would suggest the amount of extra information we need to retain to sort of maintain that relocation shouldn't be massive. So I think that sort of approach should be kind of doable, I think. So yeah, I think we'll definitely explore some of those approaches. So to move on to usability issues, we've had a couple of issues around optimization. So when you build your kernel, you often end up with all of these strange suffixes on the ends of functions, like this isra.0, construct.0, all these type of things. And the problem is these things weren't represented in BTF, and a lot of the time this cuts you out of being able to do tracing on a lot of the static functions, which is obviously a bit of a pain. Now this is sort of solved in a way. So BTF now encodes these a representation of these optimized functions if you use that BTF gen optimized option, which is default now. But one of the problems is that we need to also unambiguously link those representations to the functions that they represent, because in BTF we don't use the suffixes because Dwarf doesn't either, so we want to be consistent with that. So we need to know which function in KOSIMS which has that suffix this BTF representation refers to. And this kind of feeds into the next issue around BTF usability, which is something that we've run into. And this is very important in the fentry context. So multiple static functions can have the same name, but can have different function signatures. This is a pain. Currently, we just leave out these functions. So a function foo can like have an integer parameter in one compilation unit, and it could have a pointer one in another. And obviously, if you're doing fentry and you're attaching to these and making assumptions about the types of what you're attaching to, this is a real problem. So I think we generally agreed that BTF needs to find some sort of way to encode addresses for functions. We haven't really talked about the mechanisms in a huge depth, so I just wanted to explore that a little bit here. I'm going to suggest a sort of tried and tested approach, which is to just have a simple symbol table in BTF. So in the BTF header, we have a new section dedicated to recording the symbol table for BTF IDs and have an address associated with them. So the table would have a very simple format. It doesn't need all the things a normal symbol table does. It doesn't have to have names or scope or anything like that. It would just need to have BTF ID address pairs. So a particular BTF ID could also have multiple pairs if that same function signature was associated with multiple sites, which it can be. So that just at the bottom of the page here, we can kind of see what it looks like. So multiple BTF IDs, multiple instances of the same BTF ID can have different function addresses associated with them. And so the reason I propose this is it's sort of a simple tried and tested solution. It's backwards compatible. We can continue to use BTF kind func to represent kinds, variables to the kind var to represent variables. We just have this extra information in the symbol table. My instinct, I have to test this a bit more. I would suspect it will simplify deduplication. If we add new kinds incorporating symbol addresses, the big problem is that if the address becomes part of the information describing that type, then you can't dedupe them. So the same function signature could be shared by multiple functions, but if they have different addresses, those functions won't be deduplicated. And that can have a cascading effect on BTF size. So having that kind of split between the function description and then the function address, I think might be valuable. And when the BTF is loaded, we can just have a simple representation of this and just have a simple index into that symbol table to get addresses. Another thing we probably need to think about here as well is that in Linux, we've been trying to make it harder for people to get access to the addresses of functions. So if you look at proc KO sims without privileges, you just see zeros for addresses. So I think separating out the address information in the BTF representation and then being careful about who can get access to it when it's loaded into the kernel is probably something we're going to have to think about as well. But this is just a suggested approach to this. I think the main thing we need to do is find a way to have addresses in BTF. The mechanism, I think, is something we need to probably figure out. But this is one suggested approach. So Nick is saying 1 address per entry. Addresses are big, make them optionally much shorter, base relative. Yep, that's a great idea, actually. That's something we could do. And actually, one of the things you have to worry about as well is that one of the there's a config option which basically means that all the addresses get obfuscated, they get all moved by a certain amount when the kernel is loaded. So we'd need to do that base relative computation anyway, probably to deal with that configuration option. So that's a great idea. So anyway, that's just one way we could deal with the address issue. I think we're going to need to grasp the nettle on this in some way, though, because we really want to disambiguate functions to make them all accessible. And there's another issue as well, which the addresses come in handy for, which is variables. At the moment, we only have per CPU global variables. We really want to have all global variables, and actually potentially static kernel variables would help as well. Particularly, this would help the debugger use case. If we have variables, sometimes a global variable is a jumping off point for a list or something like that. So not having that information limits your ability to do things in a debugging context. So my colleague Stephen had an RFC proposing to add variables. But one of the things we ran into with them is the same thing we've run into for functions, where we can have ambiguous names again. So the same name variable can have different types. It's kind of worse for variables. Sometimes the same name can be refer to a struct or to a pointer to the same struct in different compilation units. So we need to get that ambiguity resolved here too. So this is another case where the symbol table approach might make sense. So again, this is sort of why I suggest a symbol table, because it cuts across functions and variables as well, and we don't need to perturb any of the existing function or variable representations. So Chris is saying that's an important topic for tracers. Being able to have type info for variables is a major benefit. So another issue we've run into, and this is actually a sort of evolving BTF issue as well, is that BTF at the moment, parsing BTF requires you to know about the various kinds within the BTF. So one of the things that can often happen is you can build BTF with one version of a tool and then try and read it with another version. And if the version you're reading it with is older, it might not know about particular kinds that have been added. So for example, if you add like the enumerated 64 kind, the older tools don't know about that kind, so they can't parse it. So they fall over trying to read that BTF. So the suggested solution here is, if at encoding time, we can also encode information about the BTF types that BTF knows about at encoding time. If we can give enough information for parsers to be able to read BTF, then we can sort of solve this problem. So the suggestion is to have a section within BTF with the layout of the kinds. And there's only a couple of things you need to specify for each one. You need to specify, after the sort of common BTF type structure, is there an additional structure, and what size is that structure? And then you also you can have optionally multiple structures. So for example, for a structure, you have multiple structures for each of the elements within that structure. So in that case, you need to know what size each of those elements are. And if you have those two pieces of information, you can then parse. So if we have that kind layout section, even if the tools are older, they can use the kind layout to parse BTF, even if they don't know about some of the kinds that have been added. So basically what you're doing is, at encoding time, you're saying, these are the BTF kinds I know about, and then BTF tools can use that to parse the BTF that you have, and then they can kind of walk past any kinds they don't know about, and we can make progress. So here's an example of BPF tool being run. So this is a separate format argument I've added to BPF tool in the patch series. So the idea is we provide a way to dump metadata about BTF. So we can dump information about the BTF header, and then information about the kind layout. So we can see here the info size is the size of that singular element following the BTF type. Some elements have it, some don't. And then the LM size is the size of the kind of variable number of elements argument that follows as well. So if you have that information, you can then parse the BTF, even if you don't know about the kinds that are specified. So 5 minutes remaining. So yeah, so let's keep moving. So one of the problems you have as well is when you're loading module BTF, when you hit that mismatch problem, we don't have a way to explicitly detect that. So what essentially happens is with your module BTF, if one of the references to the underlying VM Linux BTF is wrong, then the parsing fails and then the module BTF can't be used. But we don't have a way to explicitly check the mismatch between module and kernel BTF. So one suggestion was to add CRCs for VM Linux and module BTF. So the idea is when you load a module, the module has its own CRC and also the CRC of the object that it was built relative to. So in this case, the module BTF would have a CRC for the VM Linux BTF. And when the module is loaded, it checks that CRC against the one it expects for the kernel. So if basically at loading time the kernel sees that the module expected a different VM Linux BTF, we can fail up front and not have to deal with the issues of just sort of going along with parsing until we hit a wall. So this provides a way to explicitly deal with that problem. So I think that would be a potentially useful approach. Then, sorry, sir. Okay. So then we move on to issues involving BTF. So one of the challenges with that, sorry, I'm hearing noises from the room. Is that someone asking a question?
There was no question or comment.
Oh, okay. So just very quickly then, evolving BTF, this is a less of a priority, obviously, but we really want to make sure it's possible to add new kinds and so forth without breaking too many things. So BTF generation consists of running PA hole with a bunch of options, some of which were opt-in, some of which were opt-out. We wanted to simplify that and also not have to do this thing where we have to check the version of PA hole to see if it's got the options that we want to use at encoding time. So we recently added the BTF features option, which is essentially a simple list of options, opt-in options, which you can specify for BTF encoding. If the features don't exist, PA hole will ignore the encoding request. And the idea of that is we don't need to check the version of PA hole for particular features. It just makes kind of coordinating between the PA hole tool and the core kernel a little bit easier. And it also makes it a little bit semantically easier because we're just dealing with a set of opt-in options. And then I've kind of talked about this before. So this is the issue with new BTF kinds being added and older tool chains breaking. So in terms of changes, then we end up with some small changes to the BTF header, adding the kind layout information, potentially a symbol table, and CRCs. So I think that adds up to about 24 bytes. For the kind layout section, we're talking about 80 bytes for the current number of kinds. So 4 bytes for each one. So that gives us that information that allows us to parse. Function addresses, probably about half a megabyte for the number of addresses. But, as Nick suggested, we could maybe look at finding an offset relative encoding for addresses to save a bit of space there. Variables add about 2 megabytes to VM Linux BTF. So there's a little bit of overhead there. And pretty small overhead to modules. And then CRC verification has a computational overhead, but that's only at module load time. So what's done so far is we've done the BTF features. We've done the encoding optimized functions. Work in progress. I've sent a patch series out, which has the kind layout, CRC verification, and standalone BTF and renumbering. Obviously, we'll need to take a look at that and see if that's still valid. So to be done is having BTF delivered via module and BTF symbol table and BTF variable support. So the variable support, I think, should probably come after we figure out what we want to do about encoding of addresses, because we have that disambiguation problem that I referred to earlier. So hopefully we can make life a little bit easier for people who want to adopt BTF that are currently blocked, people who want to use BTF for specific use cases, either in the BPF context or elsewhere like ftrace and debuggers. And hopefully we can make it easier to evolve BTF for new features. But because these things involve UAPI changes, we really want to do them in a coordinated manner. So trying to find synergies between these solutions, I think, is a useful exercise. So this is why I wanted to kind of lay out some of these ideas and see if there's connections between them all. So thanks for your time. That's me done. So questions, comments, we greatly appreciate it. Thank you.
So one question, like you didn't mention, I don't know if you consider that, like we should probably specify the sorting as well, order. So like for symbol table, we should decide whether it's sorted by name or sorted by address, but it has to be sorted like just to make the tooling faster by default, right? Like without having to resort and all that stuff. That's one of the problems with like ELF symbol tables, like random order. Maybe we can even do like a both orders basically. Like in one order, it will be like have the ELF have the symbols listed, and in other order it will be just like the index of the entry that would be at this, like ordered, like alternative ordering. Like we can discuss it on the mailing list, but basically what I was just going to say is that like probably sorting should be part of kind of the standard.
Yeah, exactly. Actually, I think in this particular case, I think sorting by BTF IDs might make sense, because then you'd have very close together all of the addresses of that match a particular function signature. So in that case, that's probably a useful order to have. So I guess, but I think ultimately what should dictate it is the use cases. So, we want to sort things to be most effective for whatever ways they're being used. So if you're doing things by function signature, that would make sense, but you may be doing things in different ways too. So I guess we just need to think that stuff through. Absolutely.
Alan, thank you very much for your presentation, and thank you for working on these challenging problems. You are, pretty much single-handedly working and trying to address all of these BTF issues. They're definitely tough, as your presentation demonstrated. So we should, this is not the end of the discussion, it's the beginning. We will continue discussing all of these ideas. And even so, one quick comment here regarding the CRCs. So Andrei's idea about adding the hash potentially to types. So the reason we are thinking to add this base CRC and BTF CRC is to avoid this validation issues that are hard to debug when the BTF mismatch, when the kernel module BTF is built later. So maybe actually instead of doing the CRCs for this extra validation step, we will just go and add CRC to all the types that were deduplicated. And then instead of running the whole dedupe in the kernel, we'll just match the CRC, and that will be the last this relocation / adjustment based on the CRC. So instead of instead of using the CRC to prevent mismatches, let's actually try to solve it completely. And maybe CRC will be the answer, some sort of a hash per type. Not necessarily for all the types, but for types that were deduplicated. Because deduplication, the standalone stuff makes sense, but we cannot just load it, because, for example, the module would be built with escape buff that built with debug mode. It will have a completely different layout, and the module might assuming different everything, and the last step of core relocation will just not be correct. So we cannot just split it and assume it's there. The tooling will work, but it not necessarily will be safe. So this dedupe, the combination of combining the BTF, even though it was standalone, I think it's necessary.
Yeah.
So this is just something for us to address on the mailing list.
Yep, absolutely. Thanks.
Yeah, just the arrows.
The arrows
Yeah.
but this one goes to.
Yeah, you're the presenter.
Okay. So how do I go to the next one? This?
Yeah, sorry, just use this.
But this one.
Then just use this.
Okay. Oops. Hi everyone. I am Kumar Karthikeya Dwivedi. I'm a first year PhD student at EPFL, and also I've been contributing to BPF for a couple of years now. So today I'm going to talk about exceptions in BPF. Some of this is already upstream, and some of this is something that I'll send out soon. So let's dive right in. So this is the agenda. First, we begin with a very high-level introduction, and then an example, some use cases that exceptions are meant to serve for now,
And then we talk about the high-level design and some of the future directions this work could take. So what are exceptions? So they allow you to abort the execution of a program and return control back to the kernel. So if you know Rust or C++, they are very similar to the panic or std terminate APIs that allow you to immediately abort a program. You have a kfunc called BPF throw, which allows you to generate an exception, throw it from a program, and it takes a cookie parameter, which by default becomes the return value. But there's also a way for you to override the return value in case an exception is thrown. So this cookie is then passed to this special exception callback. So once the program has completely aborted, there's an exception callback that will be invoked, and then you can decide what to return at that point. But more importantly, the verifier does not really follow a program path during verification once it encounters a BPF throw call. So we'll see how we can use this to do really interesting things. So this is an example. We first, like on the top in bold, you see __ exception CB. So this is a way to define an exception callback for the program. So we have a global function exception callback, which we specify here. And inside the program, there is a condition where if it's not satisfied, we just call BPF throw. So in this case, we pass PC act short, which is like a way to drop the packet. And then our exception callback will receive this cookie and it can decide what to actually return. So this is a way to basically tie the call side of the exception back to the exception callback. And like once this condition is not specified, the program aborts, it returns control back to the kernel. So one of the first motivating use cases of this thing was assertions. So right now we have these macros, BPF assert equal, less than, greater than, less than equal, greater than equal, or range. So basically they allow you to update the verifier's knowledge about a scalar value. So this support is already inside the verifier. Whenever you take a branch inside the verifier knows when it follows an execution path that this is the current value in this program path of this scalar variable. So what this stuff does is for the other branch where the condition is not met, it basically calls BPF throw. So in some sense, you're asserting that a specific value is true or a specific value is in a certain range at runtime. And if it is not satisfied, you just end the program immediately. So and one of the other advantages of relying on the verifier for this is that whatever improvements that come to the verifier's range analysis basically apply back to the way we expose assertions to the program. So once, if we can like compare ranges to ranges, like there was a recent patch from Andre, so we can also assert that variable lies within a range or something like that. So 1,000 feet view. At every program point where we can possibly throw, that is, if we see a BPF throw kfunc call, for all frames in the call chain, like if you have multiple function calls happening at that point, we basically have to generate frame descriptors, which basically describes the state of the program for each frame at that point. So suppose if you have some resources allocated in the first main subprog, and then you call a static subprog. So whatever you have on the main subprog, this will be part of the frame descriptor information, and we'll see how it looks. And whenever we unwind all of these resources that we want to release, when we abruptly end the execution of a program, we want to know this information so that we can release them at runtime. So if you have a socket that you have looked up and spilled the pointer on the stack, when we are basically unwinding your program stack, we want to release the reference to the socket before we return control back to the kernel. And in the end, the program is aborted, and frame by frame, we keep on unwinding and releasing the resources. So in this case, like say this is the main function of a program where it calls BPF object new, which allocates memory, and then you spill this pointer to the stack. So on the top right, you see the frame descriptor where the first part we don't really care about, the R10-8, but R10-16 we know that it's a program allocated object. Now suppose this calls a BPF function, and this one ends up doing a BPF SK lookup. Which again spills the pointer to the stack. Suppose you do that. So in the frame descriptor for the frame 1, you can see that you now have SK at FP-8. And then if you call something else, again, you spill something to the stack. Again, that information is made part of the frame descriptor. Now, what happens if you call BPF throw? So at runtime, since we'll have all of these frame descriptors available to us, we can start unwinding the stack by first, like for each frame, we figure out where the resources are located. And then for every frame, we start releasing them. So in this case, we'll do BPF ref count release. In this case, we do BPF SK release. And in this case, we'll do BPF object drop. So just what the program would have done itself, we do it for you through the BPF throw call. So in case of resource cleanup for unwinding, we basically now have a frame descriptor for every call instruction. And then before verification, we have to do a pass to figure out all possible call chains that can throw. Why do we do this? We'll get into in a minute. And this frame descriptor information comes directly from whatever state the verifier keeps track of. So whenever it is analyzing a program, it knows at what point, at what place in the stack there is a resource. So we can just directly lift that information from the verifier itself, and then look this up using the program counter at runtime. So why do we need a pre-verification pass? So if you don't know, there are two kinds of subprogs in BPF. So you have a global subprog, then you have a static subprog. So in case of global subprog/functions, the verifier basically does their verification beforehand, before starting the verification of the main program. This is basically used to reduce the verification burden, and also global subprogs can be replaced at runtime. So basically, like whenever we have a call chain like the one on the screen, so suppose your main proc calls a static function, which calls a global function, which calls a static function, which calls BPF throw. Then during verification, like when doing the SIMBEX, the verifier sees global subprog, static subprog, and BPF throw, and then main static subprog 1 and global subprog 1. So basically, it never, like if we don't know that global subprog eventually leads to a BPF throw call, we cannot really know whether we have to generate frame descriptors from main and static subprog 1. So basically, like a pre-pass is needed to analyze all the call chains and basically mark whichever subprog can possibly be reachable from a BPF throw call. This is similar to the BPF tail call reachable stuff we already do. So but we do need this to be able to actually generate the frame descriptors for main and static subprog 1 in case they call global subprog 1. So this is something that also came up like for the first part that was merged. We were discussing whether we can allow people to basically catch exceptions within a frame. So right now we have this catch-all callback. When the complete unwinding of the program is done, we have this callback that you can execute to basically do something, change the return value or do some action. But sometimes you really want to catch an exception being propagated in the middle of your program, right? So how can we support this? So right now, like there's not a lot of users of this stuff. I've just been trying to integrate into ScareDXT, but once we have more and more people, how can we go about doing something using this? How can we go about doing something like this? So one of the options is that we lift compiler support and basically have some way of describing that whenever you throw an exception, this is the landing pad that you want to execute, and the compiler basically puts some metadata alongside the program, and this can be passed to the verifier when loading. And when it when it calls BPF throw, it starts basically simulating, like unwinding the program, jumping to the landing pad and seeing whether we have to continue or stop. So this would be one option, like lifting the compiler support. Or the other option is like we imbue the verifier with constructor and destructor semantics, where we tell that for a specific object on the stack, this is the cleanup action that you have to do. It knows it beforehand. But there are different trade-offs with both, because like if you have a catch block, you also have access to all the objects in the local scope of the frame. So sometimes that is much more like useful than like having a function that does the cleanup, because it lacks context. So what next? Are assertions the only thing that this primitive is good for? I would argue no, because uh, I've recently understood that this is like a much more fundamental primitive that can allow you to rethink how we do safety property enforcement right now in the verifier. We have a lot of complexity for a lot of things that we implemented recently, and something like BPF exceptions would allow us to get rid of a lot of that complexity, as we'll see. Uh, this can be both fast and correct in terms of having no overhead at runtime and still ensuring the basic safety properties that the verifier guarantees to the user. That is, the kernel will not crash, the kernel will not stall. Uh, So what if we could cancel a program? So right now we talked about whenever you have a BPF throw call, you generate these frame descriptors, right? But what if you could generate frame descriptors regardless of whether a BPF throw call is made or not? Basically, like if a program is marked cancelable, if you could generate these frame descriptors, we pay some memory overhead, but the ability that we get in return is uh, if you interrupt a program at some point, you could figure out how to basically abort it at this point if a BPF throw call was made. That's the whole point of the frame descriptor stuff. Basically, at any program counter, if we see a program, if there's an interrupt and we see the program stuck at this point, we could know the state of the stack of each frame, and we could steer the execution of the program to basically say a trampoline which ends up calling BPF throw eventually by fixing the program counter. So why should we have something like this? Like, why is it useful? So once we have programs that can be canceled, we can actually do interesting things. So I'm going to cover a case which the verifier vehemently rejects right now. So for example, loops. So right now we have this case where we have BPF iter, which basically guarantees that eventually the next iter call will return null, right? So basically the verifier relies on this contract that eventually the loop is going to terminate. But what about loops that cannot be proven to be terminatable at like during static analysis? What if you have like a linked list where you cannot prove acyclicity? So in this case, uh, if we have the support to cancel a program, we can actually have loops which seemingly for the verifier run for an infinite, it's basically an infinite loop, but you could cancel the program after a certain time limit or a certain like bound on the program's execution. And the runtime cleanup would ensure that you leave the kernel in a consistent state and you return control back to the kernel. So if the verifier cannot like statically reason about a loop's termination, then the ones that it considers infinite, it will reject the program and basically say that the program will never terminate. In such a case, if we have cancellation semantics, it would allow us to express a lot of things that we cannot do right now, like iteration logic for data structures which the BPF runtime does not manage, like not BPF managed linked lists, but linked lists managed by the program itself. And possibly even have spin loops inside the program so that you can implement your own spin locks inside BPF itself. So like just as an example here, so suppose that this linked list is built out of array map nodes. Now I think like this, for a lot of people working with BPF, this is a well-known trick where you basically use the array map as a heap and build data structures out of it. So in this case, we have a linked list. So let's ignore all the like bounds check on the element access, but for simplicity. And in this case, we don't really have any guarantee of acyclicity, right? So let's ignore what the IE0 to BPF max loops is doing. Let's just assume it's an infinite loop. And then inside this loop, you have this part where there are some kernel resources on the stack inside the loop iteration, right? So this area marked red would be the thing that we would want to clean up if we find the program counter in this range. So BPF max loops is quite a big limit. Like it's 8 million iterations, if I'm not wrong. And depending on what you do inside the loop, it can run for like 20 milliseconds or more, even more than that. Like depends on what you do inside the loop. So it's already in some sense allowing you to run the loop for a long time. So instead of that, like we would rather cancel this loop if we figure out that it's stuck, And based on our latency requirements of the program's execution bound, we don't really want to run the program anymore. So recently we have added these three primitives, right? BPF object new, which basically hands over kernel memory to the program, and BPF linked lists, which basically allow you to allocate nodes, add them to a linked list, which is managed through kernel helpers, similar for arbitraries. The reason that the verifier gets entangled with the implementation of linked lists and arbitraries, we had to teach the verifier about ownership, about synchronization and everything, is because this memory is managed by the kernel. It's memory coming from kmalloc. And this in turn forces the verifier to reason about how this memory will be released. In turn, it forces the verifier to reason about how this memory is being used. If it's stored in a linked list or an arbitrary, we need to enforce that the invariants of the linked list and arbitrary are maintained, and eventually we are able to recover the memory stored in these linked lists and arbitraries and hand them back to the kernel. Then we need to teach the verifier about shared ownership and unique ownership if a node is accessible from multiple CPUs. And this also is a bit restrictive, and reasoning about the semantics is not really easy. Instead, we could remove all of these all of these complex semantics from the verifier by basically building on much lower level primitives. If you had a way to write express loops that the verifier cannot reason about, and it can still terminate them, you could build synchronization primitives. You don't really need BPF spin lock. You could probably build a spin lock that probably has NUMA awareness right into your BPF program. You could build your own data structures and iteration logic, because once you have a loop that you can use to iterate over a data structure, you can basically implement find operations, search operations for a data structure. And all of the memory that we manage in this way should ideally not come from the kernel allocator, but some program specific heap. So some kind of an array map, but the problem is that the array map locks up memory. So we would want something more dynamic that allows you to request memory and release memory on demand. So based on this stuff, what have I tried so far? So I have tried spin locks with multiple levels. So right now in the verifier, we have this spin locks where you can only take one at a time. So in this case, we can have something like lock spin lock A, lock spin lock B. And the way it prevents a deadlock is once you have a deadlock, you have a bound on the loop that you are using to spin for the spin lock, right? So once there is a deadlock, all of the waiters are waiting for the lock to be released, but nobody is making progress. So eventually, the owner or whoever is not making progress will be aborted, will be cancelled, and that in turn ends up cancelling all of the other waiters that are waiting for the lock. So you have this built-in deadlock avoidance in some fashion. And then data structures, basically using this stuff and using a shared heap of the program, like an array map or something like that, you can build out all kinds of data structures using these primitives. So you can have hash maps where you iterate over them, do locking, linked lists, arbitrary skip lists, and even the QP try that was sent to the list some time ago. And exceptions through the cancellation semantics would underpin the safety argument for all of these. They would allow enforcing the termination property without really compromising the safety of the kernel and the program. And you would use maps as your memory allocator, and basically unburden the verifier from reasoning about all of the concurrencies, synchronization, lifetimes, and memory management semantics that we currently do. And basically only enforce memory safety, kernel termination guarantees, and just get rid of everything else in that sense. And this would also allow you to compose higher level verification frameworks with the current verifier. In some sense, you could write a program that's in the BPF front end of the Rust front end of BPF, and it could restrict you in doing things in a certain fashion, but the underlying verifier doesn't really care about all that. It just cares about that you eventually get rid of hogging on the CPU and not violate the memory safety constraints. So with that, I'll take questions.
You mentioned adding kind of bounds at runtime. Would there be some way of observing them so that you don't run into issues where everything's working fine up until you reach that bound, all of a sudden everything breaks?
So right now this is like just the experiments that I've been doing personally. What I do is basically teach the verifier that this is a user space pointer that is a pointer coming from a map, right? And this is the type. So the verifier knows that whenever you access this, it emits a bounds check for you, right?
Sorry, I meant kind of the runtime
Mhm.
bounds when you're talking about, for example, like loop durations.
Okay.
Because so right now you have the nice property, at least, that when your program is loaded and you pass the verifier,
Mhm.
then at runtime it always kind of works. Whereas here you could get to this point where you're very close to the bound or the maximum, amount of time you're allowing,
Yes.
and then you suddenly
I
pass
see.
that
I see.
without
I see.
knowing.
I see. Yeah. So this is basically a trade-off that you have to make. So you need basically this is the worst case bound of your program. So this case should not be hit, right? But it's basically a way when there is a bug in your program, or suppose if you have a cyclic linked list, which shouldn't be possible at runtime, you basically are still able to recover, and basically the program should stop executing and let the kernel continue. So this is basically a worst case recovery mechanism. In the ideal case, your program would just continue executing normally like it should.
Yeah. My
Yeah.
point was it'd be nice to be able to monitor that, perhaps, so that if you're accidentally getting close to the limit in production,
Mhm.
then you'd know ahead of time before.
So like you could choose to do whatever you want. One of the policy decisions is that you cancel the program, but you could choose your own limit, or wherever this limit is enforced, like you could also make it configurable through a different BPF program, which basically decides what to do when it encounters this condition at runtime. Yeah.
Okay, thanks.
Can you talk more about this, how to protect for memory safety? Because I think what's your plan and what you have done? Because I think it's important for many tracing programs that so they can directly access the kernel memory, but there's no guarantee on the memory. It could be, you could follow a pointer, but the objects may already be freed. That's more dangerous. Yeah.
So do you mean like the pointers?
What's your plan and what you have done in that direction?
So with respect to the pointers that you manage using your own heap, you're talking about that, or you're talking about the point?
For example, you accessing some kernel memory, kernel variable. You follow the pointers. Let's say.
So that is already there, right? The pointer to BTF ID with the probe mem semantics. Basically, like it does exception handling for you at runtime. If you follow a bad pointer, and if there's a page fault, the kernel like already has this support where it basically marks the destination as 0. So if you have because it can allow you to read stuff, but it cannot allow you to write stuff from tracing programs. So you already have this support where you can follow pointer chains, and then basically you can even follow invalid pointers. All it does is it will have an exception at page fault at runtime, and it will fix up the access for you.
But what if the memory is already being, like, say, freed or just not out
Yeah,
of
so
synchronization?
basically it's in the page fault handler. Like once it hits the page fault handler, it just
so you say kernel already handles that natively, so you don't
yes,
have.
right. It happens right now, like for tracing programs. Yeah.
And then what do you say about this memory safety issue you using exception?
So if in the case if you have these program owned heaps, right, to like allocate stuff from and use exceptions to manage it. So in that case, you need stronger guarantees, because you will also be writing to it, right? You'll not just be reading from it. For reads, we can have this exception handling stuff. But for writes, we really need to ensure that you're in that memory bound, in that memory region. So we need runtime checks. But there are ways to basically optimize that out so that you pay very little cost to do that.
That memory is allocated from at runtime by the program.
No, so that's the whole point. Like you don't really want to use the BPF object new BPF the memory allocator. Okay. You want your own separate map, which basically allows you to chunk up objects from it instead of letting the kernel do it.
Okay.
Yeah.
Hi. So thanks for the talk. It's really interesting. So I see that now we have the ability to sort of do a stack unwind and resource cleanup, and upon an exception. So I wonder, is it hard to sort of extend this also to like normal execution paths? So basically, doing resource auto cleanup
inside the kernel.
Well, not really. Yeah, I guess inside the kernel. So that the programmer don't need to manually
In
unlock
that
or
case,
whatever.
we'll have to write the kernel in BPF, I guess. So, but yeah, but it's hard to do inside the kernel because in this case we like rely on the verifier static analysis to understand what resources to leave. Maybe the verifier could work for a certain portion of kernel code which does something similar, but yeah, like right now it's hard. It's very hard to do.
I see. Yeah, thanks.
Two quick questions. Like for the frame descriptors, don't you always need them when you also have tail calls because you don't know whether BPF throw is being called?
Yes, if you call BPF throw, then you need to have them ready at runtime. Basically, you need to pay some cost in terms of memory so that you can, whenever a throw does happen, in the worst case, you know how to unwind the program. So you need them available. But it's like they are only generated for the cases where you actually call throw. So for only those program counters. And a lot of the times, like the state of the program does not really change much. Like you can have the program executing, but the objects allocated on the stack remain the same. Or there's like duplicate spills of the same acquired object. So in some sense, there are ways to optimize that out and basically like reduce the memory overhead further.
Okay, and for the cancellation, I mean, one thing that was mentioned earlier regarding monitoring, right? I mean, like the one worry is that you might leave the program at like an undefined state, right?
Yes.
Like if you change something in the maps and suddenly you cancel everything, right? It's probably really hard to debug in production.
Yeah,
That's
so
something to
this
think
is
about.
this is where like being able to support like having callbacks per frame would be really useful, so that you can do some kind of recovery code before the program really ends up unwinding completely. And in that case, we wouldn't really allow these kinds of loops because you don't want recursion, right? You don't want that loop to end up throwing again and then you go to the landing pad, then you do a loop throw again, like it's an endless loop basically. So it's like a more restricted landing pad where you can do some recovery of the program and then you keep unwinding. Yeah, so you would need to combine it with something like that. Okay, that's it. Thanks.
So hello everyone, my name is Raj and today I'm going to talk about our work on BPF termination. So we all are here because we all love BPF for one or the other reasons. Why we love BPF is because of the safety and termination guarantee it provides. What it means is that an administrator who wants to install a piece of code on a runtime is ensured that this piece of code cannot stall or crash the kernel. So termination as a guarantee is ensured by the verifier by traversing the whole BPF program to ensure the whole program is a directed acyclic graph. On top of it, because of the instruction limits, stack, and nesting limits, we always know that a BPF program will always end in an insignificant time. Now, the word insignificant here is quite subjective, and this is because of several recently added helper functions. Now, these helper functions have something in common here. They all iterate on a list and then call on a user-provided callback function. Now, depending on how large the list is or how costly that callback function is, each of these helper functions can execute for a really long time. To take an example here is a simple BPF program having two nested loops with some iterations. And at the end, we are just printing hello world. Now, this innocent looking BPF program has a runtime of about 2 minutes, which is insane if you are completely stalling the CPU for about 2 minutes. And depending on how much nesting you add or how many zeros you add on the iterations, we can easily increase this 2 minutes to several hours. So even though termination was guaranteed, fast termination was not. And this calls for a runtime mechanism through which we can kill BPF programs whenever needed. Now, before we go on to the challenges, I want to talk about some use cases of dynamic termination. So far, we talked about the long runtime case, where a BPF program ends up running for an unexpectedly long time. It can further have two different use cases, not very different, actually slightly related. Abrupt termination is where an administrator or an observability tool, let's say, finds out that one of the CPU is getting stalled because of a BPF program. In that case, they would want to kill this BPF program. And another example is about BPF orchestrator. Let's say we want to replace an old version of a BPF program with a new version. Now, depending on the severity or the priority of this whole event of replacing one BPF with another BPF program, we might want to do this as fast as possible and not even wait for the prior execution to complete. So this calls for the orchestration use case. There is another sub-umbrella within the, so not sub-umbrella actually, it's a sub-use case in dynamic termination. That's the unexpected runtime state. So we just saw about the use case of BPF exceptions when if the programmer decides that because of several reasons of some helpers or some allocations failed or something else, if the programmer decided that it does not want to continue any further, they can call a BPF throw and call an exception. Now it's the exception runtime to responsibility to clean up all the resources and abort the BPF program. Similarly, talking about stack exhaustion, that is one of the talks my lab mates Siddharth and Roop are going to give in a bit. This is, to give a spoiler, they proved that using several nested BPF programs, we can exceed more than the 16 KB kernel stack, and which can lead to stack overflow. So what we would want here is that the moment we see that the stack is going to get overflowed now, we abort the previous bloating BPF program and save the day. So we just saw about some possible use cases about dynamic termination. Now let's talk about the challenges, like why cannot we just kill a BPF program? What's so difficult about it? So about a generic kernel thread, we have the obvious problems of memory leaks and deadlocks, because in a generic kernel code, we have no idea about how many resources are currently allocated. So if we just choose a random point and terminate it, we will have the heap memory, which is not freed. We have the locks, which is already there, and someone else might be deadlocked on it. So these problems are there. But because of BPF, we are getting an advantage here. Because of that static traverse, static analysis done by the verifier, we have a bookkeeping maintained internally by the verifier. So at any given point within the BPF, we know what are the objects which are live and what of them are not. However, there is one problem still remaining. Whenever BPF makes a helper call, these helper functions are nothing but kernel functions. And the verifier has no idea about what is going inside these helper functions. So we get the same problem that if a helper function is executing and we end up killing in between that, we will still have resources in the helpers which are not freed up. So memory leaks and deadlocks again. So two issues we have here. The first one is, how do we track these objects which needs to be freed up? We need to track these resources to clean them when termination was requested. And the second issue is, how do we know when should we terminate and when should we not? So in this case, we should never be terminating when a BPF is currently executing a helper call. So to deal with these two issues, we will be talking about two separate approaches. The explicit approach is the one which we tried and have, okay, we will go on with that further in a bit. And after discussing the explicit approach, we will go on with the implicit approach where we propose the fastbar termination. So let's move on to explicit approach. Now, since BPF bytecode does not originally have any sort of, I mean, let's say talk about a C++ program or a C program. A C program does not have any kind of garbage collection happening. So to provide that, we can have manually or explicitly manage the lifetimes. Now, for this case, what we can do is we can have some sort of allocation list or any other data structure, where for every allocation and deallocation, we log some information. Now, whenever we want to terminate, we can just iterate that list and find all the resources which are not deallocated yet. So this way, we can implement a manual garbage collection. There is an obvious problem to this, is that even though termination is not required, we will still be logging information to the data structure. So this is a runtime overhead for even no termination cases. There is a second not so obvious disadvantage of this approach, and that is that we saw previously that BPF has this information somewhere or the else, the verifier bookkeeping. But this explicit approach of garbage collection is not leveraging that fact. So this is a indirect disadvantage we are seeing here, and that why we are not leveraging an information. So that brings us to an optimized way that we can generate landing pads during the verification step itself. So that we can say as the C++ style unwinding, where we pre-generate landing pads, and whenever termination is called for, we jump to a relevant point in that landing pad. So this is the industry standard way, and most modern programming languages are using this technique right now. And the big advantage we get here is that until someone calls for termination, it has zero overhead. So we just saw how we can deal with the first issue about how to track lifetimes. Now talking about how to deal with when can we unwind. This is the place where we talk about safe termination points. What does this mean is that whenever we are not in the BPF text, let's say we are in a helper execution, that is an unsafe point, and we want to not terminate when we are at that unsafe point. Another way to say that is that whenever we are in the BPF text, that's a safe termination place, and we can trigger termination if we want to. Now, how do we know if we are in a safe zone or not? So there could be several approaches. I want to discuss two of them here. One of them is a basic flag check approach where we modify every helper call and we check for this flag. If the flag is true, instead of running our original helper logic, we will go and we will take the execution to our cleanup mechanism. And this flag check will be happening every time, so there is a runtime overhead associated. Another better way to remove the runtime overhead would be to install kprobes. The idea here is we install kprobes on each of the BPF instructions, and the moment a helper function returns back to the BPF text, one of these kprobes will get fired, and we will get the execution control again. And from there, we can start our cleanup procedure. So we just discussed the explicit termination approach. And there are some shortcomings for both the approaches we discussed. So for the GC approach, we had the obvious problem of runtime overheads. But regarding the unwind table, even though this is an industry-wide way, accepted way to deal with cleanups, the problem is that it brings a lot of complexity to the Linux kernel. If we are generating landing pads during the verification step, there are still a lot number of steps which is happening from the BPF bytecode to the x86 translation or any other machine code. So there can be function inlinings, that code eliminations, or several iterations of JIT optimizations. And for each of these steps, what it means is we have to synchronize that landing pad, the unwind table accordingly. And if we have any sort of bugs or incorrectness in that landing pad, we are inviting invalid memory access problems. So all in all, we are weakening the memory safety guarantees here. Now let's talk about the implicit approach. But before that, let's quickly summarize what has happened so far. So C originally had no lifetime managements. To deal with that, what we propose is we explicitly deal with all the resources and propose the garbage collection approach. But we realized that BPF verifier is giving us this advantage of managing lifetimes. So to leverage that, we said that why not generate landing pads during the verification step itself. However, there is a third property which we are not leveraging yet. The property that the verifier also restricted the control flow. So there cannot be any infinite loops. The size of the BPF program is limited. All of this comes under the restricted control flow property, and we are not leveraging this yet. So can we do something about this? Here comes the implicit lifetime management approach we are talking about. The idea is, since BPF verifier already does the branch traversal, it gives an assurity that every branch, no matter what is the runtime state or what helper returns during runtime, etc., no matter what, every branch will perform cleanup. And that's where the memory safety property is coming from. So another way to put this is that the BPF program already encodes cleanup. So if we know that the program will always clean up automatically, why not just accelerate the whole execution in some way so that the program will always terminate and always clean up before terminating? So this accelerated execution is what we are calling as fast path termination approach. And here is the steps we are going to follow for fast path termination. Fast path termination is about dynamically patching BPF programs whenever termination is called for. And the patch program will be a faster, but yet a safe version. There are two steps involved. When termination is called for, we patch away all the helper calls so that we get a fast fall through. But again, the step two is that step one is not completely true. We have to selectively leave those helper calls which are freeing up resources. Now, what these two steps mean, we will go through that in a visual explainer now. Let's say this is a BPF program having a bunch of allocations and deallocations happening. And there is also one of these long-running BPF helper function calls, like the BPF loop, or it could be anything else. Now, let's say the first allocation happened and we have the first object with us right now. And then we get the kill signal. So as per the two steps we discussed, we are going to patch away all the helper calls here, but selectively leave only the freeing up helper calls. So what we did is that we stripped off all the helpers from the BPF and only the simple BPF ALU instructions would be remaining. Now, as the verifiers would have already imposed a null check for all the resource allocations, we are leveraging on this fact that when forcing these helpers to fail, we will be forcing the program to take the nearest exit route. Now, this is what we are calling as the fast fall through here. Now, at the end, the last free call will be executed, and this is what we are saying as implicit lifetime management. Even if we force the helpers to fail, we still are assured that these exit routes will still clean up before terminating the BPF program. Now, we are making an important assumption here. The assumption is that by making these helper fails, we are assuming the programmer would have checked for the failures and would have taken the right step for it. However, spoiler, this is not always true, and we are going to talk about that in a bit. So we talked about issue one in the implicit approach, how to track lifetimes. Now talking about the second issue, when to trigger unwind. Unlike the implicit approach, we don't need the concept of safe termination points here. It is going to be always safe to patch a program. However, there is another kind of problem involved. We need to be sure that we are atomically patching the instructions. The point to note here is that this BPF program will already be executing, and if we try to mangle it during the execution, we might end up in an inconsistent state. So for that, we need some level of at least the instruction level atomicity while patching it. However, to avoid all of this game, another simpler way would be to halt the execution temporarily, apply the patch, synchronize this patch to all the CPUs, and then let it resume. A way to do this would be, again, we can reuse the flag or the key probe approach we discussed in the implicit section. And just that the reason why we would be using the flag check or the key probe approach is not different. So coming back to the motivation here, we saw these long-running helper functions and how they can end up executing this BPF program for several hours. Now, in this case, let's say the program we were discussing before, we actually ended up running the BPF loop, and now it's running for a real long time. And what can we do about this? So what we found is that the long-running helpers are actually always comes under two categories. The first category is when these helper functions keeps giving back the BPF program the decision whether they want to continue the execution or not. So if you see an example here, in this example, a BPF program is calling the BPF for each map element helper. And this helper is now iterating through each element of the map and calling back the callback function, which is a logger just printing the object. So in this case, what we can see is that depending on the return value, the helper decides whether it wants to continue the execution or not. So what we can do is cleverly pass the return value upon termination request so that we use the existing facility of early exiting this long-running helper function. So this case is valid for the 3 of the 4 helper functions we saw. However, for the last helper function we saw, which is the BPF find VMA, this does not hold true. This comes under the second category where this helper is just another long-running helper function. How? Let's see that. So in this case, we again call this long-running helper. And we see that it is calling this kernel function called find VMA, which goes and traverses a maple tree to find out the correct VMA object. And only if the correct VMA object is found, it calls the callback function. So in this case, we see that the long runtime is not because of the BPF program, but because of the kernel code, because of a piece of kernel code. And in this case, the observation here is that we cannot safely terminate in any way if a kernel code is responsible for long runtime. We can only safely terminate when BPF is responsible for long runtimes. So coming back to the assumption we talked about previously, the assumption that all helper functions do have a failure case which is checked currently. However, that does not hold true. We found two examples. One is the BPF spin lock helper function, and one is the BPF ref count acquire kfunc. In both these cases, it is always implicit. I mean, in BPF spin lock, it is always applied. In the ref count acquire, it is often applied that the failure cases will not be needed to be checked. So if you see the example for spin locks, we always know that the spin lock is going to succeed, and we will only go to the critical section after the lock is acquired. However, if we want to patch this program so that the spin lock starts returning error cases, we need to deal with those error cases and only go to the critical section when the error didn't happen. We want a similar kind of change to be made in all the helper or kfuncs which are not having error checks mandatory right now. And this will make the whole BPF more of a termination compliant. So what did we gain from the fast path approach, from the implicit lifetime management approach? First of all, we removed the complexity which a probable landing pad approach will bring into the kernel. The complexity of managing the landing pads through several layers of translation process, we are removing that. And by removing that, we are assured that there cannot be any bugs in the landing pad which could end up weakening the memory safety properties. But however, we have some limitations of this approach. The first limitation is that we propose some changes and in some of the helper and kfuncs to make it more BPF compliant. However, that means that we are putting more baggage on the BPF programmer to check for more and more failure cases in their BPF programs. However, a point I would like to make here is that the verifier already imposes a lot of these programming practices on the programmer so that to basically ensure safety, to basically ensure that if an allocation is not happening, we don't end up dereferencing null values. So we are just trying to make that programming practice more consistent by adding these compliancy proposals. Now, the second limitation here is that even though we passed away all the helper functions, which we believe is the meat of the whole execution time of any BPF program, we still have left with the simple BPF instructions. Now, even after the program is passed, those simple BPF instructions will be executed, and it will take it will bring some amount of delay. So this is a delayed termination approach, and it won't be giving an immediate termination. The last point I want to make here is that whatever objects were allocated before the termination happened, let's say we got a map object, we got a kernel pointer, or anything like that, even after we have called for termination, those objects could still be modified. Now, depending on the use cases, if that is too severe, a programmer can make more checks to check whether a termination was called for or not. But that basically means we are circling back to more baggage on a BPF programmer. So we just discussed the implicit approach. And we are towards the last part of the presentation here. So what did we take away from the fast path termination? In the fast path termination, we tried to leverage the fact that BPF program already encodes cleanup. And this is pretty unique to BPF because in other programming languages, we are almost not sure that a programmer is always responsibly cleaning up the resources they have acquired. There could be inherent runtimes which are doing that for the programmer, but often a programmer cannot be trusted. However, in case of BPF, we are getting this unique property and we leverage that. Also, because of the control flow restrictions, we could think that we can just accelerate and be sure that a program will terminate. It won't keep looping back and forth, and there won't be ever a chance that we never terminate. Now, then we propose that we can patch a BPF program to accelerate the execution. And towards the end, we saw that how the long-running helpers can also be leveraged based on the fact that if they are switching back and forth between the BPF and kernel, and they support early exit through return values, then we can leverage that and pass the BPF program for that. Now we come to the summary of the whole presentation. We saw that BPF termination is a two-part problem. The first problem is how to know which resources to clean up during termination, which is how to track live objects. And the second is how or when can we trigger unwind. We saw how it is not safe to trigger a termination when we are within a helper function. Now, then we saw a couple of explicit lifetime management approaches, the list and the unwind table approach. They all had their own runtime overheads or complexity issues. And then we moved on to propose the fast-path termination. And towards the end, we made some assumptions and then tried to make the whole BPF more termination compliant by proposing further changes on some of the helper or kernel functions. So that brings me to the end of this presentation, and thank you. Any questions?
I have a question maybe. So in terms of, you mentioned earlier like this kill signal, right? Like how would you go and implement that? Because oftentimes BPF program is not its own process, right? So it would affect like that process that it's currently running under. And then the question is like, what about this race condition, like until the time when you would go and patch something, right? I mean, it still is executing. And then what about other programs? I mean, other events that would trigger that program because it's the same text section that you would patch, right? So they would be affected as well.
Yeah, actually for the text section problem, we think that at least we can have a per CPU BPF text section so that if you are patching in one of the CPUs, at least the other processes are not getting interfered. Or another way to think that would be, okay, again, just to take more clarification, is the question that once we have terminated a program, is the problem that we still would end up triggering the same patch program, or is the question that another parallelly running process can still execute that BPF program? So I need that clarification.
I mean, others could, I mean, I don't know, let's say like a load balancer, whatever that you have, right? I mean, other like there could be processed in parallel from other CPUs as well, and they would probably be affected too. But like, I mean, like this patching, unpatching is like, how would you ensure that it's only affecting the program code that is currently running that you actually want to terminate, but not others that are okay, right? That do not hit this condition, for example.
Okay, actually, yeah. So talking back about the per CPU thing, I think that if the problem is that parallelly some other program can start running that same BPF program, then we can introduce the BPF text as a per CPU text and not the global text. However, there is indeed a limitation that in the same CPU, if some other process wants to execute that BPF program, then yeah, this is a problem which is not solved yet.
Yeah, because it can be like, I don't know, 1 million packets per second running the same program. And if you patch one, you drop all the other packets as well.
Sorry, can you repeat the question?
If you have, say, an XDP program, which is load balancing packets, and you run on the same CPU, you have like hardware queue receiving packets. And if you patch the text, you will affect all the other like 1 million packets per second.
Yeah. This could be a problem in the same. Yeah, this could be a thing, but another way to look at this would be that most of the time the XDP and the network packet dealing BPF programs are not really long running. So in a way, we can say that these network packet and this section of BPF which deal with networking applications does not really run for a long time. So most of the time we are looking at the probing or other use cases where we can try to traverse the VMA and do some debugging or observability. And in that case, we end up running for getting a long execution.
Yeah, and do you have an example of like use case which happened in production where your program runs like for a second when it doesn't use printk, but just like a real example?
Yeah, actually, that's a good question. So right now, I don't believe there is an example on open source, But we believe that as the complexity of these BPF programs will increase and the whole infrastructure will get more and more complex, is that when one BPF program is getting uploaded, it might be interacting with other BPF programs. Or we might be trying to call the find VMA, let's say the find VMA helper, and that the developer might not be expecting there would be a large number of VMA lists depending on how many lists they are. Because if there are like each objects are of very large size, then sorry. So if there are several objects in the VMA list, then even though the helper was expecting this, even though the programmer was expecting it to return quickly, but during some corner case during the execution, we will end up having a big list which will be iterated like forever. So that is one of the probable use cases we are seeing that, and that is something we are envisioning when the whole system gets more and more complex. More BPF programs or the BPF infrastructure complexity in itself is increasing. So we are envisioning this problem to come like in some time.
Thank you for a very interesting talk. One more question. So like this is actually a really interesting idea of reusing the program itself to do this fast pass execution to accelerate it to release the resources. But it will only release the resources that has to be released within the program lifetime, like spin logs. So this approach is like very interesting and will apply to things like spin logs mostly, and where they have to be released within the lifetime of one program. But anything like a socket ref counts or any kfuncs that do acquire, they won't be, right? So the cleanup pass might not exist inside the program because the resources are staying longer than the program itself. So you cannot reuse the execution of the program where the signal happens to do the cleanup of all of the things. Like let's say like task struct acquisition kfunc, it will just like increment the ref count, it will stay there. So if you just like continue and you patch all the calls inside that particular program, it will just continue. So you still need probably to solve this problem a combination of the approaches of one that Kumar just presented, of actually like analyzing the code and seeing what the program acquired in this asynchronous kind of way and releasing it separately. And spin logs, for example, yes, they can be used by this accelerated path. But it's great that like different people working on a similar problem from like very different angles. It means, well, that the problem is real and we'll solve it eventually.
Yeah, I would like something on that point actually. So along with spin logs, we also like plan to deal with the allocations, other allocations as well. Like let's say talk about ref counts. So when we get a ref count, then we also have to put the ref count as well at the end. So while we increment the ref count at the beginning, we also try to decrement before exiting. So the idea here is that we don't patch away those put reference count helper functions or kfuncs, so that even those cases could be dealt with in this proposed approach. So do you think that could solve this issue?
Send the patches, we'll see. It's hard to see it's working, but yeah, looks very interesting.
Yeah, all right. Thank you.
Thank you.
All right, so we have a break until 11:30.
Where's Johnny? Did he come? No, he couldn't make it. I mean, like, he was at QCon, but then family, kids, so he will present virtually, basically.
time they changed the battery.
Okay.
Yeah, it's still full. I think you guys changed it up.
So we definitely had a lot of people just anyone or whatever customer that they wanted, which.
So you don't need like you don't need a U program, like you don't have to, like a guy or like a Facebook yeah, okay, yeah. Okay. Yeah, nice. Does the user space runtime have like helper functions in this?
Yes, all have like that. Loaders we can use.
Okay.
You can run like video create completely.
Okay. And so it doesn't touch the kernel at all. There's no system call.
You can also work with
Yeah. This is super cool. Yeah, I was just talking to somebody recently about he's like a binary hatching person, and he had this like elf loader thing, which he would change the elf loader to be this other elf loader, like not the Linux, but it would be something that like basically would allow you to rewrite pieces of the program. You specify it in like which elf section you wanted to change, and we were talking about whether or not we could basically implement trace points, like or with the first FNV, like those little like no ops at the top of functions, like just do that in the elf loader for any binary. So you give it a binary and it puts those things in, and then you have the sort of hatching framework also kind of put there. So it's like an elf loader piece which would implement basically what you're talking about. I think like what you have is like the same idea without the elf hatching. Yeah. Yeah, the other thing is that now is doing a project on doing a CFI kernel. So
To connect, check.
all the indirect functions.
Why is it not working?
That's also like another thing where it's like there's a lot of different places that we want to run these programs, and they're like kind of unusual. Like we tried so hard to use the FNG ones, and every time we worked, like it worked. We're like, we thought it worked. And they were like, no, it's not working anymore. But
yeah, you triggered after discussing with you, I think, that triggered like a few weeks of like, wow, we can do that. The whole summer thing went away. Like, oh man, then we go back. You know what? Actually, the whole summer thing actually still works out.
And then we realized, okay, if we attach the small structures, then it's like he has like he's got LPC for every indirect function.
Right now it'll make noise. So.
I'm at least going to get a drink, so it was great to meet you. We should talk more.
I was graduated from science papers like I'm not even we were talking about maps that get updated by the user space and K-Pro as well, and then they would like, no. And then it's like, oh, no, we can't. So, like a new was it? No, that's perfect, because that's exactly what I wanted. Like, I was talking about some preliminary results, because I tried bringing funk latency from BP, from React new probe that traces the latency of a single function that you can specify. I tried running with BPF, and I didn't see the optimization yet. I just wanted to see how I can Oh, that's why.
All right, back from the break. Please, everyone, have a seat. You all set? Perfect. All right. So the next session will be by Hari Shankar on verifying the verifier. Okay, take it away.
Hello. Yep. Okay. Hello, everyone. I'm Hari, and this is work done at Rutgers University with my amazing collaborators here. Let's verify the eBPF verifier. So here's a quick summary of my talk. The eBPF verifier is essential to the safety and security of the eBPF ecosystem, and static analysis is a crucial part of this eBPF verifier. But despite our best efforts, writing correct static analysis is really hard, and this is where formal verification tools can be put to good use. We present a tool called Agni based on formal verification that automatically checks the correctness of part of the static analysis in the verifier on every commit. Agni reports that the static analysis in the kernels 513 to 519, the latest we checked, are correct. And for prior kernels, Agni reported that the static analysis has bugs, and Agni can generate proof of concept eBPF programs that manifest these bugs in the eBPF verifier. Mainly, I'd like to use this talk to solicit feedback from this wonderful community. So please give us feedback. Okay, so the static analysis in the eBPF verifier must be sound. Soundness means that the verifier should reject unsafe programs, where safety refers to some of these properties. And in doing so, it may reject some safe programs, but that's okay. But writing correct static analysis is really hard. In the recent year, there have been several vulnerabilities in the CVE database related to bugs in the static analysis in the verifier, and they've been exploited and threatened to undermine the eBPF ecosystem. So with my research, we sought out to answer the question, can we formally verify the soundness of the static analysis in the eBPF verifier? This brings us to the goals of our work. We want to make sure that the kernel static analysis is sound on every commit. Now, the verifier is a large code base that is constantly changing with fixes to old algorithms in static analysis and new algorithms to support new eBPF instructions. And one option we have is to manually encode the kernel eBPF verifier code into logic on every commit, perform the verification, talk to developers, and fix issues. But I can tell you from experience that this is not fun, and it's very tedious and also error prone. So we thought it would be a good idea to automate this process. So how do we automate? Our goal is to start from the source code of the kernel on any commit. We develop a tool that automatically extracts the semantics of the eBPF verifier C code into logic rather than manually writing them. We develop soundness conditions to specify when the kernel static analysis is sound, and then we perform verification using an SMT solver. Okay, sometimes we find that the particular kernel commit is sound. That's great, we have a sound verifier. But what if our soundness checks fail? We care about the real world. Can this soundness violation be actually manifested through an actual user-supplied eBPF program? And this is where we go ahead and synthesize a proof of concept eBPF program that demonstrates a mismatch between the concrete eBPF bytecode semantics and the abstract verifier semantics. And this allows us to weed out the false positive from the real bugs reported by the SMT solver. Okay, so this figure shows a non-exhaustive list of the various kinds of analyses done by the eBPF verifier. And the focus of my work has been on the value tracking analysis done by the verifier, which tracks the values of program variables or registers, the values program variables or registers can take across all executions. To make the analysis practical, the verifier over-approximates the set of actual values of program variables using abstract values from an abstract domain. The verifier uses two domains for value tracking, the bitwise domain and the range domain. And these two components learn from each other, making reasoning about the soundness of this combination a little complicated. So let's see the bitwise tracking analysis. The verifier uses the bitwise domain to track individual bits of a program variable. The kernel calls this the domain of tri-state numbers because for the purposes of tracking, each bit in a variable can either be known to be 0, known to be 1, or unknown, denoted here as mu. So let's see an example. Let's look at variables as if they had only 4 bits. And suppose we want to track the individual bits of a 4-bit register, R2 in this eBPF program snippet. Tnum R2 can be used to track R2. And initially, we don't know anything about R2, so all of R2 is, Tnum R2 is set to unknown. And on line 1, R2 is the result of the logical AND of some unknown external variable called input with 8. And even though we don't know anything about input, we can say for sure that R2's least significant 3 bits are certainly 0. Only the most significant bits may be set, if at all. As R2 undergoes further operations, the value of Tnum R2 is accordingly updated. And importantly, the information encoded in Tnum R2 can be used to determine the infer that the value of R2 will only be either 4 or 6 in all executions. And this can later be determined to use the safety of the memory access at line 5 that depends on the value of R2. Now, the kernel specifies algorithms for abstract operations on abstract values corresponding to the BPF operators. The soundness of the verifier's analysis depends on the soundness of its abstract operators. Shown here is the Linux kernel's implementation of Tnum AND corresponding to BPF bitwise AND. So how can we say that Tnum AND is sound? Let's look at how we can think about soundness of an abstract operator such as Tnum AND. Let's say we have two tnums, P and Q, and they are tracking program variables X and Y. If P is tracking X, then X has to be a member of P. What does this mean? So using a previous example, if P is the tnum 0, 1, mu, 0 from earlier, then member of P, 4 returns true, whereas member of P, 1 will return false. Similarly, since Q is tracking Y, Y has to be a member of Q. And let's say that Z is the result of the BPF bitwise AND operator on X and Y. And R is the result of the tnum AND of tnums P and Q, which corresponds to the implementation I showed before. To see whether a tnum AND operator is sound, we can ask the question, is it ever possible that tnum AND produces an output where Z is not a member of R? And we can prepare a logic formula that looks like the one here and present it to an SMT solver. There are efficient solvers out there that can find satisfying assignments to these variables in the formula. And if the solver finds a satisfying assignment, this means that we have a problem and tnum AND could be unsound. Okay, all that might be pretty straightforward, but if you recall, I also mentioned that the eBPF verifier also does range tracking. It uses an upper and lower bound to track a range of possible values a variable can take across all executions. Formally, this is called the interval domain. And if you use a previous example again, the range of program register R2 can be tracked using the abstract value interval R2. Interval R2 starts with the maximum possible range for 4-bit variables 0, 15, and after line 3 concludes that the interval R2 is 0, 6, which means that the value of R2 will always be between 0 and 6. But recall our analysis in the tnum domain. It was more precise because it was able to infer that the value of X will only be one of two values, 4 and 6. This begs the question, can the range analysis somehow learn from the tnum analysis? And the answer is yes, and this is also what happens in the verifier. This brings us to the idea of refinement in formal methods, using abstract values in one domain to update the results in another domain in order to improve the precision of the analysis. If we use the information in the tnum domain, we can update the range from 0, 6 to 4, 6 in the interval domain, which is more precise than what we had before. Okay, now let's see how we can reason about the soundness of refinement. Note that this is not what happens in the Linux kernel, it's just how someone maybe with a formal methods background would think. Consider this program snippet that we have here where R7 is the result of the addition of R5 and R6. And let's say at this program point, the two analyses in the interval and the tnum domains are tracking R5 and R6, and they have these specific abstract values. Because there is an addition, we can perform an addition in the interval domain to obtain 8, 10. We can also perform an addition in the tnum domain to obtain mu, 0. Now we define a new operator called the refinement operator that takes two output abstract values from different domains and combines them into an output value in a particular domain. Here the refinement operator produces an output in the tnum domain, and tnum R7 is calculated to be 1 mu, 0 by the refinement operator, which is indeed more precise than what we had before, mu, 0. Okay, so but what about the soundness of this entire process? Typically we reason inductively, which is that if we prove that the soundness of the abstract operators in each domain is sound, and separately prove that the refinement is sound, we can claim that the entire analysis is sound. And this is what we call modular reasoning. Modular reasoning makes our life easier because we can think about individual components, prove their soundness independently, and claim that the entire process is sound. But unfortunately, this is not what happens in the eBPF verifier. We start with the same initial abstract values in both the interval and abstract domains, and the tnum addition operator produces an abstract result as usual. However, the verifier defines an operator for the interval domain which isn't the typical refinement operator we saw before. It consumes inputs from the interval domain directly without producing an intermediate interval result. So we cannot modularly prove the soundness of the entire process by proving the soundness of individual components, and that's why we have to prove the soundness of the entire analysis in one shot. So here's an overview of all the eBPF verifiers value tracking domains. It uses 4 variants of interval abstract domains. For example, this S32 abstract domain tracks an upper bound and lower bound of a program register when interpreted as a signed 32-bit value. And we've already seen the tnum domain from before. And as we also saw, the eBPF verifier also performs refinements which are non-standard from conventional formal methods. The effect is that ultimately the eBPF verifier does abstract operators that defines abstract operators that operate on abstract values drawn from a combination of these different domains. So how to think about the soundness for multiple domains in one shot? Here are the constraints you saw before for a single domain, previously, tnums. And here are the new constraints for multiple domains with the changes in red. This is similar to what we had before, but the abstract values P and Q are now a combination of abstract values from all domains. And the abstract operator, the abstract operator is also one that modifies the abstract values in all domains in one shot. And this is the code snippet from the eBPF verifier that performs operations on abstract values for ALU operations. The top level function contains a switch case for each ALU operations. As we are interested in bitwise AND, we need to look at the BPF AND part of the snippet. And each of these cases perform several function calls. And you can see also there is a call for tnum AND here. To prepare a logic formula, we need to encode this slice of the eBPF verifier's code. And this is where I wanted to highlight the importance of automation. It would have been very tedious and error-prone to extract the correct abstract operators in logic manually. So Agni's automated verification supports the usual arithmetic and logic operators listed here. We exclude multiplication from an analysis because its implementation contains a loop, which needs to be unrolled when converted to logic, which leads to a very large formula, and verification times out. We also support the following jump abstract operators. An important feature of Agni's verification is that the constraints are strict. It only reports bugs that happen during program verification. As an example, there was a recent post on the kernel mailing list where a fuzzer discovered a bug that occurs only when the verifier followed a branch that could never be taken during an actual eBPF program execution. Agni does not report this bug, and this is a good thing because we don't want to burden developers with too many false positives. It is, however, easy to weaken the constraints, and by doing so, Agni was indeed able to discover this bug. Okay, so here are the results when we ran Agni on a few major kernels. It proved that some of the newer kernels are sound, but Agni reports that these other kernels have abstract operators that are unsound. So what do we do about them? Even with strong constrained static analysis like ours can generate a lot of false positives. We wanted to know whether these soundness violations are actually possible to be manifested by real eBPF programs. And how can we do that? By generating actual eBPF programs that expose bugs. Now, I wanted to highlight that generating eBPF programs is hard because you cannot simply achieve any arbitrary abstract state in the verifier. Consider the realm of all possible abstract values. Let's say using our soundness constraint from before, we see that the abstract operator B AND is unsound. This means that there exists some abstract values P and Q to the abstract operator that cause unsound behavior. Now, the eBPF verifier begins with all abstract values set to some initial values, and it is possible that P and Q do not belong to this initial set of values. However, it might be possible that the verifier can reach these values by using some sequence of abstract operators applied to this initial set. Crafting the right sequence of abstract operators is challenging because it requires manipulation of abstract values across a combination of these abstract domains. At a high level, we use a technique that is a combination of a program enumerator and a solver. The enumerator generates skeletons of eBPF programs with holes for operands. The solver fills in the holes with values such that the program will manifest bugs. Agni's synthesis supports ALU and jump instructions from before. And I also wanted to highlight that adding support for jump instructions was difficult but critical because jump instructions manipulate abstract values in ways in which purely ALU instructions are not able to, allowing us to explore more abstract states. Okay. So yeah, I just wanted to give a small demo of the synthesis part. So yeah, this is a video here. So we have a collection of the bugs synthesized by Agni in this directory. And I'm going to go into the 5.8 kernel. And here are all the BPF programs which are actually can trigger a bug in the kernel. So if you, I'm just going to give an example of one program, which is, and all of these programs are such programs. And what I'm going to do next is we're going to go into an actual kernel that is running 5.8 and see if it's possible to see the bug that we have, that Agni has generated. So I'm just running the script here. So what you can see here is that, as I am going to highlight here, this eBPF program, and this is just a part of the verifier log. This eBPF program generates an instruction that generated an instruction that produced S32 min value, which is greater than S32 max value, and that should never be the case in a sound verifier, where the minimum bounds is greater than the maximum bounds for a particular register. So, and these are, so Agni has produced all these eBPF programs that you saw before, which exhibit similar behavior in the verifier, which exhibit unsoundness. So I just wanted to highlight that not only does the developer know that there is a bug, but the developer also has an actual proof of concept eBPF program that they can run in the verifier and see the bug manifesting. So here's a summary of our results. And I said before, we used Agni to verify 16 kernel versions, and out of these, we found that 9 were unsound. And in the unsound kernel versions, we discovered 27 previously unknown soundness violations and 93 known ones. And these known violations were part of 8 well-documented CVEs. And Agni is able to produce a proof of concept eBPF program in 97% of the cases where it found soundness violations. And for those interested, here are some numbers for runtimes and peak memory consumption for 2 representative kernel versions, 5.9, which Agni found to be unsound, and 5.19, which was indeed found to be sound. Proving that a kernel is sound takes longer. In unsound kernels like 5.9, the SMT solver can stop after finding a soundness violation and then proceeds to synthesizing it. The peak memory consumption is in the range of 16 gigabytes. So I want to conclude with saying that we have put some decent amount of engineering effort into this, and we would like developers to use this tool. And our goal going forward is to make Agni as push button as possible, and your feedback would be immensely valuable with this. Concretely, we want to work on reducing verification time. As you saw before, it takes a lot of time to maybe around a day at least to verify a kernel. And I would like to give a shout out to Paul Chenot for his efforts to parallelize Agni so that each BPF instruction can be verified in parallel. We also want to explore profiling the verification to identify bottlenecks. And we also want to ensure that the code extraction from C to logic can support future kernel versions reliably. And we also have some interesting avenues for future exploration as well. And with that, I'm happy to have you ask questions.
I have a question. Feedback. How easy it is for kernel developers to extend Agni with new instructions? What's your take on that?
Yeah, it should be if you have concrete semantics for that instruction clearly defined as the eBPF instruction set, and you know what part of the verifier code. If it's similar to like ALU instructions we saw before, like there's a switch case, then Agni is easily able to extract the semantics of that instruction, and you can perform the verification. If you can specify the semantics of the concrete part and the abstract part easily, then it's straightforward.
And I think we should add all these generated test cases from the previous kernel to our CI. I mean, that would definitely be useful as well.
Yeah, definitely. We have a lot of these cases, and each of these cases are a concrete demonstration of a mismatch in the semantics. So that'll be great.
And yeah, we are actually adding this validation check that the range is well formed, and with special flag, we will, reject the program. So it will be actually easier to detect this. In your case, right, like you've shown the verifier log.
Yeah.
But human has to go and look at like, oh, this doesn't look right. So now we'll have like enforcement basically.
So you're saying you will have an enforcement if the verifier finds that
yes,
there is a case where there is a mismatch in the.
Yeah, there is patch stat right now under review, but like, and it's just like small part of that. But basically, like after each modification for LU operations or for conditionals, we check that like all the ranges are well formed, and if they are not, by default we reset them to like unknown basically.
I see.
But like if you specify a new flag that BPF tests, sanity checks, whatever, strict some name, which you can specify when you load the program basically. And in that case, like when we detect this violation, we'll reject with the message. So that should help you with writing the test case.
But I mean, just a question: isn't that I mean an issue with the verifier that the analysis isn't sound, and that's why it went into a state where
Yes and no. So there are known situations where like we don't detect, like dead branches basically. And when we have dead branches, we have non-overlapping ranges, but we still try to combine them. And when you combine non-overlapping ranges, you get invalid range very often.
Right.
And we just, well, right now we accept that this is possible because, I don't know, we haven't patched up all the different cases and all stuff.
Yeah, I remember. I think that example that I showed was one of those cases where there were non-overlapping ranges. The verifier followed one dead branch. That was the recent post in the mailing list, right?
Yeah.
I think like in terms of the CI integration, once we would get there, right, it would probably be useful to have this at least once a day if possible, depending how much this can be parallelized and their time shrunk down so that it's still easy to bisect what change introduced this.
Yeah, exactly. I think the main, I mean, we've been trying to reduce the verification time a bit, but also it's kind of, and make it as push button as possible. So you can just like have it with CI, it'll take some while, you don't need to monitor it. If we get to that point, make it as push button as possible, then it'll be.
Yeah. And one thing that would be super useful, if you have the cycles for it to basically check the current batches that are going on the mailing list to the soundness validation, right? I mean.
Yeah, definitely. That's immediately the next thing that I was planning to do after the conference, to check Andre's patches. But one, I think there was the last time I tried it, there was one breaking change with respect to our code being able to handle it. So I think, but it should be doable to handle the patches.
Yeah, question on behalf of people that are maintaining BPF CI, like what are the runtime dependencies for like this approach? Like if you were to integrate it into CI, like what kind of things you expect to have?
Right, so our dependencies are the C to logic extraction, that depends on the Clang toolchain. We need LLVM. We basically convert the C code into IR, perform some LLVM passes on that, and then convert it to logic. It also depends on the Z3 SMT solver.
Is that available as like a Linux package that we can just install, or like how much work would it be to get it into GitHub Action Worker, basically?
How much work would it be to get it?
So we use GitHub Actions, right, for CI, and so we have environment that GitHub Actions provides, right? So like, how much work would it be to get this to work in that environment, basically?
Yeah, I mean, I'm not entirely sure, but I think so. The Z3 solver is available as a package for Linux, so I think that should be pretty straightforward.
Yeah, you were just talking about like push button, right? So like I would just suggest to look into GitHub Actions.
Yeah.
It's available in major distributions, I assume, right?
The SMT solver itself?
Yeah.
As a package, yes, exactly.
Perfect.
One more question, like from the bugs that you found in the old kernels, are there some commonalities, specific areas where you think, okay, review, like it wasn't found in reviews, but then it needs to be more attention on that, or any takeaways from the bugs that you found?
So I think we found that the jump, one of the major, obviously the major kernel versions, there was a lot of change, was 5.7 RC1. And generally we found that the jump instructions are the ones which are which also take the longest to verify, but also are the ones which were most buggy. And I mean, it's the logic is also pretty complicated compared to ALU instructions. So that's the general pattern we observed. But yeah, happy to discuss any other patterns we have.
Perfect. Really awesome work. Thank you very much.
you.
What do you prefer?
Okay.
I think we can start this way.
Okay. All right. Looks like we give you guys a few more minutes of memory model, which may be a good thing. It's really cool verification stuff. That was really, really nice talk. So please interrupt at any time with questions. It's more important to have a discussion and get me to understand what's going on with you guys and vice versa than it is to get through a set of slides. In any case, I last did one of these about 2 years ago, and it was, and we got some stuff we're going to go through here. Time permitting. I mean, some parts of it I'll skip or not, depending on how things go. But we've got this thing called the PSABI, and it defines a bunch of stuff. I'm not going to go through this in detail, but it doesn't necessarily cover a memory model. And there's one of these now for hardware. This thing essentially provides a manual to let compiler writers know what code they should generate. And with BPF, this is kind of implicit. There's JIT source code and also LLVM implementation, which are kind of the sources of truth for this documentation, which, you know, source code of documentation can be a good thing. Now, back 2 years ago, I said, look, we should use Linux kernel memory model because, well, in part because the other memory models are kind of a strict subset. The Linux kernel memory model promises more ordering than the other ones do by design. It's set up to do that because it needs to cover all the CPUs that can be out there. Okay, so that's easy enough, except that a month or two ago, Alexi says, hey, we need some more BPFM work. And I'm going, okay, I'm not sure what, but yeah, you know. And this reminded me of back a long time ago in high school. We had a vice principal. He's kind of, I mean, he's not the principal in charge of vice. That was a joke back then, but not really. He's kind of the principal, and you had the vice principals. This guy had a poster up on his wall. It was a line drawing. It shows this guy. He's kind of a disreputable guy. He's got kind of shaggy hair. He's got, you know, a few days growth of beard. He's got one black eye and several teeth missing. He's got this manic smile on his face. And the caption to that poster, and this was kind of my attitude towards this thing, is, we attack your problems with enthusiasm. Okay, so I don't know what's broken, but I'm going to fix it. Okay, I can take care of this. But to my surprise, I got this email from Jose Marchese, who I met before, and he's going, hey, it's great to hear you're working on this. I'm going, okay, why are you so excited about this? But what turned out is that there's a bunch of things that have to happen with this. And one of them is that we need to concurrently share data between a bunch of different places. So you could have multiple BPF programs that have common maps, common data. You have BPF programs talking to user space programs in various ways. And also, of course, you have helpers in kernel code, and you have to get that straight as well. So, there is some potential problem to be solved here. And here's why Jose is near as I tell. I actually met him. He was at the Rust workshop, Rust and Linux workshop in September, and I met him shortly after that. And the thing is, we got these memory models at the language level. We've also got it down at the ISA, and some of these things are formal and executable. You can say, all right, here's this stuff, tell me what happens. And that's really nice. But we don't really have a formal memory model for the BPF instruction set itself. And of course, Jose, he's in the compiler bucket there, in the little compiler arrow. And so he really wants to know precisely what's going on with the memory model so that he can generate the proper code. I mean, totally understandable. And well, that's what this talk is about. If I can do the right thing here, I did not want to do that. Let's see if I didn't. Okay, it looks like I managed not to break anything. Okay, don't worry, I won't manage to not break anything again. So that's what this talk is about. This talk is about very specifically supplying a memory model for the BPF instruction set itself. All right. So we'll touch on a bunch of other things. There's some future work, possible expansions of the BPF instruction set, and we'll look at those later, but the main part of the talk is going to be pretty focused just on the instruction set and the memory model. So as I say, more work required, but this is kind of the next step. There we are. So the Linux kernel uses assembly, C, and actually there's some Rust. Alice Real showed me a smartphone that was running a Rust language Android binder inside the kernel. So, they're actually doing some pretty impressive stuff with that. And of course, assembly's been around forever. It has C. And the thing is that because of the special requirements of the Linux kernel memory model is not just confined to the same sorts of orderings that a language is going to promise you. Part of the reason for this is that a lot of the compiler writers really seriously, truly, and horribly hate the idea of tracking dependencies in the compiler. And so they say no to that. And that means that the language memory models don't know about dependencies. And we'll talk a little bit more about what those are and how those work later. And that means that the Linux kernel memory model relies not just on the compiler, but also on some strict coding conventions. And I'm not going to go through this in detail. We'll look at one of them later on in the slides when we get there. But if you look at memory barriers.txt in the documentation directory and search for the control dependencies, there's a big list of things. If you want your control dependencies to work, don't do this, don't do this, don't do that, don't do the other thing. And for address and data dependencies, which are used by RCU, there's an RCU dereference.rst in documentation/RCU that gives out a bunch of restrictions, things you're not supposed to do to your pointers if you want your stuff to work. All right. But the downside of the language models and the compiler writers hating tracking dependencies is that they are afflicted with something called out of thin air problem. What that means is that we don't want to use a language level model for the BPF instruction set. It is, after all, instructions. It's kind of both. We saw that it was kind of in the middle. There was language stuff above it a couple slides ago, and then there was instructions below it. And for the purpose of this presentation, we're grouping it more with the instructions that's below it because we don't want out of thin air values. And the hardware instruction sets avoid those. So here's the canonical example of out of thin air. This is a C11 program. You could kind of sort of get the same thing in Linux kernel with read once and write once, but not exactly. The difference is the compiler is allowed to reorder things if it wants to. So we've got the first thread over there on your right. Excuse me, on your left. And it's picking up X and putting it into a local variable R1, could be register, and then it's storing that. And we're starting out with X and Y both 0 initially. So it's just picking up X with no ordering and storing it into Y. Now, at the hardware level, it's really hard to store something before you've loaded it. All right? But the language level models don't recognize dependencies, so they don't know about that. As a result, on the other side, we're doing it the opposite order, picking up Y and storing it to X. And if you take the mathematical core, of the C11 memory model, it is perfectly legitimate for the answer to come out 42 for both X and Y. Now, that's just in theory, not in practice. There is no compiler or hardware that can actually do that, but the mathematical core of the C11 and C++11 memory models would allow that to happen. All right. Now, it's accompanied by a little note that says, don't do OOTA without saying what it is, because nobody's figured out how to precisely formalize it in a way that the compiler writers are willing to put up with. So as a result of that, we don't want BPF to do that kind of stuff, okay? And we'd like to make it easy for analysis tools to work that out. Therefore, we're going at the hardware level, and we're going to be honoring dependencies. Okay, there we go. So we don't have to look at all the BPF instructions. We do have to look at the atomics, the conditional jump instructions, load instructions, and memory reference instructions. So we'll deal with those. And why isn't load a memory reference instruction? Well, yeah, it is, but there's special things with load and store is a subset of that. So we'll treat them separately. Let's start with the atomic instructions. And the idea is that we want to we got this implicit memory model now. We want to make that explicit, again, so that tooling and compilers and JITs can take full advantage of it. All right, so we'll start off with the atomics. So we have 3 sets of atomics. These are the exchange and compare exchange instructions. Okay, and we also have, we'll also take a look at add, or, and so on, and also look at BPF fetch in combination with the add, or, and XOR. All right, so first we'll do exchange and compare exchange. They're fully ordered. What that means is if you have, let's just take an exchange, a BPF exchange instruction with all the stuff that takes it happen. All CPUs, tasks, whatever, all entities in the system are going to agree that everything that preceded that instruction in that task is ordered before that exchange, and that exchange is also ordered before everything afterwards. All right? And that's going to be global across the whole system. And that's consistent with the way that the atomics exchange and atomic compare exchange APIs work in the Linux kernel. Or if you prefer, you can use the relaxed compare exchange and put a full memory variable before and after. Either way, you get the full ordering of everything. Okay, that's straightforward enough. The next set of atomics are just the add, or, and XOR, but without BPF fetch. All right, and in that case, they're unordered. That means that the CPU, the JIT, the compiler, whatever, can order stuff freely across them. That's perfectly legitimate, and they're consistent with the Linux kernel non-value returning atomics. Atomic add, atomic or, atomic and atomic XOR. So these are unordered, they can be freely ordered, those instructions have no ordering semantics. And then finally for the atomics, there's this BPF fetch modifier. If you combine that with one of the BPF add, or, and XOR things, that gives you a value back. So the difference between not having the fetch and having the fetch, without the fetch, it just does its atomic and that's that, you don't see what happened. With the fetch, you get the value back. And in that case, they're all going to agree. It's fully ordered again. Everything before that atomic will appear to be ordered before that atomic from everybody's viewpoint, and likewise, that atomic will appear to be ordered before everything after it. And again, that's consistent with the value returning APIs in Linux kernel. Okay, so we're through the atomics. Let's take a look at the jump instructions. And this is only the conditional jump instructions. The unconditional jump instructions have no ordering semantics. So this is kind of strange. What we have is that in many architectures, in many computer architectures, a jump instruction, conditional jump instruction, has very weak but still very useful ordering semantics. And the way that works is that this is again just the full list of them. And the thing here, the thing that's important is if your JIT is too smart, it needs to be careful. So the weak ordering applies. You got a load instruction, and that load instruction's value may go through some processing and then ends up at either the source or the destination registers, the two things that are being compared by the jump instruction. And if there's a store instruction after that jump instruction where control flow either goes to it, okay, but that's before the control flow converges, if all that stuff holds true, then the load instruction that the value came from will be ordered weakly before the store instruction. And that kind of intuitively makes sense. If you're going to decide whether to store something and you're loading something to figure that out, you kind of have to do this load before you do the store. But there's a couple caveats here. First off, the compilers are not helping us here. The compilers do not understand control dependencies and will happily break them. And we'll see an example of why this control flow converges qualifier is needed with conditional move instructions a little later. All right, so here's an example. So we've got some Linux kernel C code over there on the one side, and we've got the BPF instruction assembly on the other side. So we do a read once of X. If the value comes back is non-zero, then we write 42 to Y. And on the BPF side, we get the address of X and put it in R1. So the colors match up with what compile code goes with flash assembly instructions. And then we go and we pick that address up. We pick up we load X on the second line. And then we've got if R1 equals 0. So we've got R1, which value came from that load. That's mentioned in that branch instruction. So that's one of the conditions we had to meet. And then we say go to LBB02 down there on the bottom. So that means those 3 green instructions are within the scope. They're there before control flow converged. And that means the store, we pick up the address Y, we pick up 42, and then we store them. That store is therefore ordered very weakly after the load that's on the second yellow line. So the last green line is ordered after the last yellow line. And that's a control dependency. And this is a case where everything works out and it's nice. But the thing is, the compilers don't understand these and can break them. This is an example, one example of many, where the breakage would happen. Here we read X. If it's non-zero, we store Y1, but if it's 0, we store Y1 as well. Now, presumably, you'd have other stuff in the then and else statement, and it wouldn't be quite this silly, but this is a minimal example. In this case, the compiler can and will optimize it as follows. Oh, well, we're doing it in both cases, either side, so I don't care. I'll just pick it up and I'll store it. Forget the if statement. And if there's other stuff in the if statement, the compiler may just hoist that particular store out of the if statement and leave the rest of it in the if statement. Either way, there are CPUs that will reorder that. Okay, so and this is an example, I said earlier that we don't just rely on the language memory model for Linux kernel memory model, we also rely on coding restrictions. And for control dependencies, which by the way, please be very careful with them. They're fragile and easily broken. If you only use them if you absolutely have to for performance reasons, is one of the reasons why. One of the coding restrictions is if you're storing, you better not store the same thing on both sides of the if statement. At least not so the compiler can figure it out. Okay, like I said, please avoid them when you can. All right, so that's a broken dependency. That's why the coding standards exist. That's why the memory barriers.txt has that section in it that you should read if you're ever going to use them. The thing is, you're going, okay, well, wait a minute, we got a whole bunch of different architectures, and some of them do different things. What happens? And there's 2 different groups. The strongly ordered architectures, x86, IBM mainframe, and so on, they use TSO, and that means if you have a load instruction, it's going to be ordered against all the following store instructions, no matter what, and so you're covered. You had a load instruction, whether they have the if or not, doesn't matter. The store instruction came later, it's ordered. The weakly ordered ones, ARM v8, PowerPC, and so on, maybe RISC-V, what happens is that the hardware actually tracks the control dependencies for you. And so it realized, oh, we loaded this, it went into this branch statement, we've got this stuff under here that came after that, therefore I need to order it. But either way, no matter what kind of CPU you have, the ordering is preserved. Okay, what do we mean by weak? I've mentioned several times it's weak ordering. Well, with the atomics, we said that all the CPUs and threads, no matter where, agreed that we had one group of instructions, we had the atomic instruction, we had another group of instructions, that those 3 groups were ordered. Everybody agreed that. Here, not so much. It's visible to a given another CPU, but separately to the different CPUs. What the heck does that mean? Okay. Well, if we take a look over here, this is an example where the ordering isn't helping you. And the reason is, the ordering is visible separately to each CPU. Here we're trying to see that ordering across the center and the rightmost CPUs. So we stored 1 to X. We have a control dependency. We picked up X. We do a write to Y only if X is true, and that means that there's weak ordering between that read once and that write once in the center there. And the right-hand side does a SMP load acquire, and that does acquire ordering, which in the case of the Linux kernel memory model applies. If you were in C++ or C, you'd still have a problem. And then we read X. Now, if we had ordering across both threads, that read of X on the far right there would be guaranteed to C1. Okay, because we did a write, we read that write, we did another write, and then we read that write, should be later, right? Except that the ordering by control dependencies is only from one CPU to another. Here we have 3 CPUs involved. We have to see the ordering across all of them. And therefore, you really, truly can see both R zeros equal to 0. And there are CPUs that will really do this. All right. And so when you're using this is another reason to be careful with the control dependencies. They're a little more limited than you'd like, or might like, I suppose. Now, I said earlier that the store had to be before control flow converged. All right, and that doesn't make sense for the strongly ordered things, because if it's after, right? Who cares? For the weakly ordered ones, well, it doesn't know that things converge, it sees the branch. But the problem is the compilers can optimize, and there are these conditional move instructions. And that means we can see things like this. What happened is that we had a read once, we did an if, we stored different values, which means that the compiler is not going to break us that way. And then we stored to a different variable. And the control flow converges before we do that final store. Well, the compiler, if it has a conditional move instruction, could do something like the assembly language in the right-hand column there. It can do the load all right. It can also then just say, okay, if the condition is true, we're gonna do the move. Otherwise, we're not, and then we're gonna store. And that means that there is no branch. There's just a conditional move. And so that means that the hardware tracking done by ARMv8, for example, only applies to the red arrows there. It does not apply down to the move. So conditional control dependencies only apply up to the point where control flow converges. Okay. Load instructions. And what happens here is that if we do a load instruction and we use the value loaded to compute the address of a later store, that's an address dependency. All right. And intuitively, of course, if you picked up a value and use it as an address later, you really can't go backwards in time. You can't guess. So there's some ordering there. And this is in fact respected by all CPUs again, and it's weak in kind of the same sense that the control dependencies are weak, that the branches provide weak ordering. And again, we have different ways that this happens. In the strongly ordered things, they order all loads before all stores, so that's good. In the weakly ordered cases, and also loads before loads for that matter, in the weakly ordered cases, those things are tracked by the hardware again. And weakness happens in the same way in some of the weakly ordered architectures. These things are only pairwise from one CPU to another. So if you have something involving multiple CPUs expecting the ordering, it doesn't transitively play out, just like it did for control dependencies. Okay. And the final thing here for memory reference instructions, all of them, if you're referencing just a single variable, so you got a bunch of threads and they're playing with just a single variable, which by the way isn't that great for scalability, but still it's something that makes sense in some cases. All the CPUs and tasks will see some global order consistent with the loads and stores. It'll be as if all of those loads and stores happen in some global order. And this is actually supported by all CPU architectures, with Itanium being the exception that proves the rule. But the reason we get away with that in the Linux kernel is that Itanium is volatile, which is used by read once and write once, to generate load acquires and store release instructions. And those things provide heavy ordering. So that's why, but Itanium might be on its way out. I think it got removed and maybe coming back in. I'm not sure what's happening with it. In any case, I'm not too worried about it. As long as the compilers still do what they've always done, it'll work fine. If not, they did a bug and they need to fix it. And if it's not here, we don't have to worry about it at all. Sorry if you like Itanium. What can I say? I liked it too back in the 90s. They didn't come out with it as quickly as they wanted. That kind of soured me on it a bit. Okay, so JITs have to respect memory ordering. Okay. And there's a bunch of viable strategies. The things that are tricky here are the address control and data dependencies. And one way is to just generate instructions that match the BPF instruction set fairly closely. All right. So if you have a branch, generate a branch. Okay. Maybe you can do a conditional move if you are careful. Another thing you can do is you put atomic signal fence, memory or CST everywhere, basically telling anything downstream not to reorder things, the compiler not to reorder things. And the other thing you do is you could explicitly track and preserve the dependencies. So those are kind of like three strategies you could use to preserve the address control and data dependencies. The first one being the easiest, the second one not being too bad, the third one being, well, if somebody makes that work, that'll be wonderful, because then it'll be available for the compiler writers, and maybe we can make the language a little, memory models be a little more sane. I'd like that. A lot of people wouldn't, but I'd like it. The other thing we can do is we could just say that any loads have to be ordered before prior stores, and do whatever is necessary to make that happen. This is something that works quite well in the strongly ordered instruction sets. Okay. And there was there's some push to make C11 and C++11 relaxed atomics obey this, although ARM came out very heavily, strongly against this a week ago. The other thing you do is you can rely on the source code following the Linux kernel coding standards. So those are different strategies that are available when you're doing JITs. Doing JITs straightforwardly shouldn't be a problem. I heard a rumor that people are actually taking the BPF assembly language, turning into LLVM intermediate representation, and then doing full compiler stuff on it, in which case all bets are off. But if you're doing that, be careful, please. Okay, we're getting towards the end here. I'm going to do a couple of these. These are just a bunch of examples that I did to say, was I being sane? What I did was I took the GCC atomic built-ins. This is a little bit weird. I'm using the GCC built-ins as defined by GCC, but I was using Godbolt's compiler thing with a Clang backend, all right? Yes, it's the GCC API, but I'm using the Clang compiler. Now, the GCC atomics has all the orderings that you'd expect from C11 and C++11, relax, acquire, so on. They're all there. With the BPF instruction set, as it is today, we only have to worry about two groups. One group is relaxed, which has no ordering, and all the rest of them get full ordering, because that's what we can do right now. And if BPF were to add some sort of acquire, load, release, store, or some sort of weaker memory barrier, then we would revisit this and possibly have some of these things not be fully ordered. Right now, that's the choice we have. I'm going to look at atomic thread fence of atomic SC, the sequentially consistent atomic fence. BPF doesn't have memory barrier instructions in its instruction set. But that's okay, because you can do an atomic and get full ordering. So if you do an atomic with a field that isn't involved in anything. And in fact, the Linux kernel does with SMPMB. If you go look on x86, on recent Linux kernels, the full barrier in the Linux kernel on x86 ends up being an atomic instruction working on a stack variable. And that sounds kind of strange. I mean, you got mfence, right? What the heck are you doing that for? Well, it turns out that mfence has a bunch of extra semantics involving I/O and things like that make it slow. And doing an atomic instruction, doing a useless atomic instruction that's only there for the ordering turns out to be quite a bit faster. So that's what they do. Anyway, so BPF can do the same thing. Why not, right? And so we're going to call that BPF MB, just because if I try to write all that on every slide, it'll get to be a mess. So I'm going to take a look at loads and stores, and then we'll be, well, actually, I'll take a look at loads, and then we'll go to the future work part. So there's a thing called atomic load in and atomic load, which, by the way, Clang does not yet support. If you try to actually do one of these in Clang, it'll tell you, my backend doesn't know about this, forget it. Now, if you do it for x86 or one of the other ones, it doesn't know about it for BPF. But it could. And one way to make it work is in the relaxed case, just do a BPF load or BPF load LDX, depending on what size you're doing. And if you have non-relaxed ordering, you do the same load or store, but you follow it with a BPF MB, all right, for the other orderings. And so that's straightforward enough. And the same sort of thing happens for store, which, by the way, is not yet supported, or wasn't when I ran this. Maybe somebody fixed it already. I didn't think to check. And again, you do a BPF store or STX, and I've got a bug on the slide. I'm sorry. That should be, no, I've got it right. I'm just confused this morning. All right. Or I'm doubly confused and I have it wrong and I'm confused about being confused. Who knows? But to make that work, you would do this BPF MB funny atomic instruction followed by the store or STX, and that's how you'd get a non-relaxed ordering store. Okay, so we have exchange. It does what you'd expect. It supplies full ordering because it does. Compare exchange, same difference. And the fetch ops, you know, you do what you'd expect with those. And here, LVM Clang for both of these actually does all of them, but there's this funny NAND thing that it doesn't do. It'd have to make a compare exchange loop out of it. And likewise with op fetch. And there's some miscellaneous atomics, which can be done, and fences, which would be implemented that way. Atomic signal fence is a little bit strange. You'd have to do the same, as far as I know, you'd have to do the same inline assembly trick that the Linux kernel does for the compiler barrier, which is you have an ASM that has no instructions, but it uses the memory clobber. And that doesn't actually generate any code, but it tells the compiler to forget everything it knows about memory. It's a little bit ugly, and then it causes registers to get flushed and stuff like that, but it works. It would be really cool to have this function might not return clobber on the ASMs. And there's I need to ask people around here about that. I may as well right now. It'd be really cool to be able to tell the thing, this ASM might not return, because then it could preserve the registers, but have the right ordering still. But you know, who knows? Okay. And so let's talk about things that might happen in the future here. We might need to worry about BPF programs and helpers. Right now, the story is that they have to define what ordering to supply, if any. We don't want to force them to have ordering because they need to be lightweight. Some of them do. Different programming languages is kind of it's solved in practice just by people being careful. But if you have a BPF program in one language and BPF program in another language and sharing memory, you have two different memory models, and the compiler writers have to be careful to take advantage of that, to make that work. User kernel interaction. We have the same thing as for different programming languages. And there's a bunch of other things to happen where there's queues from the kernel to the user space, and that ordering is provided by those queues. And perhaps the BPF instruction set will gain some things. I'm going to skip through here a little bit rather than going through the, I guess I'm going to focus on this one a little bit. The compilers have to respect the BPF memory model, as do the JITs. And if that happens, things work out with multiple languages. So that's the thing that makes that work. Formal verification tooling, we might get some things going there, but I want to get agreement on what this is first. And perhaps we'll have acquire loads, release stores, and full barriers. If we do, then we can modify the memory model appropriately. Okay, so that's what we've got there. I can take questions, or people respond offline, or whichever. Either I've bored people to death, or got it right, or people too scared to ask questions. I'm not sure which. We got one. All right.
People are too scared to ask questions.
Okay, what's the question? Oh. Are people too scared to ask questions? He was claiming it was a third of my options, which are people too scared to ask questions. And the question for him, are people too scared to ask questions, in which case I have to ask you guys that question.
Did you have a chance to look into the current state from compiler side and also JIT side? Whether you found any inconsistencies that definitely needs fixing or not yet?
The ones I looked at, I kind of blasted through them. I apologize for that. The ones I looked at did what I would have expected. There were a bunch that didn't generate anything, but you know, that's, if people aren't using it, maybe they don't need to. But I checked that a few weeks ago. So if somebody did something last week, I'm sorry, I don't know about it. Good question. So we'll have to keep checking.
Oh, there's a question in the chat.
Oh, okay. Can I see it? Maybe well, why don't you just read it? Why don't you just read it out?
Okay, so the question is, you mentioned issues with code that transformed LVMIR. Does the same apply to BPF to C that races from BPF assembly to C, used for offline verification and native code generation?
Okay, might well. You know, if you were to, no matter what you do, if you take the BPF instructions, then put them through something that has a full-fledged compiler at the end, that full-fledged compiler is not necessarily going to pay attention to address data and control dependencies. And so those would either have to be, you have to do something in generating the C to preserve those, and we went through a few options to do that, or you have to rely again on coding conventions at the program level, the level of the source code that generated the BPF instructions, to make it so those transformations just can't happen.
Yeah, my question is, do you think it's worthwhile to say that BPF has control dependencies, or maybe you can just say, no, control dependencies are not part of the BPF memory model?
I considered that. So the thing is, the control dependencies are troublesome. I was not all that excited about control dependencies being added to the Linux kernel, to be honest with you. And then if you go read that thing I pointed out, you find a lot of scary text. This can happen, this can break, that. I wrote that with the intent of discouraging people. But there are some places where performance is really important. We don't use control dependencies very many places in the Linux kernel, but they are used. And where they are used, I mean, they are, you know, on the weekly order machines, it makes a difference not having the memory barrier there in some of the places where they're logging and transferring stuff into queues and stuff like that. So I figured that it would be a mistake to leave them out because they are used a little bit. But in most cases where you're thinking about using them, it's probably a mistake to use them. Not in all cases, but in most. Good questions. More? If not, thank you very much for your time and attention. And thank you for the people having the courage to ask the questions. Cheers.
Okay. Next session is on overflowing the kernel stack with BPF. Take it away.
Hello. Hello all. This is Roop and my friend Siddharth. We are presenting overflowing the kernel stack with eBPF. Yeah, so eBPF actually enabled us in a wave of innovations where we can extend user space programs into kernel in the runtime, ensuring all this stability and safety. And this guaranteed safety is being possible because of statically verifying the eBPF code by the eBPF verifier engine. However, the eBPF verifier is inherently assuming that all the safety conditions and checks that it has validated is being upheld by the execution environment. And one such assumptions is availability of stack space in the BPF program. So giving this actually, we kind of found a couple of issues with the stack around like attaching it, and also some kind of things with the nesting. And before going into it, we're going to give some background around like how eBPF program is going to interact with the stack. So whenever a BPF program is called at an attach point dynamically, so BPF program is going to inherit the stack. Inherit the same stack that it is running on, and this stack is being limited to 512 bytes. And so yeah, and if a helper function or kfunc is being called, it is again going to inherit the same stack. And yeah, so now we in this part of the section, we're going to concentrate like whether we can increase this 512 bytes to a larger number. And yeah, for that, like we have to use a couple of components in eBPF. One such is BPF to BPF calls. So whenever BPF to BPF calls is similar to the conventional function calls. In eBPF, when you call a function using BPF to BPF calls, it is going to create new stack frame, and all these calls are going to have contain in the same program, and it's still 512 bytes. And yeah, the next component is BPF tail calls. So whenever you call, whenever you use a BPF tail call, it's the jump instruction is going to call the new BPF program. So you can use this for calling BPF to BPF programs, and it's going to use the latest calling stack frame, and then it's going to reuse it and then grow its stack from there. The new BPF program is going to grow it from there. And yeah, so this is how we can visualize like in how it calls, and it can grow the stack like this. And what do we have right now with these two components, with these two combinations? What are the current checks and limits that the verifier has and the runtime has is, whenever you have this combination, it's not 512 bytes, but it is actually reduced to 256 bytes. But in the runtime, the JIT actually emits instructions where whenever you call BPF tail calls, it's going to check how many tail calls it's happening, and the limit right now is 33 tail calls. And if we use this combination, and then if you craft a program using all the limits, then you can actually reach to a program where the 512 bytes program is being grown to possible to grow it to 8 kilobytes of stack space. So so what's happening here? So the first thing is verifier is actually making two critical assumptions about the runtime, and the first one being kernel stack will always have 8 kilobytes of stack space available for a BPF program to run, and the second one being the total size of the BPF program's kernel stack, and the stack for any helper function it calls will be less than 8 kilobytes. So with this background, we're going to concentrate the first problem that happened, which is around the attachment, and then we'll go to the other problem, which is around the nesting. So in the first problem, we're going to concentrate on the base kernel of the base kernel stack, and the first thing we're going to ask is, so is it always the base kernel stack being innocuous, and then is it always small? And there have been cases that we have seen in community where file systems and networking kernel stacks can grow into a bigger stack number. And the question is going to be like this, where what if you attach a BPF program on top of this unclean stack? To just explore on this, we considered XFS file system, and then we ran a couple of test cases where under the constrained memory conditions. And so you can see here the base section where it has the XFS, and then and when it hits some kind of exceptional path where it needs to find some kind of memory and then scheduling, it actually grow the stack to very huge extents, and we almost reach more than 6 kilobytes of base stack. And in that, like we chose the top function where which is part of scheduler functions, and we chose kprobe. I mean, we have kprobes are offended to dynamically attach these functions at the runtime, and when we tried it using kprobes, I'll be showing at the end. And before that, like I mentioned the 8 kilobytes of program that we have that it explained in the first section. So this is what it looks like. So we have the base attach mechanism of kprobe in the base section, and then we have our 33 tail call BPF programs contiguously next to each other, and then we have the helper function which is being called on the top of the 33rd program. And these three sections actually combine consume almost like more than 10 kilobytes of almost near 10 kilobytes of stack memory. And if we just add up all these numbers, the base part which is bigger, and then attach type function, and then the 8 kilobytes of BPF program, and then helper functions, we actually overflowed the first overflowed the stack, and then these are first problem that we identified. And my friend Siddharth is going to explain the problems that he has encountered around stack overflow because of the nesting thing.
Hey, hello everyone. Thanks, Drew. Now I'm going to discuss about how uncontrolled nesting in BPF program is causing issues like stack overflow. Roop already discussed that base kernel stack can be bloated, so that he attached a BPF program with all the combining both BPF to BPF calls and tail calls to exhaust the stack. So let's see how we can leverage helper functions and how we can extend that part to overflow the stack. So the point we are making is verifier assumes that the helper calls stack usage is small, and there is a new desire to nest multiple BPF programs is violating these verifier assumptions. So the old way is that in both trace points and kprobes, the nesting is completely restricted. So how they are doing it is they are using a global variable BPF prog active to check whether a BPF program is running on the same CPU. So if a new BPF program which is called inside the same CPU, then it will prevent it from running. So what happens? I want to discuss on what happens if these checks are not implemented in these BPF type programs. So consider a two BPF programs, each has been calling the same helper function. So first BPF program is attached to a kernel function, and the second BPF program is attached to this helper and calling the same helper function. This may cause a recursive loop, and this potentially cause a stack overflow. So obviously the limitations of this approach that kprobes and trace points took is when there is a BPF program which is attached to a helper or a function which is called inside these helper functions, there is a chance that these tracing events might not get triggered. So to overcome these limitations in BPF trampoline type programs, it was implemented that it is implemented to nest multiple BPF programs on the same CPU. It is done by using prog active variable, and And obviously, the limitations of this approach is you can nest multiple BPF program, and if you were able to nest like 33 or more than 33 BPF programs, you will be able to overflow the container stack. This is one of the experiments that we did. We took a kprobe BPF program and attached it to sys socket function, and this kprobe is program is something like what group discussed, which is of 8 kilobytes of which takes 8 kilobytes of stack space combined with all these tail calls and BPF to BPF calls. And there is this another BPF type program called, which is of type fentry, which is also is of size 8 kilobytes and is attached to a helper call which is made inside the first BPF program. And through this, we are able to exhaust the stack. And here is the demo video, which is showing the same, and I'll try to. I don't know. It's not. I'm unable to.
It may not work. I'm not
yeah,
sure. Like
it's
with
not
the BBB
redirecting.
system
I'll
here,
skip that
yeah.
for now. If you guys are interested, you can look through this video in our slides. Yeah. And these are all other potential attach points we have explored. Like you can attach two. Obviously, we can do 2 trampoline type BPF programs, and we can also attach a FNT type BPF program on a trace point, and we can also do an FNT on a kprobe. So if you might be wondering if we were able to, if without using tail calls and BPF to BPF calls, can we exhaust the stack? It's possible just by attaching this helper BPF program. I mean, the second BPF program in the figure. By attaching the same program multiple times, we can exhaust the stack. So here comes. We have defined our 2 problems. So there is we want to discuss on what could be the probable solution and related questions. So the requirements that we define to address these problems are either kernel runtime should be ensured and able to accommodate the stack space required for the BPF program to run, or it should entirely prevent the BPF program from running. The probable solution for the problem 1 that Roop has discussed, where he's able to bloat the entire base kernel stack, is the problem is that BPF program is attached to an unknown stack state. So if we are able to provide a new stack for this BPF program so that this BPF program is able to run on this new stack, so based on memory requirements, this can alleviate the issue that Roop mentioned. And for the second problem, for the uncontrolled nesting, we can extend this stack switching solution, and as the memory is limited, we can pose limits on this number of nesting that we do. And this is a point for discussion. So in both of these cases, as the memory is so limited, if we ask kernel for more stack space, or if you want to nest more BPF programs, there might be a chance that some BPF programs might never get executed. And the open question that we want to pose is what happens if a BPF program never get executed? How does it impact BPF program extensions, which are designed for mostly Linux security modules or the seccomp filters, because the policies that were enforced might not get executed. So other question is, can orchestration tools like BPFD can alert admins to able to monitor these BPF programs and prevent the stack overflows from ever from occurring? So in summary, we discussed how BPF programs interact with kernel stack. Then we showed 2 problems that we encountered. By first one is due to the incorrect assumptions about the availability of stack space for a BPF program to run. And the second one is due to uncontrolled nesting. Finally, we raised discussion points on what could be the probable solution to mitigate these issues. And yeah, and we raised some open questions as well. Thanks. Would like to take questions.
I can ask a question. Did you try to implement the stack switching approach? Like, what would it take to get to this point? And also, like, how do you deal with nesting in that case?
Yeah, we are still working on the solution. We are facing some issues like double fault when there is nesting, so we are still working on the solution.
And then also the follow-up question, but if you're still working on it, like how much overhead would that incur, right, for the execution?
Yeah, we haven't tested that yet. Yeah.
Yes, I guess I was thinking about, you've got like a user space daemon is inserting the BPF program, right? And so maybe one of the semantic questions ends up being, like, is this something that when you're loading the BPF programs, we can somehow calculate what the maximum possible stack would be, and then limit that in some ways so that it can reflect back up? I'm thinking about the last one around alerts.
Yeah, what we want to ask is if a user space daemon able to analyze how much a kernel process can, how much stack space a kernel process can take, and able to assess if this BPF program can overflow the stack, then he can prevent it from being attached in the first place.
Yes, so I guess that has maybe a parallel with the exceptions discussion earlier of like how many guarantees can we provide ahead of time so that at runtime you don't have some sort of breakage of your changes.
I can make a comment on that. So in general, in the kernel, there's absolutely no guarantee that the stack doesn't overflow even without BPF, and they do overflow if you call the functions in the wrong order. If you nest file systems and networking and block devices in the wrong way, then the kernel stack overflows. It happens all the time. It's just we don't talk about it as much. And we only have 8 kilobytes available on 32-bit architectures. So even if BPF, like nested BPF programs can get to 8 kilobytes, you're already toast.
I managed to catch it before it. Yeah, so I think the interesting thing about the BPF in the context of the stack here is that, whereas maybe for the rest of the kernel we can kind of foresee it a little bit more ahead of time, we maybe can do some testing and stuff like that. There's really very little understanding that we may have about what the BPF is going to do on a particular path, right? So to that question that you asked before, it's like, I think that we can know how much, maybe we can do some more static stuff to know about that BPF piece. But the problem is that we don't know about that kernel piece in general, and we don't know either about the helper function piece, really, when it comes down to it. So maybe we could somehow learn a little bit more about the helper functions and how much stack they use. And that would really go a long way to helping to know what this is going to do before we load it. Oh, this is going to be a big throw. Okay.
I might also speak a little bit to that. So on the Cilium project, we use a lot of tail calls, and I don't know how deep they go, but maybe 6 or 8 programs tail calls deep. Could be more. I think we have 20 or 30 programs, but they don't all call sequentially. So like we have like a full CI that we're running through all the different variations, and we're trying to ensure that we're exercising all those code paths. And then we're testing against various kernels so that hopefully on particular kernels we'll be able to detect this. But I don't think we're doing so much on terms of platforms. I guess the problem explodes quite a bit, but I don't see anything fundamentally different in terms of testing from a particular BPF applications perspective around this. I mean, you can still spin things up, run it against a kernel, try things out.
You can take this.
Thank you. So instead of using the BPF tail, what we have done in Meta is like create an orchestration chainer and then use those functions using freplace. So you can load the programs independently and then do the freplace to have the complete tailing of the BPF chainer functions. So that could basically solve the stacking problem.
Maybe one thing that would also be worth looking into, like analyzing the kernel under some workload to see like where are the heavy hitters in terms of kernel stack usage, right? I mean, aside from the 32-bit issue that you have anyway, that you mentioned, but maybe it's also worth to analyze those particular spots, and perhaps they could be refactored differently, or I don't know. I don't know if you did some work.
The main thing we do at the moment is static analysis, where we limit the amount of stack space for any function to between 1 or 2 kilobytes per function, but that of course easily escalates. One thing that I have been thinking about doing is to have more runtime testing where we can mark the stack, part of the stack read-only, so we trap whenever we exceed something like 8 kilobytes or 12 kilobytes of a 64-bit kernel stack, and then print the backtrace to see where exactly we use the most amount of stack in a given system at any given point. And then we can adjust the start of the stack for the kernel to get to a point where we can very exactly see, does anything use more than 11.2 kilobytes of stack? And that gives us some indication. It's still no proof, but it has some way of testing it better than we do at the moment.
Any other questions, comments? Okay, thank you very much. And now we have a lunch break until 2:30.
Dude, this is like the coolest thing ever.
No,
I had never ever seen
Really?
these. It was like literally they're on the thing. I'm like, this is amazing.
Yeah.
I actually have an extra lanyard from a previous conference. Might go up and
Hard. I'm not sure where the other box is at. Could you give me one?
Oh my God. The easiest. One more question. So tomorrow we basically would love to start at 9. So first of all, you would be there as well. Would you be there too?
It will be here at 6 in the morning, so.
You will be here from 6 in the morning. Oh wow. Okay.
We're here at 6 this morning. We'll be here at 6 tomorrow, most likely. Because they're all going to be here at 9, right? Or
Yeah. So tomorrow starts like half an hour earlier, so 9 a.m. Friday again 9:30, so that's fine.
Thursday or Wednesday?
Oh, sorry.
I was like Friday.
Tuesday. Yeah, sorry. Tuesday is like 9. Wednesday is 9:30. So cool, perfect.
And then Wednesday will be done around 3 or still till 6?
6.
Okay.
And today's only one with 6:15ish.
Okay, yeah.
And tomorrow also 6.
6, Wednesday 6 also. I know you like having one of these also, so
sounds good.
I'll put this one here.
Yeah.
Oh, somebody sabotaged me.
All right, so it's 2:30. Welcome back, everyone. While you take a seat, the next session will be by KP about an update on the BPF LSM site.
Hello, everyone. I'm KP. I work for Google. I upstreamed the BPF LSM roughly 2 or 3 years back, or maybe more. It seems like 2, 3 years, but it's actually 4, 5. I want the session to be a little bit more interactive. One of the reasons is I'm doing a demo, right? And the demo is going to fail. So I want you folks to ask questions on why it is failing. My slides are, I'm going to talk about how I tried to write an LSM yesterday with BPF, what challenges I ran into. And I want to discuss with you folks that, do you run into similar challenges and what can we do to improve these? So the end goal is to make the developer experience for writing a BPF LSM better and make this more accessible. So yeah, I picked an LSM. That was the easiest one. I looked through the source code. I was at the airport and I was like, can I do this now? And the simplest of the LSMs that I saw was safe set ID or load pin. And I picked safe set ID because I knew something about it. It was written by Case, and I think I could implement it. And I mean, I was so overconfident that I thought I'll do it in an hour before I board the flight. That didn't happen, by the way. I was still coding it there while we were attending the other talks. So what is the safe set ID LSM? There is in Linux, there is a capability called cap set UID, cap set ID, which allows unprivileged use, which gives the user a capability to switch user IDs, real effective. It's a very simple LSM. It takes like a string. User X is allowed to transition or set UID to user Y. But it can be more simple. It can be more flexible. There was a bunch of bugs that were found in this LSM by Project Zero folks. This is used by Chrome OS. So there was a detailed analysis on how you could break through this LSM. And I wonder if this had been written in BPF back then, these changes to upstream them, the delay that you're involved, like in upstream process, we could have fixed them much faster. So how did my development experience go when I tried to implement this in BPF? I was looking at the code, right? Some part of the code is pretty complicated. It's mostly string parsing in C in the kernel, right? So this is what I said. There is a UID from is allowed to go to UID2. You can also, it allows GID from to set GID to GID2. And I thought, okay, this is pretty simple. I could implement this with a map, like it could be a hash map, which says UID from can set UID to a bunch of other UIDs there. And I will create 2 maps, one for the UID and one for the GID. Seems pretty simple. One int to an array, and that's a hash map. The in-kernel implementation is a bit more involved because the kernel hash map API, it actually buckets it, but it's very, very hard to read to my tired eyes yesterday at the airport. So any issues? Yes, there were a lot of issues. What I would have liked is the inner array to be dynamically sized. And actually, it can be dynamically sized. I saw a patch from Daniel that enabled this. But I tried to set the BPF F no pre-alloc flag, and I got an E inval. Actually, the kernel doesn't tell you why you got the E inval. You just have to guess. And your guess is the mutant, right? You mutated this flag value, and so you try removing the flag, and you see that it's not valid. But in Daniel's patch, you can see that BPF inner map is the flag you're sort of supposed to use. But then when I used BPF tool dump map ID name, it showed a bunch of zeroed out entries. So that, and the problem with zeroed out entries in a map like this is that UID 0 is root, right? So you want to be very careful on where you're using 0 in these maps. Otherwise, you may be setting a policy on the root user. Anyone has any guesses? Like, is this the right thing? Is BPF inner map supposed to give a dynamically sized inner array, or am I doing something wrong? Hint, hint. It's a call out for interaction. Anyone? Daniel?
I think there's a self-test in my patch series, so I'm not 100% sure because it was a few years back, I guess.
Yeah, 2020. Okay. So yeah, I think that maybe BPF tool, when it iterates, the very fact that it is iterating on the max entries, it creates like empty entries inside the map itself with zeros. So this is a hash map with an inner array map.
Kumar?
Yeah.
So if you have an inner array map, then how does no pre-alloc work? Like,
it doesn't work.
Yeah.
It doesn't.
Okay.
That's why I got the E inval.
I see.
But it worked with the F inner map. Daniel's series about the inner array, it actually allows inner array dynamically sized map. There was something about the Cilium load balancer with a lot of extensive memory allocation. And it seemed like a reasonable use case. It's not really relevant. It's the kind of rat holes you can get into while coding stuff like this. So it's 10 array entries somewhere. I can code it. It was fine. Like I initialized -1, which is UID that is irrelevant, like UID false or something, and I solved my bug. So yeah, then I was like, I looked at the LSM code. There were 4 LSM hooks that were there in the, there was a set GID, set UID, there was a cred prepare, and there was another hook. I started writing the code, but I thought maybe if I have my API constant, I could start copying code from there and put it in the program. And surprisingly, most of it worked. This is the peak of like productivity, and then there is there was the decline where I ended up in BPF verify errors, and we needed to grab a ref count. Ref counting is hard. Like we saw a bug, there was Jan posted recently about BPF dpath, and if you try to use an object that you've not grabbed a reference to, it can create these use after free scenarios. And so I realized I knew about that bug. So imagine if I was not aware of the yarn bug and I needed to grab a ref count to the group info structure in some LSM hook, I wouldn't know how to go about it, right? And the goal of is somebody who's watching this video will figure out that, or we will write talks about this, is to send a patch to the kernel that says, hey, there is an acquire release semantics in kernel functions that you can use. And I wrote this quickly, right? I copied some functions from task struct. This is how you should go about it as well. Copy stuff that works in the BPF file. And then, yeah, you can do a acquire release kfuncs to make this happen. But then it still failed. And I was like, what is going on? It turns out that the group info structure that I was getting was from an argument, but I was referencing a BTF pointer. And that is not a trusted argument anymore. So I need to tell the verifier that I trust this argument to be used in a kernel function. So I had to do this. I saw a bunch of other things in the verifier. So this is where I think you need to be a kernel engineer to figure out that this is what I need to change the kernel to enable my sort of unrelated non-kernel use case. So it needs a little bit more knowledge about the BPF internals there. Luckily for this stuff, we had good documentation. Thank you, Kumar. Okay, so, and I think to make this experience better, we'll need a lot more of these acquire release and annotating types as trusted, maybe inline, which of the kernel struct members are trusted so that we could use some of the metadata emitted by Clang or use some annotations there. So one thing that would improve the experience for LSM developers is a lot more of acquire release to really write safe code here. Then this is today morning, right? I built the code I wrote the code initially in the self-test code base in the kernel. I built it, everything worked. So I thought maybe I can go a step further. I will use Andre's lib bootstrap, BPF bootstrap, which is really awesome way to bootstrap your BPF project. Again, for folks who are trying to write BPF code, getting your toolchain and VM Linux and everything in order, this makes it quite easy. So I thought maybe I'll port it to that and I will push it to GitHub, which I did, by the way, at the end. But then I built the same code and the verifier complained of a same code worked in the kernel, didn't work in there. This is where I was like, okay, what is going on? So Florent, who is a colleague of mine at Google, I was sitting next to me, he said, you should try to use the BPF loop iterator there. So I missed the development of the BPF loop iterator, so I figured it out in the kernel. Seems pretty reasonable, right? Like you iterate over the BPF loop values, and you go in the callback, you do your checks, and you return whatever result you want from the context. You can stop iteration from the callback as well. This should have all worked. And then I realized, then Kumar was sitting next to me, and many people have disturbed during the course of this conference, that there was another error showing up. And this time I was getting nervous and more nervous because my demo wouldn't work. That there is a variable offset inside this function that the verifier doesn't like. So the first trick that I saw was that I checked the bounds of I tried to hint the verifier saying that if n groups is greater than max groups, like you return an error. So it means that here there is an upper bound to n groups. It's not such a big number that you have to verify or loop that you have to unroll. It worked 50%. Like sometimes it did and sometimes it did not. I don't know why. But different tool chains here. This worked. This is 100% success rate so far. So what you do is instead of iterating over the dynamic sort of number of groups that you got from a structure, from a BTF type, you iterate over the max possible. And then when it goes above a certain value, you break the iteration of the loop. And then it worked 100%. Any ideas of what's going on here? What am I missing? Is this the right way? Is this the trick that folks have been using for quite some time with BPF loops? Thanks to Kumar for the idea, by the way. Okay. My attempts at interaction fail. So I think this is what for me, then I got the LSM to work, and I'll show you what it looks like right now. So that's the code. These are your maps. So this is the array of UIDs that a particular UID is allowed to switch into.
Could you make it slightly bigger, maybe?
Oh, yeah. Now? More? Okay. So this is an array, right? This is a hash map whose value is this array. So one UID, many UIDs that it can switch into. Similar thing for GIDs. One GID, the GIDs it can set GID to. That's basically the whole policy that is here. Bunch of kernel code copied so that I can use the same APIs from the safe set ID LSM. Let me go to this is the key thing that I had to implement is in a more BPF way is the policy lookup. When an LSM hook set GID, set UID received a particular UID as an input, I need to find out whether it has a policy or not. And to my surprise, when I was working on this previously, we didn't have this helper, but this is very helpful. BPF map for each element. You can iterate through that very sort of a complex map. And then you can just say, oh, I found this UID here, right? I found this policy for this particular UID, and you return the value in the context. So this is typically what you would go about for iteration in maps. And the rest of the code is basically the same as the kernel code that is there in the safe set ID LSM. So this speaks volumes to how good BTF has become, and how the verifier as well, to the correctness, also to the correctness of the kernel code, like pretty nice. And then we go and run this in a VM. How do I do this? See? Knew I would fail. Start a VM. By the way, if you want to see this whole VS Code VM running with a F5 setup, my colleague Florent is doing a talk in the toolchain stuff. You can build a kernel and then run the kernel inside VS Code with this. So shameful plug to Florent's talk. So here we go. We've got the VM running. I can SSH into the VM. Open a bunch of sessions. Okay. So we run our SafeSet ID LSM program.
I think you also need to make it slightly bigger, maybe, if possible.
Okay. So this is not how it is supposed to be. I just picked Andre's bootstrap code, which runs a for loop, but you can pin the policy maps and the policy programs, and then you can quit from here. It's not really needed to keep this program running. It's a question I got often in other forums, that what happens if the BPF program, the thing that loads the BPF program dies? Well, you can pin the maps and pin the programs. Obvious for this room, not obvious for some other audiences. Okay, bigger. Okay. So then we do this. We go and we So this is a file that has a capability set. There is a system in Linux called file. You can set special capabilities to binaries. This file has can elevate to cap set UID. So this is something that I've already done, and this then raises cap set UID, and then it tries to switch to another user. The user ID for Bob is 1003, right? And it is trying to switch to user ID 1002. If you see the crux of the policy that I implemented here, it's a very, that's 1003 is the policy for Bob, and 1003 is allowed to, this is why I think it would have been nice to have dynamic initializations of the array type in the BPF program itself. Otherwise, you have to do this. That's something that I did here, is it's only allowed to switch set UID to user ID 1001. And I'm trying to set UID to 1002. So this should fail if my demo works. So I run this binary. It was killed. And if I see cat, and if you see there, this is the UID transition was blocked. This is basically what cap set UID LSM does, and we could implement it totally in BPF. Few things that worth calling out here, very nice to have, was the BPF send signal command. We implemented it because I think there was Tetragon uses it, but it's very useful to have. I think kernel LSMs use it as well. So yeah, that's my experience of implementing a BPF LSM, BPF-based LSM in a day that is an entry LSM. It works. But but there are definitely gaps that we need to address here. The discoverability of what you do when you have a particular error is a common theme across all BPF development. What do I do with this E22, right? For the K-funks, how do we tell people that this is how you would go about implementing a K-funk, or how would you request a particular K-funk for acquire release to be added? So we need to do something here. It'll graduate towards a period of time. Over a period of time, it'll go there where we'll have most kernel objects with acquire release semantics. But until then, it'll be a bit of a rocky road. I think this was pretty cool from Frederick from Cloudflare. The user namespace create hook. I think there has been a long-standing debate on how policies should be implemented there, with multiple things being shot down, a sysctl like that disables unprivileged user namespace creation. And here we have an LSM hook, right? That is there for you to plug in, and you can implement your BPF program and implement your policy whichever way you want. Simple things that have triggered debate are now
very solvable in a very pluggable way. So thank you for that. Another simple thing that people haven't really agreed on in the past is, what is a container? Well, don't care, right? Define what your container is in your BPF. In something that is similar here, we use it at in our own internal container framework, right? You have your container manager, which starts your container thread. When it forks, you can set blobs on whatever definition of your container is. Generate a unique container ID based on whatever namespaces you think a container should have, or a UUID, whatever. And then you pass on this blob across the whole process hierarchy. You can also pass your policy there. You can say that I want to enforce that this process tree will never exec. Very silly policy to have, but you can enforce that. So you can encode your policy from your container spec into the actual container workload and pass it through the process hierarchy. You can say, I want all executions in this container to be audited, right? I want to get audit logs. And then your BPF programs will check, hey, what policy do I have? Do I need to audit it? Okay, I'll send the audit logs back somewhere. So you can build the configuration there and pass it through to BPF. Another sort of something that was blocking in the in how do we restrict file systems? Complicated discussion to have in kernel land, easy thing to implement with the BPF LSM. This is actually what systemd does with the BPF LSM on right now. If you want to restrict certain file systems, you can just write this restrict file systems equal to ext4 and tempfs, and you will not be allowed to create any other file systems apart from these. Very simple, and it's basically got a map of like magic numbers that you're allowed to have for the file systems. So one thing I don't know whether this actively discourages developers from building BPF LSMs, but at least it actively discourages it from being enabled in the distros by default. And in Ubuntu, for example, I don't know, but when I sent the patches, I said we can have this compiled in, but somebody will need to go into the command line and say, enable BPF LSM there. And if we have these patches merged, which is the last iteration that I sent out on Friday, it is really there, right? There is all the feedback has been addressed. But just to give you a summary on why this overhead is, why does it exist? Why is it relevant, right? And if you care about this and have access to the kernel mailing list, please reply so that Paul Moore, hi Paul, you can merge it. So the issue in the kernel currently now is LSM callbacks are indirect function calls. There's so many conferences I've said this in, but I'll repeat this again. Indirect function calls are susceptible to a CPU vulnerability called branch target injection. Very complicated stuff to explain in detail, but basically there was a bug called Spectre v2, and these indirect function calls were replaced by a complicated hack called, or a mitigation, I would say, called red pollines. The red pollines are each indirect function call goes to a sequence of instructions at one point in the kernel that basically flushes the branch predictor. And I'll show you what the impact of this is on performance numbers, but it is significant. And if you think these LSM hooks are basically everywhere in the kernel, when you send a packet, there is this red polline call. We don't want red pollines. We don't want to flush the predictor when there is a socket send message. So it's not just BPF LSM that is going to benefit with this. All LSMs are going to benefit. There was a mitigation from the CPU vendors. They added this something called eIBRS, where the CPU is seemingly not susceptible to branch target injection. But then there was another class of speculative attacks called the branch history injection, which is relying on a different microarchitectural buffer called branch history buffer. And the recommended mitigation even on a modern CPU is to enable both eIBRS for branch target injection and red pollines for branch history injection. So it will still be slow on newer CPUs. So the solution, it's a simple one. We know the list of LSMs at boot time. We don't know them before boot time, but we know them after boot. So we go, instead of creating these indirect calls, we go to the kernel and patch them back in.
We say slot 1, SE Linux, slot 2, AppArmor, slot 3, BPF, right? And that's it. We create these empty slots and we patch in the LSMs there at the early boot time. Once you know the address, it's not an indirect function call. It's a direct jump to a function. No fancy branch predictors involved here. So the impact here is pretty significant, as you can see. I did a little perf command, right? You have a lot more branch misses without these patches. And you have this as the impact of this. So pipe throughput, this is from Sysbench, improves by 10%. But this is with BPF and SE Linux enabled. If you don't have any LSM enabled, of course, you will not have any benefit. But if you have something enabled, then you will have these benefits. And you have positive impact on syscall overhead. Yeah, I made this slide specifically for Paul Moore, who's the maintainer of SE Linux. I'm giving you context, but can you guess what this number is? Don't hold me to this number. It is something that arbitrary came up, but to convey a point. Any guesses? No, I wish. I wouldn't be here if it was that. It's roughly how many branch prediction misses are happening across all Android phones that enable SE Linux in a given minute. So these are how many times a CPU is stalling. Although, these Android phones are likely not compiled with Red Pooleen, so I go back on that point. But yeah. But yes, there is so much energy that is wasted in just these Red Pooleens that we could easily fix with the static call patches. So we'll have this merge soon, and then you can try out the BPF LSM on Ubuntu as well. Any questions? I can see, yes, actually, it has got a spinner. So if you can read the question for me, I'll just go there.
The question was basically what toolchain you used where you had those failures 50% of the time earlier.
So first toolchain I used was from the self-test, right? When I wrote the program in the self-test code, it worked. When I wrote the program in the libbpf bootstrap toolchain environment, still should use my Clang, right, that I've built, and the Clang is Clang 18 for the system. I rebuilt Clang from their daily build yesterday morning. So yeah, it was Clang 18 Pahol 1.25.
I have another question. Can you also elaborate some more on another patch set, like the extended attributes? What's the current state? What's blocking? And what are the next steps?
So that I came up with, I think Song has taken forward with that work. I think what you suggested latest is it should work. We just need to be careful on the re-entrant stuff. But if you limit them to LSM hooks and to a certain, I think Christian is here. Christian had a bunch of feedback last time. We couldn't go the old plumber style where we have a discussion. So you remember we tried to get the extended attributes from BPF. And there were concerns about POSIX ACLs and these overlay systems. Would it be okay for FS folks that we just limit these to LSM hooks and the user dot xadder namespace?
If you restrict the xadder names, thank you. If you restrict the xadder namespaces, it should probably be fine.
Okay.
So the concern was for the audience basically is that you, for POSIX ACLs and for some others, for FS caps, you store UIDs and GIDs on disk, and you need a lot of context to translate them correctly, so you don't end up producing set UID binaries, for example, on accident. But if you restrict them, yeah, sure, to security dot, what is it, BPF?
Security dot, we are thinking security dot and user dot.
Sure.
Okay. Hey, feedback. Cool. Thank you for even explaining the background context. I should have done it. Thanks, Christian. So okay, I'll just go back to the other patch set on why we are doing this. Extended attributes are required for persistent policy state. The sort of natural transition from a kernel object is for a process to be executed, it's a file, right? If you can store the policy with the file, then you can, as the file transitions to being a process, you can translate that extended attribute to security policy information. Typically what LSMs do, other LSMs can do this. In BPF, you can't, right? And so if you can store this policy information in the extended attribute, you can have persistent policy across reboots. At least one of the use cases. Other use cases is you can do signature verification with FS Verity as Song implemented. Any other questions?
Okay, thank you very much.
Thank you.
Okay, so let's get started. My name is Song Liu, and this is Boris. We both work for Meta, and today we're going to share our idea to use BPF LSM and FS Verity for binary authorizations. So what we do with the binary authorization, basically, we say we want to make sure only trusted binary can perform certain critical operations, like access certain device, access certain file, open certain port. And so here are some requirements we want to enforce here. First, we want to verify the hash. We want to say, okay, this is the binary we built, and versus traditionally there are solutions, we will just verify the path. But without verifying the hash, there's no way you know the binary is actually the one you trust. And we want to build a set of flexible policies, and because access pattern will be different. For example, we have we want to verify, okay, only verified or signed BPF trace binary can open a signed BPF trace script. And we need to be able to have a policy that describes this restriction. And we want to upload the allow list and maybe a block list at the runtime, so that the primary use case is we don't want to reboot the server. We will just want to update as we release new binaries. And next, we want a smaller attack surface, and which means we just mentioned allow list and the block list, and we need to update that at runtime. We don't want to be required to protect the allow list. So if the hacker has certain permission to attack the allow list, it breaks the protection. For that, we think we need to get asymmetric keys. Basically, you have the private key only available at the trusted building systems. And then you only deliver the signed public, the signature to the servers that's running it. So you don't really have to protect the allow list. Okay, so now existing solutions, we found two things that are similar to what we are proposing. One is IMA, or people call it IMA. Basically, we found this very complicated, sophisticated systems, and it seems to not designed for the use case we are targeting. And also, we found EMA is not flexible enough. There are cases you need to have a trusted boot, have a secure boot, then you have a trusted boot. It's just, you need to switch your behavior with a reboot, which is it's not possible for our use cases. And another thing is like the FS variety itself have a built-in signature features. And what this does, like if you have this binary, is you want it signed, you attach a signature. And if someone accidentally modified the file, either by like writing to it or maybe bypass it directly to the block device, and you will know that. And the problem with this built-in signature is like it's not protecting the file metadata, which means if you remove the file and place another file with the same name in the same location, you will lose the protection. And naturally, the kernel will think, oh, this is not a protected file. You can just do whatever you want. So, and now I'll hand to Boris to talk about the FS variety.
Yeah, so just a little background, since I assume most people don't know what this is offhand. FS Verity is a generic layer inside the VFS that provides this kind of efficient hashing for files. And the sort of trade-offs or designs that it chooses is that the file has to be read-only. In fact, enabling Verity on it forces it read-only. But what you get for that is it uses a Merkle tree, as I'll explain on the next slide. So it makes retrieving that whole file hash order 1, and you detect the case Song was talking about, where if somebody tampers with the block device on purpose or an accident, on purpose only if you protect it with signatures, you can detect that at the time that you actually read from the block device. So when the file system really reads a page, that's when the FS Verity layer does the tree-based hashing, and you'd have a read failure versus the normal kind of pattern, which I think is actually easier to see if this picture is here, where like when you open a file, you can read the whole file and get a hash. That is fine, it works really well. I'm used to only support this format, but there are many files where you don't actually ever read the whole file. And so by hashing it in this way, you're like doing a lot of pointless IO that you never would have done, versus FS Verity, by using a Merkle tree, kind of turns that hashing lazy. And on the upside is it's usually a lot faster. The downside is you kind of have to be able to handle a random read failing. So if it's like a binary executing, it'll get SIG-bus, for example. But yeah, so Verity is kind of powerful, and then it lets you do all this stuff, and it's fast and secure or whatever. But as Song explained, with the built-in signature shortcomings, there's kind of hard to actually use. Like there's no apparent immediate use case for it. Like you can get these super fast hashes, but they don't hook into anything useful. But IMA added support for it, I think last year. That's kind of a good first step. And this is our project is kind of like another way to hook into it. So if BPF can use Verity sort of like as a library to do these efficient hashes, it can then do something sensible with it, which I think Song will continue with here.
Okay, so this is our proposed framework. Basically, we use FS Verity just to get efficient the checksum or the integrity checksum of the file. And we have like the security, like a binary signing service running with dedicated like servers, maybe with dedicated hardware, maybe a TPM to provide to store your private key. And that's where we sign the FS Verity digest. The digest is another way to say the checksum. And we use XTAR to store the FS Verity root hash signature. Basically, we sign the digest, and then we get the signature. We store it with XTARs. And then we use BPF LSM to enforce access control. And for that, we usually have a user space daemon to manage the key rings and load the BPF program, and maybe we update the allow list of like signatures that allow to do certain operations. Is this too small? Probably okay. So here's an example, and we hook to this BPF LSM hook that basically you have access to this file, and that's the last place basically you run when you execute a new binary. And as far as I can tell, it's like there's no return from there. So basically, you set the binary, you get a new binary, you set your you're allowed, if you're allowed, you're okay. If you're allowed to accept, but you failed afterwards, there's no return, so you are not leaking the credential to the caller. So basically what we do in there is like we get current task, and we get from the file, we get the digest, that's your FS variety checksum, and you get the xtar from the file. Basically, that's the signature, and you verify that against your keyring. If the return is non-zero, you just keep going, you don't do anything. But if the return zero, meaning there's a match, your signature matches your binary, and we set this allow list is a task local storage. Basically, it's say, okay, this task, we add that to the allow list. And now when this binary want to open something, or any binary want to open something, we see whether this file is a critical file that we need to protect. If not, we're good. If it's something we need to protect, we look up the same allow list, which is the task local storage map. And if we get any value, we return 0. This access is allowed. Otherwise, we return 1, and this operation can be blocked.
There's a comment in the chat. So John says, on all the kernels, we did some pointer chasing and found the hashes. It worked okay, but kfunc is nicer to have a kfunc for it. And the other question is, does this handle overlay file systems? The approach that you have shown in the example.
So I think there are two parts of it, and we need the file system to support FS variety, which I don't know whether overlay as FS automatically support if the underlier file system support it, and that I don't know. And then if that's there is a support, whether they're going to cause some issue, I don't know either. Okay, I'll talk about what I know. So basically, here's the new kfunc we want to introduce. Basically, it has just to access the FS variety digest. And from previous feedback from when we get this new kfuncs, we see like we want to avoid any possible recursion when you call this and trigger another like a BPF program. And so we have the limitation of restrict this to only BPF only LSM hooks. And as far as I can tell, it's like all the LSM hooks are designed that they don't like a recurse into each other. And we also have the restriction with this KF trusted args, meaning we cannot do arbitrary like argument walk. And if you go back to the example, we need this F from here. If you get this F from like working on inode or working the entry or working maybe this like a bin program pointer, that won't work. So you need, from what I see, this is probably only good hook to apply this this case. Okay, the next kfunc, we're talking about the BPF get f x star. And thanks KP for saving this to us. We were thinking to cover that in the previous one. But basically we do that and we get the file and with the name and the dynamic dim pointer for the value. And similarly, we limited this to LSM hook only, so to avoid recursion and avoid deadlocks. And same no pointer walking, so only certain hooks we can do that. And right now, we think for our case, we only need access to this user.xstars. And the reason is like we don't need like a control like who gonna write it because it's like a asymmetric key. We just need a allow list. And of course, if in the future we have special cases, we're going to introduce the security BPF namespace, which will require each maybe each FS to have a little bit of support in this, but that should be trivial change to the file systems. And this is the latest patch set we have, which was sent like a little more than a week ago. And that's all we have. Questions?
Any comments, questions? John, do you want to talk about what you wrote here in the chat?
Sure. Can you hear me? Am I like through the speakers?
Yeah,
in
we
the
can
roof?
hear you. We can
Cool. Yeah, all I was just saying is we used FS Verity with some Kubernetes deployments, and Kubernetes relies heavily on overlay FS. And hopefully I get all the details right. It's been a year or two since we've done this, but the basic trouble was that in the overlay FS, the overlay files can be changed, and it doesn't cause the underlying file system FS Verity kind of infrastructure to be kicked. And the result is you can basically have overlays and underlays with different signatures, was kind of the gist. So unless you are very careful to manage all this with BPF through like file monitoring and integrity checks and all kinds of other stuff that we had to put in place, it sort of doesn't work out of the box with the overlay FS. I think it's more of an FS Verity concern directly, but maybe there's a play for BPF. Like I said, we managed to get BPF to kind of monitor both the overlay and the underlay, which was useful. So maybe there's something there, and maybe somebody in the audience has a FS Verity and overlay FS knowledge that maybe it's not the same as it was a couple years ago when I looked at it. So
I'm talking a little off the cuff here, but it sounds like overlay could also check if I might be getting this backwards, if like the lower file has Verity enabled. Like the file systems that support Verity, when they open a file, they check is Verity on for this file via the VFS. So if overlay did that, it could then know that the file is read-only and it should disallow writing to it, like in the upper. Or again, I'm sorry if I got upper and lower backwards.
no, yeah, that makes sense to me. That was sort of my guess as well. I just think nobody's gone through the work to make it kind of operate sort of intuitively, or how people would, or at least how I would have expected it to work.
That makes sense.
And maybe I'll just add, I think the file system people have some reason that it's not as simple as it sounds. Because I remember broaching the subject, I think in an LPC or somewhere with the file system folks, and they had a list of reasons why it was a little bit tricky to implement, but I've sort of completely forgot what that list is.
I can look into it and get back to you.
Oh, that'd be great.
Thanks, John.
Have you
been thinking at all about how to make use of this sort of functionality when looking at scripting languages, where the interpreter may have stuff associated with it, but there's no clear delineation between code and data that it's opening?
I think you had something for BPF trace. That was like kind of one of your ideas, right?
Yeah, we mentioned that we can sign the file as just the binary, but actually you can also sign the data file. And for like we have, in this example, we have two hooks. We have just the two hooks. You can have like one hook for when you run the binary. You have one like tag say, okay, this is trusted binary. And for when you open the file, that you can say, okay, this is opening a trusted script file. And for that, we may need a little bit more details because like your binary may open different files and you care about the script you're about to run. So I think with some details like sorted out, this is possible to achieve that you only allow signed binary to run signed script. And if either of them is not signed, you can block it. And I haven't get exactly a demo of that, but I feel that's very, very possible.
Thanks.
So you showed the case where you cannot walk pointers with the KF trusted args. Like you had a slide after this one. Yeah. So there's an example that KP showed where you can annotate a structure and basically mark that if you walk a trusted pointer and you like load that field, then it can also inherit the trusted flag. So then you can basically mark the file struct file inside the inode as trusted, and then you can load inode dereference file and then pass it to your helper.
Yeah, thanks for the tip. Yeah. I didn't know, I didn't play with that one. But I think the other side is like we can want to make this extremely safe. And of course, that's a good solution if we know at this hook point, this file structure is always valid. And so we needed to make sure that is the case. But yeah, that's a good solution in case we have to. Thanks.
Any more comments, questions? We still have some time. Okay, thank you very much. Yeah, you can also use the mouse, and then you need to click here. I think the arrows, they don't really work, because then they get you into this field. Something to be aware of. So mic is on, and then maybe a couple minutes.
All right. So our next session is from Liam and Shankaran on sysarmor.
I'm Shankaran, and this is Liam. So we work on platform security at Meta. So today we are going to talk about sysarmor. It's an eBPF-based intrusion detection and prevention tool. So the agenda for the today's talk is, so today I'll go over the problem statement, and then we'll talk about sysarmor and the features it provides. And then we'll go into some of the interesting use cases we had and some of the challenges we faced along the way. So at Meta, where we connect billions of users every day, so the risk of cyber threat is really high. So without a strong intrusion detection and prevention solution, Meta's network and host could easily be attacked and leading to unauthorized access, data leaks, and system breakdowns. So in the past, we used SE Linux and OS Query for intrusion detection and prevention, but with performance issues, we could not able to enable SE Linux everywhere in our production environments. And OS Query is a snapshot-based system, so it lacks some of the prevention capabilities what we are looking for. So the main problem here is how do we detect and stop these advanced cyber threats in real time with low performance hit and scale it. So we ended up building sysarmor. So sysarmor is our intrusion detection and prevention tool built using eBPF. Primarily, we use like LSM BPF for enforcement. The main difference between sysarmor and similar open source tools are sysarmor evaluates its rules and policies in the BPF code, and it's optimized for high performance. So we use meter attack framework for additional coverage, and then we have currently more than 50 plus BPF hooks. As I mentioned, the rule execution happens inside BPF code, and it's highly configurable. So you can actually enable or disable detections based on different infrastructures. And we use like BPF LSM for mandatory access controls. So the detection coverage, so this is not an exhaustive list, but primarily we have coverage for like hardware networking, system calls, privilege escalations, file monitoring, access controls, task and process monitoring, and so on. And similarly for prevention, we have like network access protection, file operations, unauthorized privilege escalations, so unauthorized kernel modules, BPF, and so on. So we also support a response remediation flow. So we have our detection events flow into an offline pipeline. So we can write like automated detections or remediations based on those detections. And we have our incident response team who can actually trigger manual remediation step. So some of the things what we support right now are like file acquisition, like endpoint actions, network block, and process stop, and memory collection, and so on. So now, so this is one of our interesting like prevention use cases. So we wanted to provide like access control for our data disks that stores like really sensitive data. So the requirements looks like this. So access is restricted by default. Only allowed process will have access to these disks. And so one of the interesting requirement here is like any processes or any tools that these allowed processes invoke will also inherit the same policy. And again, it wants option to configure these policies using kernel device numbers, magic numbers, or like file or directory path. A very straightforward approach would be like write a LSM file open hook, and then you actually look for either the kernel device number or file path, and then you look at the process to see if the process is allowed. And then you have to walk through the parent to see if any of the parents are allowed in the list. But the problem with this, since this is a storage cluster, so we cannot pass through the tree every time when a file open happens. So what we ended up doing is we ended up having like 4 LSM hooks to solve this problem. And we have a task iterator that runs at the start of the process. So it will actually look for each and every process in the task and then see if it allows a policy. So it actually uses task locus storage to record that information. And then we have like for task alloc and exe creation, when this event occurs, we actually look for the task locus storage, and then if there is any parent information allow, then we copy it over. And then when the actual file open happens, then the policy becomes pretty straightforward. So we either we look for the process, and if it is allowed, we look for the task storage for additional information, and then we enforce the policy. So this is how exactly the code looks like for one of these iterators and the task alloc. I'll hand it over to Liam for covering detection and the use cases.
All right, thanks, Shankran. Yeah, so Shankran shared a prevention that we have with SysArmor, but a lot of what we do is collect signal to drive alerts and then response from a response team. So, you know, a detection is usually one or more BPF probes that, you know, contains logic to filter the data that it's collecting. So, you know, if you're looking at, say, the set UID system call, it's called pretty much constantly on any system. And you want to filter out all of those calls that are benign. So we use various criteria. So a simple one is process name. We've abandoned using process name pretty much because it's insecure. A process can easily change its name to something new. And we've settled on using, where possible, the process binary path. So we actually extract from the struct path the binary path. We catch that string in a map so that we don't have to look it up every time for the same process. And we use that as a, you know, for example, bash is allowed to do certain things, sudo is allowed to do certain things, that kind of thing. We also use container information. So we actually extract metadata from running containers and inject that into BPF, into kernel space, and can use that to make different filtering rules. And then just things that you'd expect, you know, for networking, IP address and port, for set UID, you know, the UID or GID being used. Calling set UID to nobody is fine, whereas calling set UID to root is maybe not fine. Once we have that data, we filtered it, we then enrich it. So we add, if we can grab the information for the container that contains the task, and I'll talk about how we do that a little bit later. We'll tag the event with that data. We also tag it with data about, like, if there's a relevant SSH session, I'll talk about that later too, and give this enriched data to user space that can then be used to generate a high quality event that the response team can take and actually, you know, hopefully do something with. Okay. So yeah, as Shankran mentioned, one of the big things for us is performance. So we want these probes to have minimal impact on the system. And in fact, the systems we run on, generally the owners will push back on us if we use too many resources. So we have tools that automatically track BPF memory and CPU utilization at Meta. But we also wrote our own tools to track simply like the elapsed time of every BPF program. So we record its start and end time, and then record the delta in a map for later analysis. And then we can automatically make decisions based on, you know, how much CPU time a given program is using, or how many times it's been called in the last minute, 10 minutes, whatever. As for like CPU utilization of user space, it's generally extremely low because we're doing as much work as we can in BPF. We're offloading everything we can into BPF. So one of these use cases is tracking TCP sockets. So we're very concerned about processes spawning sockets that are not authorized. So bind and connect in particular. So, you know, basically incoming and outgoing connections. We use for bind, we use a K-probe on the security socket open call. The reason we don't use LSM right now is because we haven't rolled out the LSM flag on all of our hosts yet, but we will soon. And for connect, we use the cgroup connect call, which allows us to actually disable some connects if we wanted to. And then we also look at the accept call on certain hosts. So accept at meta scale is called an inordinate amount of times. So on many tiers, we don't look at accept, we just look at bind. But we, on some tiers where it's called less often, we look at it, and that gives us an idea of what sessions are being opened. In particular, we're looking for sessions, to and from suspicious places with accept. So we also look at UDP. We look at UDP send message and receive message via the UDP send message and receive message hooks, or functions rather. We K-probe them. We just do a pretty simple thing. We use a map to store the outbound or remote IP address and port. And if you see, so the first time you see a packet going to that place, you log it. The second and nth time, you just ignore it. And then we clear that map periodically. So that keeps this relatively performant without, while giving us the data we want, which is, where is this data going to? So one thing that we're of course very concerned with is the activity of users in interactive sessions. So we uprobe bash. There's a well-known bash readline function that returns the contents of a command that you type into bash, and it's only called when the command is interactive. It's not called for scripts. So this actually has really good performance because it's a probe that only fires when a bash command is entered. It's fired at no other time versus other ways of getting this kind of data. But there's a problem with this. The problem is that you have to do a uprobe, you have to know where bash is, and you have to actually probe it. If you're running a containerized workload, every container will have its own copy of bash. So how do you find all of the bashes everywhere on the host, right? The simple way is to simply know roughly where they are and use various globbing or regexes to find where the bash is. But you actually don't always know that. It depends on how your container engine works. So what we actually do is we run a BPF iterator, a task iterator, that scans all the tasks on the host and looks for tasks where UPID is 1, aka it's a init process of a PID namespace. So that's actually now, once you grab that and you grab its real PID, you have the PIDs of every init process of every container on the host, and also generally systemd of your own, the actual host. And then you can just use /proc to actually find the root of every container, and from there you can find where bash is. Pretty straightforward. So so that's what we do and then we probe every single bash, and now you have data from every container if someone uses bash on the container. So why do we care so much about bash? What if someone uses another shell? Well, if your default shell is bash, generally shell code, when executed, will go after the default shell and will then trigger your bash. And that's part of what we're concerned about. We can actually look at the parent process of the bash command to say, oh, well, that's a suspicious process, right? Like if the parent's SSH, you expect that. That's normal. If it's something else, then maybe that's an exploit in process. So I mentioned that we enrich these events with more data. So we can actually tag an event with what SSH session is responsible for it. So we probe set UID. We originally used a uprobe, but we had trouble with keeping track of the right symbols in the binary because the packaging team kept stripping symbols out that we were using. So we went with set UID. SSH, when it forks and spawns a new session, it calls set UID exactly one time. So this was nice. You now have a probe that fires on, SSH spawning a new session. And we record the PID of that new session. Now, when SSH spawns a new session, it also creates a log message that logs the PID of that session and a bunch of information we want, like the user ID, the key that was used, all this stuff that would identify who's doing something on the box, right? So we then save that SSH PID to a map that we keep, a metadata map that is various process metadata stored PID to this metadata. And what we do with that map is we actually have various probes to inherit that metadata. So on a fork or an exec, that metadata is actually copied to the new process or copied to the PID of the new process. And what that means is that every child of that SSH session has this metadata that we can then query and get out the original SSH PID of the, maybe it's the father, maybe it's the grandfather, whatever. And we can use that to look up in just a normal C++ map the key, the username, all this stuff that really can't really be faked very well. And this is, we can enrich any type of event with this data. So if it's a network bind, or if it's a bash command, or a call to become root, any of that is all enriched with this SSH information. So another problem for us is Python scripts and scripts in general. Because in BPF, you don't see the name of the script when it's run, you just see Python, right? If you get the process name, it's just Python a lot of the time. Or if you try to get the binary, right, it's just Python. So what we did is we uprobed the Python function that is responsible for loading a script. And so every time a script is run, this fires, and we get actually the path to the script. So there's a couple things we do with this data. The simplest one is we just log it. And then we have a table, and the table tells us, oh, here's all of the scripts that are on your host that are running, which is surprisingly informative. But the second thing we do, oh, question? Yeah, go ahead.
How do you uprobe? Like, is there just one Python binary present there, or how would if I drop another Python binary on the system?
Yeah, it's a good question. So I don't have any creative solution like I did for Bash. We know where the Python that they are instructed to use is, and there's multiple versions, and we just probe all of them, right? Of all the lib Pythons that are in, user lib or wherever we can find them. But if someone were to like maliciously put another Python, we don't currently have a way to find that. Yeah, you want to?
So then what do you do when you have path hijacking, right? Because like you're basically depending on the combination of the known location of the binary plus your expectation that a function name is going to exist. But those are really easy to impersonate. So how do you deal with that?
So that's a great question. So in general with paths, the presentation that went right before me is our solution to 90% of the path issues, which is to rely exclusively on signed binaries for doing these rules, right? So right now our rules are path-based, and we want to change that so that it is based on a binary signature. As far as I think your question specifically here is that could someone trick me into uprobing the wrong file? They would probably have needed to compromise a bunch of other stuff in order to do that, is my thought. But yeah, I mean, sure, they probably could.
My thought here is that if I'm thinking of sysarmor standalone, it's a lot easier to do that than if you're, you mentioned you have all these other pieces in play that you're using with this, but if I take sysarmor standalone, it seems like it'd be really easy to like screw that up.
Yeah, I mean, uprobes are interesting because yeah, they have a lot of they're just limited. One thought that comes to mind as we discuss this is that if we eventually move to this model where all of the binaries on our host are signed, then maybe I know where everything is because of that service, right? And then maybe, obviously an illegitimate copy would be not allowed to run, and a legitimate copy would not be able to go on the host without us knowing where it is. That's my that's my first pass at as a solution. But you're right, it's a very hard problem.
So I think what you folks are doing with the execution provenance stuff and execution integrity with what Song, the work that he's doing, I think that would alleviate some of the issues. You can transition from the policy like a signature-based verification and then have your policy in the exciter itself, right? Then you know that this is coming from Python. This is coming from a verified Python. You don't need to change that. And you can have some custom handlers that are shipped as a part of that executable. Maybe uprobe, maybe something else, right? Maybe something that can orchestrate and send it back to the same logging ring buffer source that you have. So
yeah, absolutely.
I think the key here is that at least, with those other ideas that you can make this stronger. I think the big weakness, I think, if you want to take this kind of the next level, is to figure out how to not rely on file paths for your trust or your policy management or any of those other things. Because like, it is entirely possible and reasonable to expect a Python binary or some other binary that has an embedded Python interpreter to exist anywhere arbitrarily on the system, and you don't necessarily know what it is. But you do know that if your signatures are trusted, or if you have the checksums or the digest or some other like secondary mechanism, whether it's trustful or distrusted, and that's the sort of thing that I think would make, you're kind of inching towards this. And I think that would actually be a good next step towards like closing a lot of these holes that you'd have with sysarmor standalone.
Yeah, no, I absolutely agree with you, and that is 100% where we're going. Is paths are the best thing that we could get working on our own, and then with Song's help and other resources, we're going to be able to do a lot more. So I just have a few things left. Okay, so yeah, one use case that came up was container escapes. So a very common way of escaping a container, it's really a whole family, is to abuse the file system in some way, whether it's to mount the root file system or to use like special files and /proc. Files are a problem. So what we did was first we had to figure out how to track container creation and like inject container information to BPF, so we know what process is the member of what container. So we track container creation with by kprobing the create new namespaces function, and that kprobe sends an event to user space every time a new mount namespace is created. And we chose mount just because we're doing files, so it seemed reasonable to choose mount. We then query. We know when the container was made, so we can then query the container engine to get the container metadata out for that container. We then put that metadata into a map that's indexed by namespace ID. So now, whenever you have a process, you can look up its mount namespace ID, and you know what container, like all the container information for that in BPF. So then we have a kprobe on security file open. When a process opens a file, we look it up its container information. Currently we're using container username because all these containers are created by like the same user, so this was the best field for us. We use that username as a key in a second map, which contains the allow list of all the files allowed to be opened by that container. So we can then check the file against all the allowed files. It's files and directories actually, so it can be inside a directory, and that's allowed. We do that check, and then we know if someone is accessing a file that's highly abnormal for that container.
So how would you think about this in the context of like instantiating a container with a dynamic user context? Because like, for example, in Podman or in some Kubernetes deployments like OpenShift, OKD, whatever, what they do is that when they instantiate the container environment, they generate a random UID, GID, and essentially apply it to the execution context. So how would you adjust this to be able to handle that kind of thing? Because that's even starting to trickle down into nspawn and other things.
Well, if it's a random UID and GID, that should be fine because we're using namespace ID, right? So, I think unless they're spawning, the only thing that would trip this up would be if they start spawning like multiple namespaces for the same container, and then there would be adjustments you can make to accommodate for that.
I think the map that you just said, with which you have the user ID map, and you look it up in a second map. The first map seems to be to me like a task local storage blob. That's the information about what process belongs to what container. You can just pass on that information on task alloc, right? And pass on that blob. What worries me is the file path usage here again, right? Like you could that is maybe extended attribute based or some allow listing based would be better. Again,
yeah, I think this is the reason SE Linux uses Zatters, because of this problem.
Yeah, no, that's a good point. All right, I'm gonna keep moving for now, but we should discuss probably. But yeah, we could do that. And this was This was really phase one of trying to lock down this problem and address some specific issues we had. Okay, so yeah, I just wanted to bring up some of the challenges we've run into and kind of, what our solutions have been. The big one is identifying a service. So this seems like it should be easy, but it's actually incredibly difficult to do 100% of the time. So, some services run as just processes or families of processes. And, you have limited metadata available to you as a BPF program. Even getting the file path or the binary path is actually quite difficult and quite performance. It's a huge performance hit. We actually catch the file path in a map of PID to, various metadata in order to, and yeah, that could be task local storage as well. But we catch that because it's expensive. This is why the previous talk was really important, was because if we move to binary signatures, we actually have a way to identify the majority of these services. But some services are containers, and they run, one thing or many things inside the container. It's maybe not just one process. So, how do you identify that? C group is difficult to parse in BPF. A lot of times, like the container engine will inject UUIDs into it, which makes it pretty much useless to you, since you can't deal with random information really at all. Again, you have namespace ID, which on its own is pretty much completely meaningless, which is why we had to create several hooks to just inject information into the kernel to use namespace ID.
Just to that point about making it, because it's hard. I think you need the container manager and the container control plane to be on your side. Otherwise, you will be reverse engineering their implementation in BPF, which is hard. So let's say you have Podman or Docker, you need the blob to be set from the user space and have that information generated from there. And then you maintain the mapping.
They need to be part of the story.
Yeah.
Yeah. Yeah.
So what you're trying to do here, you're trying to design an LSM. And for that, LSMs have been using the labels. So
yeah.
What you will need here is so if you go full path, like what KP has been proposing and so on, so you will soon end up with a need of proper policies, the labels, and basically going towards a proper LSM to be foolproof.
Mm-hmm.
Because as you said, some things you might want to label inside of one container running under the same label. Some things you might want to split and, based on your use cases, deployments, and so on. So I think you're here really on the path to full LSM. So you should be looking more how LSMs are looking, kind of solving this and just implementing it in your framework.
Yeah. Okay. Yeah. Thank you.
Thank you. So Tupperware agent does provide the cgroup ID. I think you should be utilizing the cgroup ID so that you can track all the processes under the container and can map it with whatever reasons you want to map it. All network policies, what we implemented today, right? Like eBPF, DSCP and all, they all use the cgroup ID coming from the agent. So that is the easy mapping to all the processes, all the sub cgroup processes of the container.
Yeah, sounds good.
You started that saying Tupperware, right? So the first word of that sentence was Tupperware does, and then a big long thing that makes it easier, which goes back to what you were saying about you have to control the whole environment and have everybody cooperate. Yeah.
There was still a question in the chat.
Okay.
Can you talk more about the performance issues you've experienced with SE Linux? And maybe I'll extend, how does it compare to the measurements you did with the BPF-based file system?
Yeah, sure. Okay. So as far as the performance of our system goes, we eliminate, I don't remember the exact numbers, but 4 or 5 nines of events in kernel space, probably a lot more actually. So the hooks execute in a few hundred nanoseconds, and they just the whole thing is very fast. The data just gets, we do a few simple checks in the nice path, right? We do a few simple checks. The data is filtered, 99.999% of the time. That's it, it's done. It's discarded. And the system gets back to going on its way. The specific issues with SE Linux, I don't know if you remember any numbers, Shankaran? No? Yeah, there's sort of, it was before my time that SE Linux was eliminated at Meta. But that has, it's gone. Like I couldn't use it if I wanted to. It's been removed. And a lot of people had a problem with it. There's literally one place at Meta that it's being used right now, and we're currently replacing it with what Shankaran talked about, the LSM hook that he wrote.
I saw that you're using K-probes to hook into security file open.
Yeah.
So it's not, you're not using the LSM because of those indirect calls, right?
We're not using LSM because it hasn't been rolled out everywhere yet, the flag to enable it.
Okay. And the other part is for local storage. Like I saw you were using a map to index the.
Yes, so there's a reason for that. We support all the way back to kernel version 5.2.
Yeah.
And I needed the functionality to be able to look up the PID of, look up PIDs that I don't have the access to the task struct for.
Okay.
So that is why. As soon as we get into we're ditching 5.2, and I don't know if 5.6 is everything I need or not, but at some point we'll eliminate that and use task local storage.
And the other thing which you mentioned is to store the metadata for each process, right, and pass it on. You can do it with UUIDs, right? You can generate it doesn't have to be the C group ID or whatever.
Right.
You can generate your own UUID with the composition of the namespaces that you care of for your
Mhm.
definition of the container. But then you can pass it along, and then for that UUID in another map, you can share this is the container security relevant context for this process tree that I care about. It doesn't
Yeah.
have to be passed on to the blob, but it can be there. That's sort of what we do. I think that to answer some of the question about SE Linux challenges, right? One is of course the indirect call overhead for us. Second would be the ability to integrate into the container control plane seamlessly, and then to generate logs that we could easily consume. That doesn't work with SE Linux, and here I think it works.
All right. Yeah, thanks. Any other questions? Oh, did I have one more slide? Yeah, I did. Yeah, okay, yeah, just real quick. So yeah, the challenge is, the other challenge we have is working with files, which as we just discussed, are treacherous and will betray you. But so a lot of times we'd like to answer questions like, is a file in a certain directory? Is a file, is a file in a map of files allowed to open? Now, as we just discussed, maybe this is an incorrect approach and we should be using extended attributes instead. But so we did some work to parse out this information ourselves, because BPF dpath is like the only thing you really have to work, that the helper function you have to work with regard to files. And it just gives you a string. And also it can't be used in many places. In fact, I think it can only be used in like a handful of hooks. So we actually parse files out into a data structure where we store the file names in reverse order, because that's what you get when you walk the D entry, you get the file names in reverse order. We store the offset of each file name in an array. And then what that lets us do is quickly take basically views of the file. If you want its directory, you just kind of move up a few bytes, and you're now pointing at the directory that it resides in. And then if you want to look at the parent directory, you just kind of slide along further, and you can put those you can use those views to look up into a BPF map. So when we want to answer the question of is a file in a certain directory, we just slide along this this data structure, doing map lookups until we've slid to the the root file system. So it's not an ideal solution, but it does work reasonably quickly. Yeah, just in general, I wanted to bring up that working with files is and paths is exceedingly difficult in BPF just because of you have just C string manipulation functions and very limited number of instructions and loops and recursion all limited. So okay, I believe that's it. I'd just like to acknowledge the kernel team at Meta. They have supported this work a huge amount. We really appreciate that. And the rest of the network platform security services team. Thank you.
About your question about file paths, is it not possible to use something like an inode number superblock ID instead of file paths there? Have you considered that approach?
Yeah, so you can use inodes, and actually there is a detection at Meta that does use inodes that I'm familiar with. But there's the issue that you have to rescan the whole file system periodically to update it.
It also wouldn't work. At mount time. So
Yeah.
you would never have any reliable way of identifying anything.
Yeah, you also have to be aware of all the tricks of like swapping files and stuff.
Yeah.
You can do it, and there is a place where we do it, but it's tricky.
You'll have to hook number in different places to update your map.
Yes.
Yes.
Yeah, exactly. Yeah.
Yeah.
NFS file handle is what you need.
Yeah.
NFS solved this with the file handle.
Yeah, but there's also the arguments about the file handle right now on the list. So we don't have an answer.
My point was not using exact tuple that I just mentioned, but
Sure.
using some other alternative information on the file system instead of the file path, right?
Yeah, no, the file path has got to go.
The BPF tax.
I've got to use the file paths too. And I work at a company where we
The BPF tax tool that you mentioned.
Yeah.
How is that run? Is that just kind of a one-off thing? Do you guys have like a continual process, like continuous benchmarking that you're doing as you add probes and change things, or?
Yeah, I believe it's continuously run in prod it goes to a table, and then so you get like nice charts basically of like you could look at like this week's BPF data, like how much CPU did you use and how much memory did you use.
Okay. Set up for like every release, so if there is any change, any regression.
Okay. Yeah. So it's like continuous profiling in production. Okay. Cool.
All right. Thank you very much. And now we have a break until 4:30.
Yeah. I also said few. Okay. Sorry.
All right, so let's get started again. The next session is from Avery on extending non-repudiable logs with eBPF. Can take it.
Oh, okay.
Oh, you want?
I could just put it
Okay.
here. Is that okay?
Yeah.
All right. Can everyone hear me okay?
No, you need to take it more.
Is this better? Okay. Is this better? Okay. Hi, I'm Avery. I'm a first-year PhD student at Duke. This work started while I was an undergrad at Columbia and continued after graduation over the summer with George, James, and Hubertus at IBM Research. And so eBPF programs have large visibility into system state with the wide variety of hooks that are available to these programs across kernel subsystems. They're extremely powerful for monitoring. But when we look at getting output from these eBPF programs, we're looking at these event logs. And so it'd be great for visibility into system state to have logs that we are able to verify log integrity. And so that's where non-reputable logging comes in. If we were able to verify eBPF logs and root them in trusted hardware, we'd be able to take the output from eBPF programs and use their configurable, user-defined approach to providing non-reputable logging for workload and environment-specific data. And so when we look at this event log, we have no way of verifying its integrity. It's coming from user space, it's being logged by an eBPF program. But what if we were wanting to take this monitoring output and verify it remotely to build trust in system state? We would be unable to trust this. And so the addition of non-reputable logging would allow for the verification of workload and environment-specific data for eBPF programs. And so when we look at building this trust, we're starting with a chain of trust that starts when the system boots. This chain of trust is cryptographic measurements, so a hash of software components that is built up throughout the boot process. Each component will measure the component that precedes it to build this chain of measurements. And so these measurements are hashes that are then recorded in a trusted hardware. And so the trusted hardware we're talking about is a TPM. So a TPM is a microcontroller that is used to store artifacts that can be used to authenticate a system. And so a TPM has keys that are burnt in by the manufacturer that can be used to identify the platform. But we're really looking at these platform configuration registers, or PCRs. And so TPM has about 24 platform configuration registers. These registers can be changed by the OS or firmware by a process called PCR extension. And so a PCR extension is taking the value that's currently held in the register and concatenating it with the value that the firmware or OS wants to add and hashing this to put back into the register. And so this value held in each register is a verifiable chain of hashes that can be replayed to verify system integrity. And so when we're looking at extending these measurements, we have Linux IMA. And so the integrity measurement architecture aims to extend these measurements throughout runtime. And it does so by measuring applications when they're executed. IMA will measure executable content to detect changes in file integrity, and that can be used to attest to the integrity of a platform. And so IMA will take these measurements and log them in a log and store them in the PCR register as well to provide a chain of hashes for content that was executed on the system. And we can take these logs as well as the boot measurements to build trust in remote environments. This is done through attestation. And so attestation takes an attesting machine and it will take evidence. This evidence can be a TPM quote as well as a log that can be replayed to ensure the integrity. And it will be sent to a remote verifier to verify its integrity. And so when we look more closely at attesting system properties, we have an attesting machine with an attestation agent that will send a request to a relying party, which will send a challenge, and then the attesting machine sends evidence. This evidence is fed through a policy engine in the verifier and relying party to attest whether a system is in a trusted state. And if it is, we can send the machine a payload, whether that be keys or otherwise, because we have attested that this machine is in a trusted state. And so the project that we worked on is non-reputable logging of eBPF programs. So taking this chain of trust that's built throughout the boot process, we want to be able to measure and log the output of eBPF programs. And so given an application A that is loading an eBPF program, let's say that the eBPF program wants to store this measurement in a non-reputable log. And so this will be fed through our kernel module. The eBPF program provokes a measurement, which is then measured and carried out and processed in our kernel module interface. this interface will extend the measurement to an IMA log and store the value in a PCR register to assure that ensure that this log can be verified so that we can build trust in its integrity. And so when we look more closely at this measurement interface, this takes the form of a kernel module. And so eBPF programs are allowed to use kernel module functions since kernel 6.0. So we define a kernel module function, BPF process measurement. And so this function is available to eBPF programs, and it will allow them to provoke the measurement, and then this measurement will be formatted into a log entry, appended to a log, and extended to the PCR value. And from the eBPF side of things, we can see that this BPF process measurement function is used from the eBPF probe side. And so because we're interacting with the TPM, the eBPF programs need to be sleepable because we're interacting with the hardware device. And so any eBPF program can provoke the measurement and storage of these formatted files and data. And for our use case, we were looking at Linux IMA. And so when we look at this picture, we have IMA that is measuring system applications. What happens when we introduce containers into this picture? IMA will measure the individual applications, but there's no way of tying these applications back to the containers. And so when we look at the resulting log from IMA, how can we tell which of these measurements is coming from a container? How can we tell which application is being provoked by this container? To be able to verify container integrity, we needed a way to tie these integrity measurements to individual container instances, to build a chain of measurements from hardware up to each individual container instance to build trust. And so our goal was to take the container measurements and namespace them. Containers are isolated through a combination of namespaces and C groups. And so if we're able to associate the measurements with the namespace that provoked the measurement, we're able to separate each of these log entries with the namespace that the application is associated to. And so using the mmap file LSM hook, which is the same hook that is used to provoke measurements for IMA, we're able to attach an eBPF program. And this eBPF program will take the namespace of the task calling mmap, and it will use this to create a namespace measurement. And so the eBPF program will call the kernel module function for the logging and measurement interface. It will measure the file, append the namespace, and put this in a log in a way that we can attach the namespace to each of these measurements. And so if we look closely at this log, it looks a bit different from the original picture we had of the IMA log. That is because we're extending our namespace measurements that are provoked from eBPF to PCR11 to separate the host IMA process from the namespace process that we are doing our namespaced editions of the log. And so we can see previously that when this Podman container that was executing hello executed, we couldn't tell whether the host or a container was executing this. But with the addition of the namespace, we can tie this measurement back to a container that was existing on the system. And this is all done without requiring changes to the kernel through using eBPF. And so when we're looking at evaluation for extending to the TPM and appending to a log from eBPF, we're looking at on the TPM side, the hardware TPM side of the evaluations, we think that this is pretty fair. And then when we're looking at the vTPM, we see quite a bit of overhead when using an eBPF solution rather than an in-kernel solution. And so these evaluations were done by creating a wrapper to ptrace, which executed a file, stopped the file's execution after the first instruction. And so from there, we can then isolate the measurement and the TPM extension that's added from this overhead. And so this project aims to provide non-repeatable logging for eBPF programs. This has a wide array of uses, as we can now enable the logging of workload and platform-specific system properties from eBPF programs. Thank you.
I might, because I can't see that far, so I didn't understand. So you extend, so you differentiate, so you measure to different PCR register, or do you extend the hash?
Yeah, so we're recording two separate measurements because we're not interfering with the host IMA process. And so we have our measurements that are namespace that are being provoked by the eBPF program that is extended to PCR 11. And so we have two separate measurements, one from system IMA versus our eBPF version.
And if you have many more?
Of course, yeah. If at this point, we would be duplicating the amount of measurements by adding the namespace on top of this. However, this is configurable via host IMA policy.
But it feels you can do the same by just extending hash, I mean, cryptographic hash, so you can mix your namespace there, and you can even use the same register if you don't have to start using different registers.
We use different registers for just separating the two processes, but
I mean,
you're right.
it's visually it's better, of course, but like if you have to start scaling this, feels like you can. And if you don't want to make changes in IMA, you can just start mixing with crypto. The hashes will be different, and this is how you will differentiate.
Yeah, we actually do the namespacing, as you say. We extend the hash of the file with the namespace. So we could, because they would be different, we just put it on PCR 11 for that separation.
Yeah. Thank you.
Couple of questions. First one, in terms of performance, what sort of throughput of logging can you achieve with a hardware TPM versus a VTPM?
What exactly do you mean by that?
As in, how many events can I effectively log per second without overwhelming the TPM?
That's not something that we looked into, but
Okay.
it would be something to look into in the future for sure.
And the other was just, at the moment, you seem kind of constrained by fitting stuff into the existing IMA log format. Are you looking at potentially having your own log, which can be used to just have a less constrained format, a more flexible way of logging information?
For sure. Using the IMA log format, we were leveraging existing IMA infrastructure, and that's why we're inheriting the log, inheriting the policies. And so we could look into extending this to having our own logging format and having our own separate logs from IMA. We were just leveraging the existing infrastructure to make this a more lightweight solution.
Okay. I'm sorry, final thing. Is this achievable with the existing kernel, or do we need some additional patches?
Yeah, it is achievable. I'm running this on a plain Fedora kernel. With Ubuntu, you'd have to recompile the kernel with a different config, but it requires no changes to the kernel.
Thank you.
Great.
The thing about the performance, so there are, of course, other layer solutions to this. So like the thing that systemd does for that systemd journal D for their non-repeatable log things, they can also, there's a hook where you can put it out to whatever else you want to, whatever other system you want to be able to attest to a point in time of the log. And so you can not necessarily be bound to the performance of your TPM because it's sitting over an LPC bus or whatever else. And that, of course, would be low performance, but you can still do, the thing that makes me really excited about this, which I think makes it awesome, is the granularity of measurements that you can do. And then you can avoid the performance issues by just periodically taking the tail of the hash at whatever time it is now asynchronously and putting that to some hardware log. The question then becomes, if you are measuring an event which is tightly coupled with something that might directly impact your integrity, if you want to do that synchronously so that your audit log is coupled with that event, then that becomes a question of how you do that. But Yeah, again, it depends on your use case. Yeah, right. Yes, naturally, yes.
In your previous slide, when you had this performance measurement, can you elaborate some more? Like, what was the issue? Why eBPF was so high, like in the first one, for example?
Yes, they're two different machines. And so we don't know what's causing that overhead. We should have put a VTPM on top of the machine that had the hardware TPM and route measurements through that. So we are unsure what's causing this overhead just because of the way that we ran the evals.
Sorry, I was involved in doing that measurement. So the virtual TPM is much faster. It overheads magnitudes faster than the real TPM. So what you see there is that the real TPM, you don't see the difference because the overhead already is that big. On the virtual TPM, you see the actual overhead because the virtual TPM performs everything faster. It's in software. The TPM chip is a $10 chip taking 10th of a milliamp on the system. It's not very fast.
Any other questions, comments?
Yeah, I'm wondering if you had considered logs which are not just linear for the entire system, but some kind of hierarchical logging, so that if you want to do attestation of like if you assume that your kernel integrity is fine, but you want to do attestation of some particular subset of the workload which is isolated from other workloads, and you want to attest to granular events that have happened within that, if you could avoid a verifier needing to go through the whole log of events that are related to workloads that are unrelated to the state, like if you want to attest to something that's happening within your particular container, say, if you had a cryptographic structure which is not just one chain of hashes, but where it branches into, okay, here I have now this chain of hashes for the stuff that's happening within this namespace, and then that gets merged again periodically for getting put into your TPM or whatever, then a verifier would not need to go through all the events in your system, but could go through just the chain of things that it cares about, as long as the integrity of the system is not subject to those other things that it wouldn't care about. That would be, to the point earlier about other log formats, that would be potentially interesting to me.
Yeah, that would be interesting. We just explored log formats for our use case. And of course, this can be configured. eBPF is very flexible, so you can, because we're working within a kernel module, you can absolutely customize this to your use case and to the log format that you desire. We're just providing the infrastructure to do generic logging.
Have to be very careful about it, because, like, how do we just to say that you have to, if you do that, you have to be very careful to separate, like, what matters and what not matter for the, for the trust, because, all the kernel matters, but that's the easy one. But then, how much, like, what can you do with the other things? And it becomes actually, it can be tricky to get right if you try to kind of optimize this way.
All right, thank you very much.
We have 10 minutes. You're right. Absolutely. Yes. The use case that I think is interesting is.
Okay, cool. So you navigate.
And this does not work. Ah, okay.
It used to us.
And this is like the largest they can get.
Yeah.
Okay, yeah, thanks.
I mean, it will be larger over there, but hopefully for you it's okay.
And it should be okay.
Okay.
Thanks.
All right. So I would say we just keep going. We're 10 minutes early, but then we can hopefully maybe also more or less finish in time with the last session that you have. So the next one is from Jing Hao on kernel control flow integrity with eBPF.
All right, thank you, Daniel, for the kind introduction. So this is hi everyone. This is Jing Hao, and it's good to see that there are a lot of use cases of eBPF onto security today, and I'm going to add more to that. So today I'm going to talk about how we can leverage eBPF to implement a more advanced kernel control flow integrity framework. So as kernel developers, we all know that the kernel code makes extensive use of function pointers, and those function pointers, they add to the kernel flexibility. However, if you corrupt them, if they get corrupted, they allow the control flow hijacking attacks. And for example, in this really old, not really old, but old vulnerability from 2016, a privileged escalation is possible by overriding a function pointer following a use after free. So basically, in the kernel, there is this key revoke function, which is supposed to call a key type specific revoke function, which is stored in a function pointer. And with that use after free, the attacker was able to corrupt the function pointer and then redirect the control flow to her own revoke function, which in turn invokes the kernel credential functions to perform the privilege escalation. So, and to mitigate the control flow hijacking attacks, control flow integrity, or CFI, is introduced. So the basic idea of CFI is that it restricts your program control flow to its control flow graph. And it verifies each indirect control flow transfer, like indirect calls, returns, to make sure that those are valid to perform. And the CFG used by control flow integrity can be generated both statically or dynamically. So get back to our example. When the attacker tries to redirect the control flow to her own revoke function, with CFI deployed, it's going to fail the check, and the process will be terminated. So with that, however, the kernel CFI approaches currently are still inflexible. So on Linux, the existing CFI techniques is the LVM-based KCFI. So the LVM KCFI uses a static policy based on the function prototypes, and enabling or disabling this KCFI instrumentation requires, a changing kernel configuration, and therefore a reboot and reboot. So the problem here is really that the KCFI policies are statically defined, which makes them hard to catch the state-of-the-art CFI, which is always a moving target. And when you are trying to catch that target, you need to change your policies, but policy changes in turn requires kernel reboot and reboot. So those causes service disruption and also increase response time against new vulnerabilities, and it's just not flexible enough. And at the same time, the static policies actually makes it hard to leverage runtime context. So we believe that eBPF, it's actually a powerful tool in the context of kernel CFI. And so eBPF can make the kernel CFI easy to deploy, because if you write your KCFI policies in eBPF program and hook them onto the kernel, essentially you the changes or enabling, disabling the KCFI policies does not require a kernel reboot and reboot anymore. And then at the same time, the expressiveness and observability superpower of eBPF can really sort of beef up the policies you can write for KCFI. For example, those dynamic policies that also traces the origin of the indirect calls. And then finally, the eBPF can also make KCFI with finer granularity. And basically, we can selectively attaching the BPF programs to the particular call set we care about. So, with the promises of eBPF on kernel CFI, let's sort of try to lay out what are the needed pieces for a simple kernel CFI, eBPF-based kernel CFI. So let's consider this the simplest form of KCFI, which is just check against the static CFG. So for that, we definitely need a way to store our control flow graph, and then we need a way to obtain the information about the current control flow transfer. So basically, we want the source and the destination, and with those information, we would like to check against it and enforce our CFI policy. So put it in terms of eBPF, and the CFG storage can be done intuitively in an eBPF map, but the later two, namely the control flow transfer information and the policy enforcement, really depends on your attachment point. So before we're going into the actual implementation, let me first lay out the scope and the threat model of this talk. So we believe that the kernel is benign, but it may contain vulnerabilities that allows attackers to corrupt the kernel memory and therefore corrupt the kernel function pointer. And the attacker would attack the kernel by issuing syscalls or sending network packets. And here we trust the eBPF-based KCFI infrastructure. And right now, our current focus will be on the indirect calls. So when we think about instrumenting the indirect call, the most intuitive way of doing it in eBPF is to use a kprobe, because kprobe allows us to attach to almost any kernel text addresses. So here we can just directly attach a kprobe onto the indirect call instructions. And to obtain the control flow transfer information, since the kprobe takes in the PT regs as the program context argument, we can easily grab the caller and the callee from the registers. And then to enforce our policy, for example, when the check fails, we can use BPF send signal to terminate the offending task. And alternatively, we can also use the crash kexec kfunc to force a kernel panic if if that's desired. But the problem of kprobe is that it uses a interrupt by default. So this nature adds a significant context switch overhead whenever the program is triggered, and we actually measured a 26x overhead on our QEMU test machine for a single indirect call. So as kernel developers, you probably know about the jump optimization of kprobe, which optimizes the kprobe instrumentation into a synchronous jump. So with this jump, the context switch and the interrupts are no longer needed. So yeah, what about the jump optimization? The unfortunate fact is that if we're attaching to a call instruction, such a kprobe cannot be optimized, basically because the call instructions are not boostable in terms of kprobe. And another thing we tried is that since the LLVM KCFI is going to add these instructions right before the indirect call, and the first instruction is always a move, and so a move instruction is optimizable, is jump optimizable in kprobe. So can we just attach to the LLVM KCFI instructions? The answer is again no, because the LLVM KCFI instructions are indeed special. The KCFI failure handler needs to decode those instructions upon a KCFI failure, and overwriting those instructions will actually break the handler. So apparently, the question we want to ask is that is there a more efficient solution? So therefore, here comes our second approach, which is a fprobe based approach. And this is derived from Daniel Workman's suggestion on the use of app entry. So thank you, Daniel. So here, the kprobe multi attachment tab in eBPF allows you to attach the functions using the fprobe infrastructure. And here, in fprobe, the program is executed upon the function entry, and it is a synchronous invocation. So this makes it more efficient than interrupts. So for example, here we have this indirect call, and let's suppose that it calls into some function foo. And then if we attach to fprobe is going to override this 5 by no op at the start of the function into a call to the fprobe trampoline, which in turn calls our program. To obtain the control flow information in fprobe programs, we can use the stack trace functionality from eBPF. So basically, we can do BPF get stack to get the caller address, and for the callee, it is always the currently probed function. So getting that is also easy. And in terms of enforcement, this is similar as kprobe. You can choose to use, BPF send signal or crash kexec. One thing worth mentioning is that the use of fprobe to perform KCFI enforcement requires the use of LLVM KCFI, because fprobe makes the implicit assumption that whenever you do a indirect control flow transfer, you're always landing on the entry of a function. But in reality, you may not always do. So LLVM KCFI will enforce that such a control flow transfer always land at the entry of the function. But with that being said, an fprobe does has its own limitations, and the first limitation is that fprobe has a less coverage than the on the indirect calls on KCFI than the LLVM-based KCFI, and those are because a lot of functions you cannot attach fprobe onto. For example, there are functions in the kernel marked as no instrumentation or no trace, and to make it worse, all the functions in the trace subsystem and all the library functions are just compiled without fprobe ftrace support. So in total, we found that there are around 10K functions out of the 59K on our test kernel that cannot be attached. And at the same time, an fprobe does not distinguish between direct and indirect calls. This means that the program will always be executed whenever the function is invoked, no matter it's like invoked directly where we don't need to check, or it's invoked indirectly where we do want to check. So there are, as we all know, that there are much more direct calls than indirect calls in the kernel. And in fact, when we test this on LE bench, we found a 7 times slowdown on our test queuing environment. So let's quickly sort of recap what we have at this point. So we have 2 mechanisms, kprobe and fprobe, and kprobe can attach directly down to the indirect calls, where fprobe attaches to function entries. And in terms of the invocation of eBPF, kprobe uses interrupt, and fprobe is just a synchronous function call from the trampoline. And in turn, the kprobe suffers from context switch overhead, where fprobe only has function call overhead, but it also pays the overhead on all the direct calls. And lastly, for KCFI coverage, kprobe can get roughly the same as LLVM KCFI coverage, where fprobe has a 17% lower coverage than LLVM KCFI. So at this point, we can conclude that the existing BPF attachment is actually not enough for a practical KCFI instrumentation. So we think that a new attachment mechanism is needed. It would be great that if we can do synchronous invocation And at the same time, we can just instrument precisely the indirect costs covered by LLVM KCFI. So therefore, we implemented our own framework, and we call it the eKCFI. So it's basically a new way to hook eBPF programs onto those indirect cost site. So our eKCFI module is gonna redirect the control flow. It's gonna instrument the kernel code and create a hook point at the indirect cost, which is gonna redirect the control flow onto the KCFI trampoline. And the eKCFI trampoline is going to perform a synchronous invocation on the eBPF policy programs. And similar to you know, kprobe and fprobe, the policy program still decides whether to allow this control flow transfer or not. It can choose to continue execution or trigger a kernel panic. So let's take a look at how we actually instrument the kernel code. We are pretty much using the same type of, you know, the same mechanism already used by fprobe. We use LLVM to generate two extra instructions at indirect control flow transfers. This includes a move to save the callee address into RAX, and the next instruction is a 5-byte no-op instruction, which can be dynamically overwritten, just like what we had in ftrace. And in this way, we can dynamically rewrite no-op into a call to our eKCFI trampoline. And this trampoline, it's actually responsible for a bunch of stuff. And it's gonna save all the needed registers. It's gonna obtain the callee from RAX where it is stored into, and also obtain the caller from its own return address. And then it's going to prevent recursive KCFI instrumentation, because that will result in an infinite loop. It invokes our eBPF program with the KCFI context. And finally, it interprets the return value from the program to perform the corresponding actions. So here, our eKCFI trampoline invokes the BPF policy program. And in the context of eKCFI, getting the indirect control flow transfer information is easy, because the trampoline already packed the caller and callee information into the program context. So you just directly grab it. And then for the enforcement, it's implemented by the program return value. It's kind of like what we had in seconf. So if the program returns a eKCFI red panic, the trampoline is going to trigger a kernel panic in turn. So here, let's add eKCFI to our existing design space. So here we have eKCFI, which hooks onto the indirect calls, and it performs a synchronous call on our eBPF program. It only pays the function call overhead, and its coverage can be exactly the same as LLVM KCFI. So we evaluated the performance of eKCFI onto you know, some applications. Here we tested it on Nginx and also Linux kernel compilation. The policy we enforce on eKCFI is a fine-grained CFG, which we obtained from the dynamic traces. So we found that eKCFI can achieve roughly the same level of performance as the LLVM-based KCFI, at least on the macro benchmarks. And but I guess a good thing to note is that the performance really depends on how many indirect calls you hit during the execution. So we also tested onto the LM bench macro benchmark, and again we enforced a fine-grained CFG from dynamic trace. So here, from this graph, you can see that around half of the benchmarks, the performance is actually on par with LLVM KCFI. But also for certain benchmarks like PO and Select, the performance is like almost 3 times slower than the LLVM-based KCFI. Another interesting aspect of eKCFI is the you know, the no-op overhead. So basically the instrumentation overhead we have, even though the the KCFI is actually not enabled. So here we actually plotted the overhead of NoOps added at different levels. So here we have NoOps added at indirect call level, which is exactly what eKCFI is doing, and we have the NoOps added at basic block level and instruction level. So basically, before each instruction. And so the takeaway here is that adding it at indirect call level, so instrumenting kernel code just at the indirect call side, does not have a huge overhead. But if, say, someone wants to instrument arbitrary kernel instructions using this framework, she is going to pay for up to 75% overhead on the instruction level instrumentation. So, and I hope I convinced you that eBPF is like it's a powerful tool in the context of KCFI. But here, let's face the limitations of eBPF-based KCFI. So the first problem is that we have to trust the eBPF subsystem. But in our threat model, we actually assume that the attacker can corrupt kernel memory. So that means the attacker might be able to corrupt memory of the helper functions or the maps. And in terms of protection, we think that hardware-based mechanisms, for example, in Intel MPK, might be useful for maps. But the kernel helper functions are still hard because they call deeply into the kernel. Lastly, I think I want to note that eKCFI does not mean to replace the LVM-based KCFI. Instead, we sort of complement the LVM KCFI to further enhance the security of the kernel. And to conclude, so we think that eBPF can make kernel CFI more flexible and usable. And unfortunately, existing BPF mechanisms are insufficient for a practical CFI framework, basically because of the performance and hook point problems. And so here, with develop the eKCFI framework, which is a eBPF-based KCFI framework with a new hooking mechanism for efficient indirect call checking. So that concludes my talk. Thanks, and I'm happy to take any questions.
So could you please elaborate a bit more on your use case, the use case you're trying to enable with this mechanism? Because you mentioned that you want flexibility, and you gave an example that you don't want to recompile a kernel, but when do you want that flexibility of changing the CFI policies, given that the kernel doesn't change? So I'm not understanding.
So yeah, and that is a good question. So we know that the CFI is still quite a hot topic, and it's the state-of-the-art CFI is like it's a ever-moving target. So if you want the state-of-the-art policy in the kernel, you probably need to change it very often. And in that case, if you are changing your policy, then you're gonna recompile your kernel if your instrumentation are like statically compiled in.
Okay, so you're targeting the use case where kernel stays the same, but you want to, use latest and greatest, like, the control flow mechanism following.
Exactly.
So, okay.
Yeah, for example, say you're just using a CFG-based KCFI policy, and then someone said that, okay, I have a CFI policy mechanism which is based on the origin sensitivity based on the origin of these function pointer assignment. Then apparently you need a different way to instrument the kernel, and then you basically have to recompile.
But in principle, it will still require you to use, like, you can't, because you said that you can enable it, like, on certain functions and things, but in order to get a proper protection, you will have to enable this and everything. So and as much fine-grained as you want, since you're talking about, the latest CFI policies. So in fact, you can't just go and enable it on some critical functions. You will really, like, it's like it would be like a second CFI on everything then for eBPF.
Right, so, yeah, but I guess the selectively attaching to the KCFI function, it's sort of a it's sort of a performance optimization in case I mean, if you don't care about performance, then why not applying it to all the kernel functions you care about? But you know, and if you really care about, if you now care about the performance, and then there are some components like you know that are not that known for like informers for the vulnerabilities, then you probably just gonna protect the critical part of the kernel.
But critical, like, you know, you gave this example of commit creds. Of course, you can kind of, you know, protect, you know, who can call into commit creds, but it's possible to kind of, you know, do wrappers around. So in principle, like, you know, it's rope chain, so you can try to build more complex chains. So in order to have full proven, you actually have to cover everything. That's why, you know, a full control flow. But anyway, it's interesting. Thank you.
Yeah, thanks.
So what you did was this EKCFI trampoline stuff, right? It sounds like what I would expect raw trace points do. Did you consider adding like kind of trace points?
Yeah. So I guess okay. Let me put it this way. So normally when you do a trace point, you have to add the function call into the kernel, right? So apparently you don't want to manually add the like trace blah blah blah, say trace EKCFI, that trace point function before HA indirect calls. And what
the assumption was that like you can instrument it somehow or something, but
yeah,
I'm just curious about the performance implications actually.
So yeah, I guess what you can do with trace point is that you can rewrite that no-op to point to your trace point hook. But trace point actually has its own problems in terms of EKCFI because the trace point hook, I mean, the trace point hook actually it's actually pretty generic. It contains not only the code that powers the BPF trace point, but also like trace point K other stuff. So actually that adds more overhead than just do like the F-entry way. Oh, now not really the F-entry, but EKCFI rewriting it to a trampoline.
Very interesting talk. I was wondering whether so essentially you're adding like NOP5 in front of every indirect call, if I understood. Yeah. So have you considered adding instead of NOP5, like NOP10 or whatever you need to? And then instead of doing like policy collecting like caller and like callee addresses and doing lookup based on two addresses, do it exactly the same way that LLVM does. Like compute some hash for every like different call site, and insert instead of like populating your trampoline with just an indirect call to your eBPF program, like put whatever instruction necessary, like compute that hash, put it in there, and on the caller side, just check this hash. Exactly the same way LLVM does, but do like everything dynamically.
So let me try to understand your proposal.
Like, I'm proposing the same what LLVM does, the same code that LLVM generates, but do the same dynamically.
Right, and I think there's another thing I didn't mention about the LLVM KCFI is that because the policy it implement is just based on function prototype, it's not a in the KCFI world it's not a fine-grained KCFI policy. So if you want to do a more like a fine-grained KCFI policy, I think you sort of need to do the eBPF way.
We'll probably take it offline. It's easier to whiteboard.
Can you talk some more about the control plane aspect? I mean, you populate this map with the addresses, right?
Yes.
So that might change maybe for every reboot, or like how? I'm not quite sure. Like.
Yeah. So right. So I have to admit that right now it's sort of something we didn't thoroughly think through. At this point, what we did is that we boot the kernel and we dynamically traced the function, the indirect function calls. So it's the same kernel, so that address always works. But yeah, that's a good point.
And then you also need to have some kind of workload that runs exactly the
Exactly.
things you want to populate in the map.
Right.
Otherwise, you panic, right?
Yeah.
So my question is, have you done this for just the static pieces of the kernel, or will this work when kernel modules come into picture?
Right now, it's only the the core kernel itself. We do not consider kernel modules, but I think that since the instruction, the extra instrumentation insertion is compiler based, so it should work for kernel modules as well.
But that would mean you have to load the map dynamically.
You have to. Sorry, what?
The graph, the control graph, that can change, right? When modules come into picture.
Yes. Right. So basically, you need to recompute the control flow graph.
And that is another security vulnerability in all the things that you have listed. So that is one more way an attacker can target you. And
sorry, could you repeat?
no, if you change the control graph for your system in between runs, that is another potential vulnerability in your kernel. Isn't that right?
Right.
Okay. So right now, this is only for static.
Yeah, right now it's only for the core kernel image.
Not just to say that you can protect the changes. So if you need to, if you now loaded a kernel module and you need to upload, update the graph, and it's authorized operation, you can make it authorized operation. So I don't think that is a problem.
The same problem also exists for eBPF programs itself, right? Because you also don't know when you load a program to hook that this new program could be executed if you want to protect that as well.
Right. I think currently the eBPF programs are not protected. I saw that the special function is like marked with no CFI.
Cool. Any other comments? Looks like not. Thank you very much.
Thanks.
No, okay. Just clicking the mouse. Okay. All right. So the next talk is from Neil on modernizing Android BPF.
How's it going? I'm Neil Capron. I work for the Android kernel integrity team, and we're looking at enabling modern BPF in Android and how it incorporates in our security model. So a little bit of background, the Android basically is not modern. So we don't have libBPF, we don't have an updated BCC or BPF tool. We have a custom or curated library, I say that loosely, to enable BPF development that was created prior to libBPF. And really, it doesn't have any of the modern functionality. We don't have core, we don't have the libBPF helpers, we don't have BPF trace, or we are very manual BPF functionality. Oh, sorry. So some of our goals, obviously, we want to join this century in BPF. We want to enable core. We want the modern development mechanisms and capabilities that BPF offers. The other piece that my focus is enabling vendors to use BPF, and I'll go into a little more on the different roles in the Android ecosystem here in a second. And ultimately, while I'm focused on BPF trace points, we're at a point where it's a pivotal time where we're going from this very archaic, outdated system to looking at bringing us up to speed here. So we want to make sure that we do that in a way that's compatible with upstream, and we can start contributing back upstream. So some concepts that we need to understand about Android that make it fairly unique. We have a standard C library called Bionic. Each user plus application combination has a dedicated UID. So that's, I'm new to Android. That was one of the things that kind of sent me for a loop. But a user could be the person using the device. It could also be a work profile. And so that's how one of the security mechanisms that basically allows compartmentalization on the file system there. Standard, we have 2 kernel versions per release. The latest Android 14 has a 5.15 kernel branch and a 6.1, so we are behind upstream a little bit. A lot of the efforts of my team has been to minimize that timeline gap. And it's important to know that older devices can upgrade to the latest OSs with their previous kernels. So this is some of the challenging, it poses challenges with that. A couple of the other terms and acronyms, we have ACK, which is Android Common Kernel. Basically take an upstream kernel and have a series of patches that go on top of it, the generic kernel image, and then particularly we're interested in the KMI. So this is the ABI stability mechanism that we've worked with vendors to define for each kernel branch. So Android 5.14, 5.15, and Android 14 6.1 have different KMIs, and going forward, the Android 15 6.1 kernel could have a different KMI than 14 6.1. The other thing to note is we do have DM-Verity-based file systems where the BPF programs are stored, so we trust the source of the BPF programs. So this is one of the differences compared to a lot of the security mechanisms that I've looked at on the mailing list so far. The other piece to note is we have a variety of architectures that we support. You can see ARM v7 is kind of being deprecated, and we do support RISC-V going forward. Sorry, RISC-V 64. So some of our stakeholders, we kind of have the 2 sides of things here. We have debugging and development. That's, again, a debug-enabled device, and that's going to be the engineers, performance, test engineers, et cetera. And then we have this release telemetry and functionality side of things, and this is BPF programs that are running on production devices. And so that's the focus of this talk. It's not so much the dynamic tracing and debugging, while I would love to get there eventually. My focus right now is that release side of things and modernizing that. So with the release side, we have the system OS level programs, which are part of AOSP, are released yearly or going forward quarterly releases and updated quarterly. The networking code is in what we call an Apex, and this is a redistributable package that's distributed via the Android Play Store monthly, and it runs on old devices, so all the way back to 4.9 kernels. So that's been one of the another challenging piece of updating libbpf is we have these old kernels. Additionally, so we have the SoC and device manufacturers, and I'm referring to them as vendors in this conversation. And my goal is to allow them more access into BPF and being able to really use this powerful technology. Some of the security restrictions we have in Android for BPF. Right now, we have a single BPF loader. Basically, it's an application that runs in early init and walks the file system looking in these specific locations for classes of programs to run. A little more on that in a second. And I think a lot of the reason for the single loader was at the time when it was implemented, it required capsysadmin, and we couldn't really expose that to a lot of user space applications. It's one shot, so once it loads the programs, you can't continue to, or you can't load additional programs, it'll exit, and it's kind of done for that boot. There are many SE Linux restrictions. Don't need to go into those right now, but we have SE Linux control on that. This next bullet point is actually incorrect. We're working on that. And the BPF program types are restricted based on their source. So looking forward, oh, I'm missing, it'll come later, but basically the networking code has the most use cases enabled, system is limited, and the vendors are limited to socket filters right now. And of course, F-entry, F-exit must remain disabled on release devices. So this is a block diagram of the BPF loader application. You can see those different ELF sources on the left side there. So we've got system in green, networking in blue, and vendor in orange. And basically the BPF loader opens them, compares their program type with an allow list based on where that ELF file is located on the file system. So again, we trust the programs are provided by a verified source, but we want to control what they can do and where they are attached, ultimately. And then you can see that user space Android specific library, we'll call it. Yeah. So this is another representation of those file systems. So you can see these are the different pieces that can be updated independently on an Android phone. So kernel, obviously, the vendor BPF programs are separate, and then the system. Currently, the BPF loader is part of the AOSP Android release, but it relies on the BPF library, which is in the networking apex for that loading piece. Similarly, the vendor programs relied on that BPF library. So that required a lot of stability and maintenance looking back all the way to the 4.9 kernels on these really old devices. So that's been one of the pieces that we've been working on lately. And then obviously the system and networking programs underneath that. These are our supported program types. We have a variety of networking pieces, a couple system, K-probe, socket filter, and trace points are enabled for system, and only socket filter is enabled for vendors right now, and they've requested K-probe, perf event, and trace point access. So some of the other challenges that we encounter, boot time, because it is a single-threaded application that starts in early init, it's blocking a lot of other stuff from running. We need to be very cognizant of how we are blocking the system there. Additionally, memory overhead's a pretty major concern. We run on phones which may have a decent amount of memory, but then watches or other devices which are very limited and constrained. The big piece that is a challenge is that the ABI compatibility between kernel, user space, and the BPF objects that can all be independently updated. And of course, security is a primary concern as well. So looking at enabling core in Android, we could do a custom Android-specific library. I absolutely do not want to do that. That would be a maintenance nightmare, but we could optimize it for a specific use case. I don't think this is the way to go. We could take libbpf, integrate it into the existing BPF loader. It doesn't solve the boot time problem. It could cause a significant increase in memory usage due to BTF data associated with each object. And again, it doesn't resolve that compatibility issue between the different programs, libraries, and systems. And then the approach that I've been considering lately is basically what I'm calling a native libbpf approach, where developers and system integrators should be able to use whatever library they want, have the same syscall interface, and then the big thing that we need to implement there is an access control mechanism to control where the program types and the attach points that they can access from the kernel side. And there may be other approaches. That's why I'm here. I'm here to learn and hopefully get some input from the experts in the community. So I appreciate your help there.
Can you go back to the slide where you say access control mechanisms? Does your access space mechanism, control mechanism need to be in user space? Could you not ship a BPF LSM policy that does the access control there?
That's what I'm getting to, is how to move it into the kernel space, hopefully. So yes, cool. That's my plan. So attach point access control. basically we need to verify that the trace points are part of that KMI stability layer that we have. And again, it varies between kernel branches, so we need to have it updatable. And it's important to understand that after a kernel release, you can have KMI additions, but you can't change or remove things. So again, we could continue to maintain that user space allow list and extend it to access or attach points as well, but it doesn't necessarily solve the scalability issue that we are encountering. So the next piece is BPF program, kernel module-based access control. This is kind of an iteration. Some of the constraints that we have are working with existing devices and existing kernels that are in development. I know there has been a lot of talk on the mailing list regarding gatekeeper applications and the tokens. I really like the token pieces, but I think we will long-term need to extend that to access control unless I'm missing a piece there in order to integrate it in this mechanism. And I'm not as familiar with the LSM side of things, so I unfortunately was double booked today and I missed the update there. I will follow up when the videos are posted. But so short term, we need to resolve this, on the 5.15 and 6.1 kernel is a challenge. So short term, one of the proposals that I've come up with is basically hooking into BPF program load and BPF program attach, and doing the attach the allow list verification there in the kernel that would enable the libbpf or whatever library to be used in user space. But we need to ultimately compare it back to the source of the kernel or the source of the program that's being loaded. And so that's where I need to examine and investigate that of how we, whether populate a map or have another program on the file system. So the first approach is the user space approach. You can see from the last piece, basically, we broke out the network BPF loader to the side there so that they can continue maintaining support for the old devices with their current solution. BPF loader has been updated in this diagram to use libbpf to enable that core step, but again, it's a very linear flow still. Obviously, we can look into parallelizing that as well. There are challenges around that. And then the other piece that was added here is the attach point allow list in the BPF loader application. So this is the native libbpf approach that I'm pursuing right now. You can see, again, we have our colors. The green is system, vendor is orange, and then blue is off to its side in its apex there. So this really allows the developer flexibility of using whatever library. It resolves the compatibility story of trying to load a vendor application with potentially a different library-based BPF loader or a different system library there. And then the new piece is that access control BPF program in the kernel there. So yeah, that's the core of my proposal. I want to kind of get some feedback around that. I do have some open questions for both, but yeah, before we get started on those, are there any questions for me?
Well, I just want to say that I totally support this last variant where like libbpf is embedded into the application, and that's what we in our internal at Meta, the internal like Android use cases actually are going with. So if you can pull this through, that would be great, probably.
Yeah, so this is my goal. I think there are some security roadblocks between me and reaching this. Ultimately, we need to have a thorough security review around this. We need to determine what's viable for an allow list, what's not, and really figure out best practices there. So that's going to be my next hurdle, is really engaging with the Android security team on that.
Yeah, just very small remark, like in your table of program types that you want to enable, you have trace point, but you don't have raw trace point. I would recommend to look into that because it's more performant, it uses the same infrastructure, but it's more performant. So like if you're enabling trace point, you should probably enable raw trace point. But also the question is, like you're saying, access control and like proc attach and stuff like that. Like well, two questions here. Like how much you can backport?
Sorry, can you repeat
How
that?
much, like those 5.15 and 6.1, can you still backport some newer patches into that?
Potentially, yes.
Well, because like whatever we add, right, like you'll need to bring it to older kernels. But then the second part of the question is like, what do you think you need?
What would I need to backport or?
No, what would you need like to add to the kernel to do the success control, like on attachment and all that stuff? Because I think we have a bunch of LSM hooks, and we are actually like in the latest kernel, we are updating them, like making them token aware and like placed in slightly better place. So, you know, stuff like that.
So at this point, I don't know what I need yet. So it's awesome to hear that the hooks are there. I will definitely do some investigation there and follow up on the mailing list. So that's awesome.
I mean, you mentioned a particular thing in your slide that said reading the BPF source code in the kernel or access to the source code. BPF prog load, you can hook and you can basically walk through the instructions. You can filter on what you're attaching to at that point as well. So your KMI can just be a map that your LSM program can read and see which access points you're allowed to access based on which program type. So I think it can be done with this, but it can be done with an LSM program that you load very early on at boot.
Okay. Is there a recommendation of this versus an LSM program? I am not familiar with LSM, so this is new to me. But if you have a recommendation there, I'd definitely.
We can find a hook and we create the recommendation, right? Okay. There is no recommendation yet.
Perfect. Thank you.
Question from your slides where you mentioned like vendors and they requested this or that type. Can you share like more details, like why they want, let's say this, next. Yeah, why they want kprobe performant and trace point? This is just observability or what?
So to be honest, I've been asking that question on a lot of things. There's been little information, but not extensive information on why they're trying to do or what they're trying to do with these things. I think ultimately a lot of it is based on dynamic tracing for performance monitoring or things like that. And ultimately, I don't know that kprobe is the right answer for the vendor piece because it really opens up access to the kernel. So I have concerns around that. I don't know that we will enable all of these. Again, I'm focused on tracepoint right now, but that's one of my questions is what should we allow? And it sounds like raw tracepoint. Are there other ones that you think are reasonable for this model? Yeah.
Can you elaborate some more on the boot time issue? It's basically that you want to have the enforcement piece first before everything else comes up, right?
Yeah, so due to, and actually if I go back to well, this is fine. Due to the nature of the networking programs of bandwidth monitoring and other functionality, they need access to them early on in the boot system. And since we have a one-shot single program here, it had to basically be as early as they are, or the networking side of things need to be. Yeah, so that's why it has to be so early. Now, could we extend the user space functionality to have multiple phases? Yes, most likely. That may be an easier approach to deal with security as far as breaking that up. But ultimately, I don't know that that is the right approach because ultimately, I imagine BPF usage is going to continue to scale. And so even no matter where you put it in the system, it's going to continue to be a problem there. So. Anybody else from this side of the room? All right. Thank you very much.
Yeah, thank you. All right, looks like we will be on time today, which is great. So the last session is from Quentin about a book that he wrote. Good. Okay.
Thank you. Yeah. Hello, everyone. So yes, this is a bit of a particular session. There's nothing technical here. That's about that book we've written for children and about eBPF. So in case you don't know me, I'm Quentin, working at Isovalent on Cilium's data path. I maintain BPF tool. I've been working with the BPF since 2016. And at the time, the references, the resources we had to get into eBPF, to get started with it, to get more familiar with the topic were more scarce than today. So one of my first contributions to the eBPF community was to write that blog post at the time, trying to list all the resources we had. Nowadays, we have a lot more resources, thankfully. So we have tutorials, we have a few books about eBPF, we have eBPF.io, which is a great website to get started. We have a lot of blog posts and plenty of other resources that are not listed on this site. So we can accommodate the needs for the newcomers to eBPF, trying to get into this thing they've heard about for Linux. We can also provide some more documentation for the more advanced users, trying to deploy it in production to understand and improve the verifier. But we still don't really have any resources for my daughter, who is 4 years old, and is asking about, well, what's this B for? Like, you have it on your T-shirts, you have it on your jumpers. Why the B? And that also stands for any decision taker really who've heard that they can improve and program the kernel with eBPF, but hey, what's a kernel in the first place? So we've been trying to address this. So we've taken inspiration from the existing book for Kubernetes, which tries to explain Kubernetes in a simple way through a story for children. And as you can see on the picture at the bottom, there are the illustrations on the left side of the book, and then diagrams and explanations on the right side. So we've been doing that. We've been doing the same for eBPF. When I say we, this is a colleague of mine, Bill Mulligan, and myself, and we contracted an illustrator for doing the illustrations. So we are very proud to present Buzzing Across Space, which is the resulting book. As you can see from that physical copy here, we've got both diagrams and drawings. But on the slides, I'll just go through the story for today because, well, I just thought it was not necessary to go through eBPF basics here. So this is a story of Captain Tux flying his starship through space and basically trying to make business, right? To carry things from one planet to another one, to carry passengers, to carry all kind of cargo. And he's accompanied by his crew. There are passengers on the ship. Everything's going well, or is it? Every time he needs to change some part of the engines, of the equipment, it gets a bit tricky because sometimes you got to change some pieces while you are in flight, or when you are on a not really suitable planet. Like if it's all water on the planet here, it's tricky to fix the ship, to fix everything we need. So here we can see two characters trying to change a piece of the reactor in space, and Captain Tux looks concerned. It works, but it's not ideal. So how can he improve the situation? And one day he reviews the crew, and he finds that EB is here. He didn't really remember about EB. She's been around for years, just like BPF in the kernel. And Captain Tux has this idea. He thinks you're small enough to go into the engine room and to fix it from the inside. So do you want to help? Are you interested in trying this solution? And of course, EB is really eager to help. So what gives? So first, they have to get into the engine room, and EB is very willing to help, but she's a bit afraid of breaking stuff, right? The engine room is very smoky, so you've got to get a very good eyesight to avoid breaking things. So Captain Tux makes sure that only the bees that can see well can go into the engine room. So that translates into Captain Tux providing them with goggles so they can see through the smoke and don't break things, which is of course a picture of the verifier for the kernel. And they start working in the engine room, but soon they realize that they would like to be more efficient, to go faster at fixing things. So they ask for some kind of special device, some kind of special droid that could translate the instruction from regular language into special. I don't remember. I think we call it buzz code in the book, which is of course the picture of the JIT compiler that we need to go faster, to be more efficient. So Captain Tux says no problem, and he works on a device to do just that. And the bees start to work more and more, and they establish a workshop inside of the engine room. They get these shelves so that they can store things and share things. So one bee is handing over stuff to the other one, just like we have maps to store data and keep states and share data with user space. And this is going well. This is going very well. The ship starts improving in all sorts of ways. It's getting faster. All the changes are now quick and efficient, and that's good. And the bees are thinking we should maybe go and talk to the passengers, see if we can also improve their trip, their experience during the flight. So the passengers have long been complaining about sending messages that they can do, but not in their own encoding. So is there a way that we could maybe be more flexible for every kind of messages going in and out of the ship? Well, yes, there is. The bees are working on that. Can we also be more efficient for sending them in terms of performance, well, receiving them too? So here we can see the bees and a gopher, but mainly the bees, trying to install a big antenna which represents XDP on the ship. And once they have improved networking, they turn into traceability, observability, and we have here the detective bee trying to understand everything that's happening inside of the engine room. We can also observe on the left part of the drawing a flame graph on the screen. So that's the bees from inside of the engine room trying to profile and understand everything that's going on. And so this is all going great. So great that the evil ship that you can see in the picture is trying to attack the ship, to steal the technology, to really to by greed to destroy things. Happily, we have the bees working on the ship, and they've also been optimizing the lasers from the starship. So we have really eBPF that can be used for defense and security, and that helps defending the ship in that case. Alas, the ship has been slightly damaged during the fight, so it had to land on a planet and to bring some more pieces to make the repairs. The bad thing here is that the pieces have changed since the previous model was used to build the ship. So we have an issue. How can the bees use these new pieces to replace the other ones that were different? And they're thinking that's a big issue. But talking with Captain Tux, we realized maybe we can do some kind of map of the ship. So they build this pretty awesome scanner to map all components from the ship to their locations and to the shape they have, to everything they need. So that's Corey, obviously, and they managed to go on and fix the ship and move forwards. So we're getting near the end of the story. The bees have been talking with passengers. They've been helping with the ship, helping with the different use cases from the passengers. And they are now deciding that they should also be helping at other locations in the galaxy. So they are kind of splitting up the hive. And some of them are working, are going away to work on different ships, on different, I don't know, different environments. And that stands really for the different runtimes that we're having for eBPF. Like now we have eBPF for Windows, we have some user space interpreters, we have a lot of projects based on eBPF. So that's the kind of diaspora of the bees everywhere in space. And the last page is just that really. The bees moving on to new planets, new territories, to spread their good word, to spread efficiency and flexibility, programming, everything, everywhere. And they live happy for a very long time after that, and that's a very happy ending. So that's it. You do? Tell me, I can explain more. What?
Room and the person running the calendar room is saying no bees here, please.
Did someone send no bees? Are you referring to?
No, I'm just kidding. I think they should.
No, sorry, say again.
It's okay. Conveyed my message.
Okay, so I hope you like the story. I have some books here to some physical copy if you're interested. Happy to give them if anyone's interested in receiving a free copy. And that's it. I hope you enjoyed the story. We enjoyed the book. Thank you.
All right. So first come, first serve. If you want to grab a book. And that concludes today's sessions. There will be, there's an evening event today. So there will be buses outside of the hotel that will take you to the Hardwood Brewery. So yeah. And tomorrow we will start at 9 a.m. So not 9:30, but 9 a.m. Okay, thanks. Have fun.
Tomorrow is tomorrow there is no. We'll do it.
Maybe two, yeah. Then Thursday I'm also here.
I'm another question for you. I was able to buy a +1 on the website for the event. Yes, right?
Okay. I don't know.
Okay. No, it said it could bring a guest, but
probably. If you manage to catch some of the organizers.
yeah, okay. I'll look around. Yes, thanks. Yeah. Yeah. Okay. Yeah, thank
Yeah, yeah.